Preface and Introduction to the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 1. Preface. It may be proper perhaps to state here, in a very few words, the objects which the author had in view in drawing up the following history of chemistry. Alchymy, or the art of making gold, with which the science originated, furnishes too curious a portion of the aberrations of the human intellect to be passed over in silence. The writings of the alchemists are so voluminous and so mystical that it would have afforded materials for a very long work. But I was prevented from extending this part of the subject to any greater length than I have done, by considering the small quantity of information which could have been gleaned from the reveries of these fanatics or impostors. I thought it sufficient to give a general view of the nature of their pursuits. But in order to put it in the power of those who feel inclined to prosecute such investigations, I have given a catalogue of the most eminent of the alchemists and a list of their works so far as I am acquainted with them. This catalogue might have been greatly extended. Indeed, it would have been possible to have added several hundred names. But I think the works which I have quoted are more than almost any reasonable man would think it worth his while to peruse, and I can state from experience that the information gained by such a perusal will very seldom repay the trouble. The account of the chemical arts with which the ancients were acquainted is necessarily imperfect, because all arts and trades were held in so much contempt by them that they did not think it worth their while to make themselves acquainted with the processes. My chief guide has been Pliny, but many of his descriptions are unintelligible, obviously from his ignorance of the arts which he attempts to describe. Thus circumstanced, I thought it better to be short than to waste a great deal of paper, as some have done, on hypothesis and conjecture. The account of the chemistry of the Arabians is almost entirely limited to the works of Geber, which I consider to be the first book on chemistry that ever was published, and to constitute, in every point of view, an exceedingly curious performance. I was much struck with the vast number of facts with which he was acquainted, and which have generally been supposed to have been discovered long after his time. I have therefore been at some pains in endeavouring to convey a notion of Geber's opinions to the readers of this history, but am not sure that I have succeeded. I have generally given his own words as literally as possible, and wherever it would answer the purpose have employed the English translation of 1678. Paracelsus gave origin to so great a revolution in medicine and the sciences connected with it, that it would have been unpardonable not to have attempted to lay his opinions and views before the reader. But after perusing several of his most important treatises, I found it almost impossible to form accurate notions on the subject. I have therefore endeavoured to make use of his own words as much as possible, that the want of consistency and the mysticism of his opinions may fall upon his own head. Should the reader find any difficulty in understanding the philosophy of Paracelsus, he will be in no worse a situation than every one has been who has attempted to delineate the principles of this prince of quacks and impostors. Van Helmont's merits were of a much higher kind, and I have endeavoured to do him justice, though his weaknesses are so visible that it requires much candour and patience to discriminate accurately between his excellencies and his foibles. The history of iatrochemistry forms a branch of our subject scarcely less extraordinary than alchymy itself. It might have been extended to a much greater length than I have done. The reason why I did not enter into longer details was that I thought the subject more intimately connected with the history of medicine than of chemistry. It undoubtedly contributed to the improvement of chemistry, not however by the opinions or the physiology of the iatrochemists, but by inducing their contemporaries and successors to apply themselves to the discovery of chemical medicines. The history of chemistry, after a theory of combustion had been introduced by Becher and Stahl, becomes much more important. It now shook off the trammels of alchymy and ventured to claim its station among the physical sciences. I have found it necessary to treat of its progress during the 18th century rather succinctly, but I hope so as to be easily intelligible. This made it necessary to omit the names of many meritorious individuals who supplied a share of the contributions which the science was continually receiving from all quarters. I have confined myself to those who made the most prominent figure as chemical discoverers. I had no other choice but to follow this plan, unless I had doubled the size of this little work, which would have rendered it less agreeable and less valuable to the general reader. With respect to the history of chemistry during that portion of the 19th century which is already past, it was beset with several difficulties. Many of the individuals of whose labours I had occasion to speak are still actively engaged in the prosecution of their useful works. Others have but just left the arena, and their friends and relations still remain to appreciate their merits. In treating of this branch of the science, by far the most important of all, I have followed the same plan as in the history of the preceding century. I have found it necessary to omit many names that would undoubtedly have found a place in a larger work, but which the limited extent to which I was obliged to confine myself necessarily compelled me to pass over. I have been anxious not to injure the character of any one, while I have rigidly adhered to truth so far as I was acquainted with it. Should I have been so unfortunate as to hurt the feelings of any individual by any remarks of mine in the following pages, it will give me great pain, and the only alleviation will be the consciousness of the total absence on my part of any malignant intention. To gratify the wishes of every individual may perhaps be impossible, but I can say with truth that my uniform object has been to do justice to the merits of all, so far as my own limited knowledge put it in my power to do. Introduction. Chemistry, unlike the other sciences, sprang originally from delusion and superstition, and was at its commencements exactly on a level with magic and astrology. Even after it began to be useful to man by furnishing him with better and more powerful medicines than the ancient physicians were acquainted with, it was long before it could shake off the trammels of alchymy which hung upon it like a nightmare, cramping and blunting all its energies, and exposing it to the scorn and contempt of the enlightened part of mankind. It was not till about the middle of the 18th century that it was able to free itself from these delusions, and to venture abroad in all the native dignity of a useful science. It was then that its utility and its importance began to attract the attention of the world, that it drew within its vortex some of the greatest and most active men in every country, and that it advanced towards perfection with an accelerated pace. The field which it now presents to our view is vast and imposing. Its paramount utility is universally acknowledged. It has become a necessary part of education. It has contributed as much to the progress of society, and has done as much to augment the comforts and conveniences of life, and to increase the power and the resources of mankind, as all the other sciences put together. It is natural to feel a desire to be acquainted with the origin and the progress of such a science, and to know something of the history and character of those numerous votaries to whom it is indebted for its progress and improvement. The object of this little work is to gratify these laudable wishes by taking a rapid view of the progress of chemistry from its first rude and disgraceful beginnings till it has reached its present state of importance and dignity. I shall divide the subject into 15 chapters. In the first I shall treat of alchymy, which may be considered as the inauspicious commencement of the science, and which in fact consists of little else than an account of dupes and impostors, everywhere so full of fiction and obscurity that it is a hopeless and almost impossible task to reach the truth. In the second chapter I shall endeavour to point out the few small chemical rills which were known to the ancients. These I shall follow in their progress in the succeeding chapters, till at last, augmented by an infinite number of streams flowing at once from 1,000 different quarters, they have swelled to the mighty river which now flows on majestically, wafting wealth and information to the civilized world. End of Preface and Introduction. Recording by Shenna Ser, Fresno, California.
Section 1 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Volume 1, Chapter 1 of Alchemy, Part 1. Chapter 1 of Alchemy. The word chemistry, chemia, first occurs in Suidas, a Greek writer, who is supposed to have lived in the 11th century, and to have written his lexicon during the reign of Alexius Comnenus. Under the word chemia in his dictionary we find the following passage. Chemistry, the preparation of silver and gold. The books on it were sought out by Diocletian and burnt, on account of the new attempts made by the Egyptians against him. He treated them with cruelty and harshness as he sought out the books written by the ancients on the chemistry of gold and silver, and burnt them. His object was to prevent the Egyptians from becoming rich by the knowledge of this art, lest, emboldened by abundance of wealth, they might be induced afterwards to resist the Romans. Under the word deros, a skin, in the lexicon, occurs the following passage. Deros, the golden fleece which Jason and the Argonauts, after a voyage through the Black Sea to Colchis, took together with Medea, daughter of Aeetes the king. But this was not what the poets represent, but a treatise written on skins, teaching how gold might be prepared by chemistry. Probably, therefore, it is called by those who lived at that time golden, on account of its great importance. From these two passages there can be no doubt that the word chemistry was known to the Greeks in the 11th century, and that it signified, at that time, the art of making gold and silver. It appears, further, that in Suidas' opinion, this art was known to the Egyptians in the time of Diocletian, that Diocletian was convinced of its reality, and that to put an end to it, he collected and burnt all the chemical writings to be found in Egypt. Nay, Suidas affirms that a book, describing the art of making gold, existed at the time of the Argonauts, and that the object of Jason and his followers was to get possession of that invaluable treatise, which the poets disguised under the term Golden Fleece. The first meaning, then, of chemistry was the art of making gold, and this art, in the opinion of Suidas, was understood at least as early as 1,225 years before the Christian era, for that is the period at which the Argonautic expedition is commonly fixed by chronologists. Though the Lexicon of Suidas be the first printed book in which the word chemistry occurs, yet it is said to be found in much earlier tracts, which still continue in manuscript. Thus Scaliger informs us that he perused a Greek manuscript of Zosimus, the Panoplite, written in the 5th century, and deposited in the King of France's library. Olaus Borrichius mentions this manuscript, but in such terms that it is difficult to know whether he had himself read it, though he seems to insinuate as much. The title of this manuscript is said to be A Faithful Description of the Sacred and Divine Art of Making Gold and Silver, by Zosimus the Panoplite. In this treatise, Zosimus distinguishes the art by the name chemia. From a passage in this manuscript, quoted by Scaliger, and given also by Olaus Borrichius, it appears that Zosimus carries the antiquity of the art of making gold and silver much higher than Suidas has ventured to do. The following is a literal translation of this curious passage. The sacred scriptures inform us that there exists a tribe of genii who make use of women. Hermes mentions this circumstance in his Physics, and almost every writing, whether sacred or apocryphal, states the same thing. The ancient and divine scriptures inform us that the angels, captivated by women, taught them all the operations of nature. Offense being taken at this, they remained out of heaven, because they had taught mankind all manner of evil, and things which could not be advantageous to their souls. The scriptures inform us that the giants sprang from these embraces. Chema is the first of their traditions respecting these arts. The book itself they called Chema, hence the art is called chemia. Zosimus is not the only Greek writer on chemistry. Olaus Borrichius has given us a list of 38 treatises, which he says exist in the libraries of Rome, Venice, and Paris, and Dr. Shaw has increased this list to 89. But among these we find the names of Hermes, Isis, Horus, Democritus, Cleopatra, Porphyry, Plato, etc., names which undoubtedly have been affixed to the writings of comparatively modern and obscure authors. The style of these authors, as Borrichius informs us, is barbarous. They are chiefly the production of ecclesiastics, who lived between the 5th and 12th centuries. In these tracts the art of which they treat is sometimes called chemistry, sometimes the chemical art, sometimes the holy art, and the philosopher's stone. It is evident from this that between the 5th century and the taking of Constantinople in the 15th century, the Greeks believed in the possibility of making gold and silver artificially, and that the art which professed to teach these processes was called by them chemistry. These opinions passed from the Greeks to the Arabians, when, under the caliphs of the family of Abbasides, they began to turn their attention to science, about the beginning of the 9th century, and when the enlightened zeal of the Fatimites in Africa and the Ommiades in Spain encouraged the cultivation of the sciences. From Spain they gradually made their way into the different Christian kingdoms of Europe. From the 11th to the 16th century, the art of making gold and silver was cultivated in Germany, Italy, France, and England, with considerable assiduity. The cultivators of it were called alchemists, a name obviously derived from the Greek word chemia, but somewhat altered by the Arabians. Many alchemistical tracts were written during that period. A considerable number of them were collected by Lazarus Zetzner and published at Strasbourg in 1602, under the title of Theatrum Chemicum, Precipus Selectorum Octorum Tractatus de Chemia et Lapidis Philosophicae Antiquitae Veritae Jure Prestantia, et Operationibus Continens in Gradium ver Chemiae et Medicinae Chemicae Studiosarum, qui urbium und optimorium remediorium messem facere paturant, congestum et inquator partes su volumina digestum. This book contains 105 different alchemistical tracts. In the year 1610, another collection of alchemistical tracts was published at Basel, in 3 volumes, under the title Artis Aurifae quam Chemium Vocunt Voluma Tria. It contains 47 different tracts. In the year 1702, Mangetus published at Geneva 2 very large folio volumes, under the name Bibliotheca Chemica Curiosa, su rerum ad alchymiam partinium thesaurus instructissimus, cu non tantum artis aurifae ac scriptorum and innubilorum historia traditur, lapidis veritas argumentus et experimentus innumerus imo et juris consultium judicius evincitur, termini obscurius explicantur, cautions contra impostors et difficulties in tinctura universala confidentia, auxerentes declanter, virum etiam tractatus omnes virum celebiorium, qui in magnu sudarant elixir, quique ab ipso hemate, et diciter trismegesto ad nostra uscra tempora decrescipia scripturant cum Principius suis commentarius consino ordine dispositi exhibentur. This bibliotheca contains 122 alchemistical treatises, many of them of considerable length. 2 additional volumes of the Theatrum Chemicum were afterwards published, but these I have never had an opportunity of seeing. From these collections, which exhibit a pretty complete view of the writings of the alchemists, a tolerably accurate notion may be formed of their opinions. But before attempting to lay open the theories and notions by which the alchemists were guided, it will be proper to state the opinions which were gradually adopted respecting the origin of alchemy, and the contrivances by which these opinions were supported. Zosimus the Panoplite, in a passage quoted above, informs us that the art of making gold and silver was not a human invention, but was communicated to mankind by angels or demons. These angels, he says, fell in love with women, and were induced by their charms to abandon heaven altogether, and to take up their abode upon earth. Among other pieces of information which these spiritual beings communicated for their paramours, was the sublime art of chemistry, or the fabrication of gold and silver. It is quite unnecessary to refute this extravagant opinion, obviously founded on a misunderstanding of a passage in the 6th chapter of Genesis. And it came to pass, when man began to multiply on the face of the earth, and daughters were born unto them, that the sons of God saw the daughters of men, that they were fair, and they took them wives of all which they chose. There were giants in the earth in those days, and also after that, when the sons of God came in unto the daughters of men, and they bare children to them. The same became mighty men, which were of old, men of renown. There is no mention whatever of angels or of any information on science communicated by them to mankind, nor is it necessary to say much about the opinion advanced by some, and rather countenanced by Olaus Borrichius, that the art of making gold was the invention of Tubal Cain, whom they represent as the same as Vulcan. All the information which we have respecting Tubal Cain is simply that he was an instructor of every artificer in brass and iron. No allusion whatever is made to gold, and that in these early ages of the world there was no occasion for making gold artificially. We have the same authority for believing For in the second chapter of Genesis, where the Garden of Eden is described, it is said, "And a river went out of Eden to water the garden, and from thence it was parted, and came into four heads. The name of the first is Pison. That is it which encompasseth the whole land of Havilah, where there is gold. And the gold of that land is good. There is bdellium and onyx stone." But the most generally received opinion is that alchemy originated in Egypt, and the honour of the invention has been unanimously conferred upon Hermes Trismegistus. He is by some supposed to be the same person with Chanaan, the son of Ham, whose son Mizraim first occupied and peopled Egypt. Plutarch informs us that Egypt was sometimes called Chemia. This name is supposed to be derived from Chanaan. Thence it was believed that Chanaan was the true inventor of alchemy, to which he affixed his own name. Whether the Hermes of the Greeks was the same person with Chanaan or his son Mizraim, it is impossible at this distance of time to decide. But to Hermes is assigned the invention of alchemy, or the art of making gold, by almost the unanimous consent of the adepts. Albertus Magnus informs us that Alexander the Great discovered the sepulchre of Hermes in one of his journeys, full of all treasures, not metallic, but golden, written on a table of zatadi, which others called emerald. This passage occurs in a tract of Albertus de Secretis Chemicus, which is considered as supposititious. Nothing is said of the source whence the information contained in this passage was drawn, but from the quotations produced by Kriegsmann, it would appear that the existence of this emerald table was alluded by Avicenna and other Arabian writers. According to them, a woman called Sarah took it from the hands of the dead body of Hermes, some ages after the flood, in a cave near Hebron. The inscription on it was in the Phoenician language. The following is a literal translation of this famous inscription from the Latin version of Kriegsmann. "I speak not fictitious things, but what is true and most certain. What is below is like that which is above, and what is above is similar to that which is below, to accomplish the miracles of one thing. And as all things were produced by the meditation of one being, so all things were produced from this one thing by adaptation. Its father is Sol, its mother Luna. The wind carried it in its belly, the earth is its nurse. It is the cause of all perfection throughout the whole world. Its power is perfect if it be changed into earth. Separate the earth from the fire, the subtile from the gross, acting prudently and with judgment. Ascend with the greatest sagacity from the earth to heaven, and then again descend to the earth, and unite together the powers of things superior and things inferior. Thus you will possess the glory of the whole world, and all obscurity will fly far away from you. This thing has more fortitude than fortitude itself, because it will overcome every subtile thing, and penetrate every solid thing. By it this world was formed. Hence proceed wonderful things, which in this wise were established. For this reason I am called Hermes Trismegistus, because I possess 3 parts of the philosophy of the whole world. What I had to say about the operation of Sol is completed." Such is a literal translation of the celebrated inscription of Hermes Trismegistus upon the emerald tablet. It is sufficiently obscure to put it in the power of commentators to affix almost any explanation to it that they choose. The 2 individuals who have devoted most time to illustrate this tablet are Kriegsmann and Gerard Darnius, whose commentaries may be seen in the first volume of Mangidus's Bibliotheca Chemica. They both agree that it refers to the universal medicine, which began to acquire celebrity about the time of Paracelsus, or a little earlier. This exposition, which appears as probable as any other, betrays the time when this celebrated inscription seems to have been really written. Had it been taken out of the hands of the dead body of Hermes by Sarah, obviously intended for the wife of Abraham, as is affirmed by Avicenna, It is not possible that Herodotus and all the writers of antiquity, both pagan and Christian, should have entirely overlooked it, or how could Avicenna have learned what was unknown to all those who lived nearest the time when the discovery was supposed to have been made? Had it been discovered in Egypt by Alexander the Great, would it have been unknown to Aristotle and to all the numerous tribe of writers whom the Alexandrian school produced? Not one of whom, however, make the least allusion to it. In short, it bears all the mark of a forgery of the 15th century, and even the tract ascribed to Albertus Magnus, in which the tablet of Hermes is mentioned, and the discovery related, is probably also a forgery, and doubtless a forgery of the same individual who fabricated the tablet itself, in order to throw a greater air of probability upon a story which he wished to palm upon the world as true. His object was in some measure accomplished, for the authenticity of the tablet was supported with much zeal by Kriegsmann, and afterward by Olaus Borrichius. There is another tract of Hermes Trismegistus entitled Tractatus Aureus de Lapidis Physici Secreto, on which no less elaborate commentaries have been written. It professes to teach the process of making the philosopher's stone, and from the allusions in it to the use of this stone as a universal medicine was probably a forgery of the same date as the emerald tablet. It would be in vain to attempt to extract anything intelligible out of this Tractatus Aureus. It may be worth while to give a single specimen, that the reader may be able to form some idea of the nature of the style. Take of moisture an ounce and a half, of meridional redness, that is the soul of the sun, a fourth part, that is half an ounce, of yellow cire, likewise half an ounce, and of aura pigmentum a half ounce, making in all 3 ounces. Know that the vine of wise men is extracted in 3s, and its wine at last is completed in 30. End of section 1. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. Section 2 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. Volume 1, Chapter 1 of Alchemy, Part 2. Had the opinion that gold and silver could be artificially formed originated with Hermes Trismegistus, or had it prevailed among the ancient Egyptians, it would certainly have been alluded to by Herodotus, who spent so many years in Egypt, and was instructed by the priests in all the science of the Egyptians. Had chemistry been the name of a science, real or fictitious, which existed as early as the expedition of the Argonauts, and had so many treatises on it, as Suidas alleges existed in Egypt before the reign of Diocletian, it could hardly have escaped the notice of Pliny, who was so curious and so indefatigable in his researches, and who has collected, in his Natural History, a kind of digest of all the knowledge of the ancients in every department of practical science. The fact that the term chemistry never occurs in any Greek or Roman writer prior to Suidas, who wrote so late as the 11th century, seems to overturn all idea of the existence of that pretended science among the ancients, notwithstanding the elaborate attempts of Olaus Borrichius to prove the contrary. I am disposed to believe that chemistry, or alchemy, understanding by the term the art of making gold and silver, originated with the Arabians, when they began to turn their attention to medicine, after the establishment of the caliphs, or if it had previously been cultivated by the Greeks, as the writing of Zosimus the Panoplite, if genuine, would lead us to suppose, that it was taken up by the Arabians and reduced by them into regular form and order. If the works of Geber could be genuine, they leave little doubt on this point. Geber is supposed to have been a physician, and to have written in the 7th century. He admits as a first principle that metals are compounds of mercury and sulfur. He talks of the philosopher's stone, professes to give the mode of preparing it, and teaches the way of converting the different metals, known in his time, into medicines, on whose efficacy he bestows the most ample panegyrics. Thus the principles which lie at the bottom of alchemy were implicitly adopted by him. Yet I can nowhere find in him any attempt to make gold artificially. His chemistry was entirely devoted to the improvement of medicine. The subsequent pretensions of the alchemists to convert the baser metals into gold are nowhere avowed by him. I am disposed from this time to suspect that the theory of gold-making was started after Geber's time, or at least that it was after the 7th century, before any alchemist ventured to affirm that he himself was in possession of the secret, and could fabricate gold artificially at pleasure. For there is a wide distance between the opinion that gold may be made artificially, and the affirmation that we are in possession of a method by which this transmutation of the baser metals into gold can be accomplished. The first may be adopted and defended with much plausibility and perfect honesty, but the second would require a degree of skill far exceeding that of most scientific votary of chemistry at present existing. The opinion of the alchemists was that all the metals are compounds, that the baser metals contain the same constituents as gold, contaminated indeed with various impurities, but capable, when their impurities are removed or remedied, of assuming all the properties and characters of gold. The substance possessing this wonderful power they distinguish by the name of lapis philosophorum, or philosopher's stone, and they usually describe it as a red powder, having a peculiar smell. Few of the alchemists who have left writings behind them boast of being possessed of the philosopher's stone. Paracelsus indeed affirms that he was acquainted with the method of making it, and gives several processes, which, however, are not intelligible. But many affirm that they had seen the philosopher's stone, that they had portions of it in their possession, and that they had seen several of the inferior metals, especially lead and quicksilver, converted by means of it into gold. Many stories of this kind are upon record, and so well authenticated that we need not be surprised at their having been generally credited. It will be sufficient if we state one or two of those which depend on the most unexceptionable evidence. The following relation is given by Mangetus on the authority of M. Gros, a clergyman of Geneva, of the most unexceptionable character, and at the same time a skilful physician and expert chemist. About the year 1650, an unknown Italian came to Geneva, and took lodgings at the sign of the Green Cross. After remaining there a day or two, he requested De Luc, the landlord, to procure him a man acquainted with Italian, to accompany him through the town, and point out those things which deserved to be examined. De Luc was acquainted with M. Gros, at that time about 20 years of age, and a student in Geneva, and, knowing his proficiency in the Italian language, requested him to accompany the stranger. To this proposition he willingly acceded, and attended the Italian everywhere for the space of a fortnight. The stranger now began to complain of want of money, which alarmed M. Gros not a little, for at that time he was very poor, and he became apprehensive, from the tenor of the stranger's conversation, that he intended to ask the loan of money from him. But instead of this, the Italian asked him if he was acquainted with any goldsmith, whose bellows and other utensils they might be permitted to use, and who would not refuse to supply them with the different articles requisite for a particular process which he wanted to perform. M. Gros named a M. Bureau, to whom the Italian immediately repaired. He readily furnished crucibles, pure tin, quicksilver, and the other things required by the Italian. The goldsmith left his workshop that the Italian might be under less restraint, leaving M. Gros with one of his own workmen as an attendant. The Italian put a quantity of tin into one crucible, and a quantity of quicksilver into another. The tin was melted in the fire, and the mercury heated. It was then poured into the melted tin, and at the same time a red powder, enclosed in wax, was projected into the amalgam. An agitation took place, and a great deal of smoke was exhaled from the crucible. But this speedily subsided, and the whole being poured out formed 6 heavy ingots, having the color of gold. The goldsmith was called in by the Italian, and requested to make a rigid examination of the smallest of these ingots. The goldsmith, not content with the touchstone and the application of aqua fortis, exposed the metal on the cupel with lead, and fused it with antimony, but it sustained no loss. He found it possessed of the ductility and specific gravity of gold, and full of admiration, he exclaimed that he had never worked before upon gold so perfectly pure. The Italian made him a present of the smallest ingot as a recompense, and then, accompanied by M. Gros, he repaired to the mint, where he received from M. Bacuet, the mint-master, a quantity of Spanish gold coin, equal in weight to the ingots which he had brought. To M. Gros he made a present of 20 pieces, on account of the attention that he had paid to him, and after paying his bill at the inn, he added 15 pieces more, to serve to entertain M. Gros and M. Bureau for some days, and in the meantime he ordered a supper, that he might on his return have the pleasure of supping with these 2 gentlemen. He went out, but never returned, leaving behind him the greatest regret and admiration. It is needless to add that M. Gros and M. Bureau continued to enjoy themselves at the inn till the 15 pieces, which the stranger had left, were exhausted. Mangetus gives also the following relation, which he states upon the authority of an English bishop, who communicated it to him in the year 1685, and at the same time gave him about half an ounce of the gold which the alchemist had made. A stranger, meanly dressed, went to Mr. Boyle, and after conversing for some time about chemical processes, requested him to furnish him with antimony and some other common metallic substances, which then fortunately happened to be in Mr. Boyle's laboratory. These were put into a crucible, which was then placed in a melting furnace. As soon as these metals were fused, the stranger showed a powder to the attendants, which he projected into the crucible, and instantly went out, directing the servants to allow the crucible to remain in the furnace till the fire went out of its own accord, and promising at the same time to return in a few hours. But as he never fulfilled this promise, Boyle ordered the cover to be taken off the crucible, and found that it contained a yellow-colored metal, possessing all the properties of pure gold, and only a little lighter than the weight of the materials originally put into the crucible. The following strange story is related by Helvetius, physician to the Prince of Orange, in his Vitalis Aureus. Helvetius was a disbeliever of the philosopher's stone and the universal medicine, and even turned Sir Kenelm Digby's sympathetic powder into ridicule. On the 27th of December, 1666, a stranger called upon him, and after conversing for some time about a universal medicine, showed a yellow powder, which he affirmed to be the philosopher's stone, and at the same time 5 large plates of gold, which had been made by means of it. Helvetius earnestly entreated that he would give him a little of this powder, or at least that he would make a trial of its power, but the stranger refused, promising, however, to return in 6 weeks. He returned accordingly, and after much entreaty he gave to Helvetius a piece of the stone, not larger than the size of a rape-seed. When Helvetius expressed his doubt whether so small a portion would be sufficient to convert 4 grains of lead into gold, the adept broke off 1/2 of it, and assured him that what remained was more than sufficient for the purpose. Helvetius, during the first conference, had concealed a little of the stone below his nail. This he threw into the melted lead, but it was almost all driven off in smoke, leaving only a vitreous earth. When he mentioned this circumstance, the stranger informed him that the powder must be enclosed in wax before it be thrown into the melted lead, lest it should be injured by the smoke of the lead. The stranger promised to return the next day, and show him the method of making the projection, but having failed to make his appearance, Helvetius, in the presence of his wife and son, put 6 drachms of lead into a crucible, and as soon as it was melted, he threw into it the fragment of the philosopher's stone in his possession, previously covered over with wax. The crucible was now covered with its lid, and left for a quarter of an hour in the fire, at the end of which time he found the whole lead converted into gold. The color was at first a deep green. Being poured into a conical vessel, it assumed a blood-red color, but when cold it acquired the true tint of gold. Being examined by a goldsmith, he considered it as pure gold. He requested Porelius, who had the charge of the Dutch mint, to try its value. 2 drachms of it being subjected to quartation and solution in aqua fortis, were found to have increased in weight by 2 scruples. This increase was doubtless owing to the silver, which still remained enveloped in the gold after the action of the aqua fortis. To endeavor to separate the silver more completely, the gold was again fused with 7 times its weight of antimony, and treated in the usual manner, but no alteration took place in the weight. It would be easy to relate many other similar narratives, but the 3 which I have given are the best authenticated that I am acquainted with. The reader will observe that they are all stated on the authority not of the persons who were the actors, but of others to whom they related them, and some of these, as the English bishop, perhaps not very familiar with chemical processes, and therefore liable to leave out or misstate some essential particulars. The evidence, therefore, though the best that can be got, is not sufficient to authenticate these wonderful stories. A little latent vanity might easily induce the narrators to suppress or alter some particulars, which, if known, would have stripped the statements of everything marvelous which they contain, and let us into the secret of the origin of the gold, which these alchemists boasted they had fabricated. Whoever will read the statements of Paracelsus respecting his knowledge of the philosopher's stone, which he applied not to the formation of gold but to medicine, or whoever will examine his formulas for making the stone, will easily satisfy himself that Paracelsus possessed no real knowledge of the subject. But to convey as precise ideas on the subject as possible, it may be worth while to state a few of the methods by which the alchemists persuaded themselves that they could convert the baser metals into gold. In the year 1694, an old gentleman called upon Mr. Wilson, at that time a chemist in London, and informed him that at last, after 40 years' search, he had met with an ample recompense for all his trouble and expenses. This he confirmed with some oaths and imprecations, but considering his great weakness and age, he looked upon himself as incapable to undergo the fatigues of the process. "I have here," says he, "a piece of sol, gold, that I made from silver about 4 years ago, and I cannot trust any man but you with so rare a secret. We will share equally the charges and profit, which will render us wealthy enough to command the world." The nature of the process being stated, Mr. Wilson thought it not unreasonable, especially as he aimed at no peculiar advantage for himself. He accordingly put it to the trial in the following manner. 12 ounces of Japan copper were beat into thin plates, and laid stratum super stratum with 3 ounces of flowers of sulphur in a crucible. It was exposed in a melting furnace to a gentle heat, till the sulphureous flames expired. When cold, the ace ustum, sulphuret of copper, was pounded and stratified again, and this process was repeated 5 times. Mr. Wilson does not inform us whether the powder was mixed with the flowers of sulphur every time it was heated, but this must have been the case. Otherwise the sulphuret would have been again converted into metallic copper, which would have melted into a mass. By this first process, then, bisulphuret of copper was formed, composed of equal weights of sulphur and copper. 2. 6 pounds of iron wire were put into a large glass body, and 12 pounds of muriatic acid poured upon it. 6 days elapsed, during which it stood in a gentle heat, before the acid was saturated with the iron. The solution was then decanted off and filtered, and 6 pounds of new muriatic acid poured on the undissolved iron. This acid, after standing a sufficient time, was decanted off and filtered. Both liquids were put into a large retort, and distilled by a sand heat. Towards the end, when the drops from the retort became yellow, the receiver was changed, and the fire increased to the highest degree, in which the retort was kept between 4 and 6 hours. When all was cold, the receiver was taken off, and a quantity of flowers was found in the neck of the retort, variously colored, like the rainbow. The yellow liquor in the receiver weighed 10 ounces and a half. The flowers, chloride of iron, 2 ounces and 3 drachms. The liquid and flowers were put into a clean bottle. 3. Half a pound of sal inixum, sulfate of potash, and a pound and a half of nitric acid were put into a retort. When the salt had dissolved in the acid, 10 ounces of mercury, previously distilled through quicklime and salt of tartar, were added. The whole being distilled to dryness, a fine yellow mass, pernitrate of mercury, remained in the bottom of the retort. The liquor was returned with half a pound of fresh nitric acid, and the distillation repeated. The distillation was repeated a third time, urging this last cohobation with the highest degree of fire. When all was cold, a various colored mass was found in the bottom of the retort. This mass was doubtless a mixture of sulfate of potash and pernitrate of mercury, with some oxide of mercury. 4. 4 ounces of fine silver were dissolved in a pound of aqua fortis. To the solution was added the bisulfate of copper, 4 ounces, of the mixture of sulfate of potash, pernitrate of mercury, and oxide of mercury, 1 ounce and a half, and of the solution of perchloride of iron, 2 ounces and a half. When these had stood in a retort 24 hours, the liquor was decanted off, and 4 ounces of nitric acid were poured upon the little matter that was not dissolved. Next morning a total dissolution was obtained. The whole of this dissolution was put into a retort and distilled almost to dryness. The liquid was poured back, and the distillation repeated 3 times. The last time the retort being urged by a very strong fire, till no fumes appeared, and not a drop fell. The matter left in the bottom of the retort was now put into a crucible. All the corrosive fumes were gently evaporated, and the residue melted down with a fluxing powder. This process was expected to yield 5 ounces of pure gold, but on examination the silver was the same, except the loss of half a pennyweight, as when dissolved in the aqua fortis. There were indeed some grains among the scoria, which appeared like gold, and would not dissolve in aqua fortis. No doubt they consisted of peroxide of iron, or perhaps persulphuret of iron. Mr. Wilson's alchemistical friend, not satisfied with his first failure, insisted upon a repetition of the process, with some alteration in the method and addition of a certain quantity of gold. The whole was accordingly gone through again, but it is unnecessary to say that no gold was obtained, or at least the 2 drachms of gold employed had increased in weight by only 2 scruples and 13 grains. This addition was doubtless owing to a little silver, from which it had not been freed. End of section 2. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 3 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, InterfaceAudio.com, Mount Vernon, Ohio. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 1 of Alchemy, Part 3. I shall now give a process for making the philosopher's stone, which was considered by Mangetus as of great value, and on that account was given by him in the preface to his Bibliotheca Chemica. 1. Prepare a quantity of a spirit of wine, so free from water that it is wholly combustible, and so volatile that when a drop of it is let fall it evaporates before it reaches the ground. This constitutes the first menstruum. 2. Take pure mercury, revived in the usual manner from cinnabar. Put it into a glass vessel with common salt and distilled vinegar. Agitate violently, and when the vinegar acquires a black color, Pour it off and add new vinegar. Agitate again, and continue these repeated agitations and additions till the vinegar ceases to acquire a black color from the mercury. The mercury is now quite pure and very brilliant. 3. Take of this mercury 4 parts, of sublimed mercury, mercuri meteoriceti, prepared with your own hands, 8 parts. Triturate them together in a wooden mortar with a wooden pestle, till all the grains of running mercury disappear. This process is tedious and rather difficult. 4. The mixture thus prepared is to be put into an aludel, or sand bath, and exposed to a subliming heat, which is to be gradually raised till the whole sublimes. Collect the sublimed matter, put it again into the aludel, and sublime a second time. This process must be repeated 5 times. Thus a very sweet and crystallized sublimate is obtained. It constitutes the salt of wise men, sal sapientum, and possesses wonderful properties. 5. Grind it in a wooden mortar, and reduce it to powder. Put it into a glass retort, and pour upon it the spirit of wine, No. 1, till it stands about 3 finger breadths above the powder. Seal the retort hermetically, and expose it to a very gentle heat for 74 hours, shaking it several times a day. Then distill with a gentle heat, and the spirit of wine will pass over, together with spirit of mercury. Keep this liquid in a well-stopped bottle, lest it should evaporate. More spirit of wine is to be poured upon the residual salt, and after digestion it must be distilled off as before, and this process must be repeated till the whole salt is dissolved and distilled over with the spirit of wine. You have now performed a great work. The mercury is now rendered in some measure volatile, and it will gradually become fit to receive the tincture of gold and silver. Now return thanks to God, who hitherto crowned your wonderful work with success. Nor is this great work involved in Cimmerian darkness, but clearer than the sun, though preceding writers have imposed upon us with parables, hieroglyphics, fables, and enigmas. 6. Take this mercurial spirit, which contains our magical steel in its belly, put it into a glass retort, to which a receiver must be well and carefully luted. Draw off the spirit by a very gentle heat. There will remain in the bottom of the retort the quintessence or soul of mercury. This is to be sublimed by applying a stronger heat to the retort, that it may become volatile, as all the philosophers express themselves. Si fixum solvis faciasque volere salutum, et volucrum figris faciat te vivere tutum. This is our Luna, our fountain, in which the king and queen may bathe. Prepare this precious quintessence of mercury, which is very volatile, in a well-shut vessel for further use. 8. Let us now proceed to the operation of common gold, which we shall communicate clearly and distinctly, without digression or obscurity, that from vulgar gold we may obtain our philosophical gold, just as from common mercury we obtained, by the preceding processes, philosophical mercury. In the name of God, then, take common gold, purified in the usual way by antimony. Convert it into small grains, which must be washed with salt and vinegar, till it be quite pure. Take 1 part of this gold, and pour on it 3 parts of the quintessence of mercury, as philosophers reckon from 7 to 10. So we also reckon our number as philosophical, and we begin with 3 and 1. Let them be married together, like husband and wife, to produce children of their own kind, and you will see the common gold sink and plainly dissolve. Now the marriage is consummated. Now 2 things are converted into 1. Thus the philosophical sulphur is at hand, as the philosophers say. The sulphur being dissolved, the stone is at hand. Take, then, in the name of God, our philosophical vessel, in which the king and queen embrace each other as in a bedchamber, and leave it till the water is converted into earth. Then peace is concluded between the water and fire. Then the elements have no longer anything contrary to each other, because when the elements are converted into earth, they no longer oppose each other. For in earth all elements are at rest. For the philosophers say, "When you shall have seen the water coagulate itself, think that your knowledge is true, and that your operations are truly philosophical." The gold is now no longer common, but ours is philosophical, on account of our processes. At first exceedingly fixed, then exceedingly volatile, and finally exceedingly fixed. Then the whole science depends upon the change of the elements. The gold at first was a metal, now it is a sulphur, capable of converting all metals into its own sulphur. Now our tincture is wholly converted into sulphur, which possesses the energy of curing all diseases. This is our universal medicine against all the most deplorable diseases of the human body. Therefore return infinite thanks to Almighty God for all the good things which He has bestowed upon us. 9. In this great work of ours, two modes of fermenting and projecting are wanting, without which the uninitiated will not easily follow our process. The mode of fermenting is as follows. Take of our sulphur above described 1 part, and project upon it 3 parts of very pure gold fused in a furnace. In a moment you will see the gold, by the force of the sulphur, converted into a red sulphur of an inferior quality to the first sulphur. Take 1 part of this, and project upon it 3 parts of fused gold. The whole will be again converted into a sulphur or a friable mass. Mixing 1 part of this with 3 parts of gold, you will have a malleable and extensible metal. If you find it so, well; if not, add other sulphur, and it will again pass into sulphur. Now the sulphur will be sufficiently fermented, or our medicine will be brought into a metallic nature. 10. The mode of projecting is this. Take of the fermented sulphur 1 part, and project upon it 10 parts of mercury, heated in a crucible, and you will have a perfect metal. If its color is not sufficiently deep, fuse it again, and add more fermented sulphur, and thus it will acquire color. If it becomes frangible, add a sufficient quantity of mercury, and it will be perfect. Thus, friend, you have a description of the universal medicine, not only for curing diseases and prolonging life, but also for transmuting all metals into gold. Give therefore thanks to Almighty God, who, taking pity on human calamities, has at last revealed this inestimable treasure, and made it known for the common benefit of all. Such is the formula, slightly abridged, of Carolus Musitanus, by which the philosopher's stone, according to him, may be formed. Compared with the formulas of most of the alchemists, it is sufficiently plain. What the sublimed mercury is does not appear. From the process described, we should be apt to consider it as corrosive sublimate. On that supposition, the sal sapientum formed in No. 5 would be calomel. The only objection to this supposition is the process described in No. 5, for calomel is not soluble in alcohol. The philosopher's stone, prepared by this elaborate process, could hardly have been anything else than an amalgam of gold. It could not have contained chloride of gold, because such a preparation, instead of acting medicinally, would have proved a most virulent poison. There is no doubt that an amalgam of gold, if projected into melted lead or tin, and afterwards cupellated, would leave a portion of gold, all the gold, of course, that existed previously in the amalgam. It might therefore have been employed by impostors to persuade the ignorant that it was really the philosopher's stone, but the alchemist who prepared the amalgam could not be ignorant that it contained gold. There is another process given in the same preface of a very different nature, but too long to be transcribed here, and the nature of the process is not sufficiently intelligible to render an account of it of much consequence. The preceding observations will give the reader some notion of the nature of the pursuits which occupied the alchemists. Their sole object was the preparation of a substance to which they gave the name of the philosopher's stone, which possessed the double property of converting the baser metals into gold, and of curing all diseases, and of preserving human life to an indefinite extent. The experiments of Wilson and the formula of Musitanus, which have just been inserted, will give the reader some notion of the way in which they attempted to manufacture this most precious substance, Being quite ignorant of the properties of bodies and of their action upon each other, their processes were guided by no scientific analogies, and one part of the labor not unfrequently counteracted another. It would be a waste of time, therefore, to attempt to analyze their numerous processes, even though such an attempt could be attended with success. But in most cases, from the unintelligible terms in which their books are written, it is impossible to divine the nature of the processes by which they endeavored to manufacture the philosopher's stone, or the nature of the substances which they obtained. In consequence of the universality of the opinion that gold could be made by art, there was a set of impostors who went about pretending that they were in possession of the philosopher's stone, and offering to communicate the secret of making it for a suitable reward. Nothing is more astonishing than that persons could be found credulous enough to be the dupes of such impostors. The very circumstance of their claiming a reward was a sufficient proof that they were ignorant of the secret which they pretended to reveal. For what motive could a man have for asking a reward who was in possession of a method of creating gold at pleasure? To such a person money could be no object, as he could procure it in any quantity. Yet, strange as it may appear, they met with abundance of dupes credulous enough to believe their asseverations, and to supply them with money to enable them to perform the wished-for processes. The object of these impostors was either to pocket the money thus furnished, or they made use of it to purchase various substances from which they extracted oils, acids, or similar products, which they were enabled to sell at a profit. To keep the dupes, who thus supplied them with the means of carrying on these processes in good spirits, it was necessary to show them occasionally small quantities of the baser metals converted into gold. Thus they performed in various ways. M. Geoffroy, Sr., who had an opportunity of witnessing many of their performances, has given us an account of a number of their tricks. It may be worth while to state a few by way of specimen. Sometimes they made use of crucibles with a false bottom. At the real bottom they put a quantity of oxide of gold or silver. This was covered with a portion of powdered crucible, glued together by a little gummed water or a little wax. The materials being put into this crucible and heat applied, the false bottom disappears, the oxide of gold or silver is reduced, and at the end of the process is found at the bottom of the crucible, and considered as the product of the operation. Sometimes they make a hole in a piece of charcoal and fill it with oxide of gold or silver, and stop up the mouth with a little wax, or they soak the charcoal in solutions of these metals, or they stir the mixtures in the crucible with hollow rods containing oxide of gold or silver within, and the bottom shut with wax. By these means the gold or silver wanted is introduced during the process, and considered as a product of the operation. Sometimes they have a solution of silver in nitric acid, or of gold in aqua regia, or an amalgam of gold or silver, which, being adroitly introduced, furnishes the requisite quantity of metal. A common exhibition was to dip nails into a liquid, and take them out half converted into gold. The nails consisted of 1/2 gold, neatly soldered to the iron, and covered with something to conceal the color, which the liquid removed. Sometimes they had metals 1/2 gold and the other half silver soldered together, and the gold side whitened with mercury. The gold half was dipped into a transmuting liquid, and then the metal heated, the mercury was dissipated, and the gold half of the metal appeared. End of section 3, recorded by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. Section number 4 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 1 of Alchymy, Part 4. As the alchemists were assiduous workmen, as they mixed all the metals, salts, etc., with which they were acquainted, in various ways with each other, and subjected such mixtures to the action of heat in close vessels, their labors were occasionally repaid by the discovery of new substances, possessed of much greater activity than any with which they were previously acquainted. In this way they were led to the discovery of sulphuric, nitric, and muriatic acids. These, when known, were made to act upon the metals. Solutions of the metals were obtained, and this gradually led to the knowledge of various metalline salts and preparations, which were introduced with considerable advantage into medicine. Thus the alchemists, by their absurd pursuits, gradually formed a collection of facts, which led ultimately to the establishment of scientific chemistry. On this account it will be proper to notice in this place such of them as appeared in Europe during the darker ages, and acquired the highest reputation, either on account of their skill as physicians, or their celebrity as chemists. 1. The first alchemist who deserves notice is Albertus Magnus, or Albert Groot, a German, who was born, it is supposed, in the year 1193, at Bullstedt, and died in the year 1282. When very young, he is said to have been so remarkable for his dullness that he became the jest of his acquaintances. He studied the sciences at Padua, and afterwards taught at Cologne, and finally in Paris. He traveled through all Germany as provincial of the order of Dominican monks, visited Rome, and was made Bishop of Ratisbon. But his passion for science induced him to give up his bishopric, and return to a cloister at Cologne, where he continued till his death. Albertus was acquainted with all the sciences cultivated in his time. He was at once a theologian, a physician, and a man of the world. He was an astronomer and an alchemist, and even dipped into magic and necromancy. His works are very voluminous. They were collected by Alchymy, and published at Leyden in 21 folio volumes in 1651. His principal alchemistical tracts are the following: 1. De Rebus Metallicis et Mineralibus. 2. De Alchymia. 3. Secretorum Tractatus. 4. Breve Compendium de Ortu Metallorum. 5. Concordantia Philosophorum de Lapide. 6. Compositum de Compositus. 7. Liber Octo Capitum de Philosophorum Lapide. Most of these tracts have been inserted in the Theatrum Chemicum. They are in general plain and intelligible. In his treatise De Alchymia, for example, he gives distinct account of all the chemical substances known in his time, and of the manner of obtaining them. He mentions also the apparatus then employed by chemists and the various processes by which they had occasion to perform. I may notice the most remarkable facts and opinions which I have observed in turning over these treatises. He was of the opinion that all metals are composed of sulphur and mercury, and endeavored to account for the diversity of metals partly by the difference in the purity, and partly by the difference in the proportions of the sulphur and mercury of which they are composed. He thought that water existed also as a constituent of all metals. He was acquainted with the water bath, employed alembics for distillation, and aludels for sublimation, and he was in the habit of employing various lutes, the composition of which he describes. He mentions alum and caustic alkali, and seems to have known the alkaline basis of cream of tartar. He knew the method of purifying the precious metals by means of lead and of gold, by cementation, and likewise the method of trying the purity of gold, and of distinguishing pure from impure gold. He mentions red lead, metallic arsenic, and liver of sulphur. He was acquainted with green vitriol and iron pyrites. He knew that arsenic renders copper white, and that sulphur attacks all the metals except gold. It is said by some that he was acquainted with gunpowder, but nothing indicating such knowledge occurs in any of his writings that I have had an opportunity of perusing. 2. Albertus is said to have had for a pupil, while he taught in Paris, the celebrated Thomas Aquinas, a Dominican who studied at Bologna, Rome, and Naples, and distinguished himself still more in divinity and scholastic philosophy than in alchemy. He wrote 1. Thesaurus Alchemy Secretitium. 2. Secreta Alchemia Magnalia. 3. De Esse et Essentia Mineralium, and perhaps some other works which I have not seen. These works, so far as I have perused them, are exceedingly obscure, and in various places unintelligible. Some of the terms still employed by modern chemists occur, for the first time, in the writings of Thomas Aquinas. Thus the term amalgam, still employed to denote a compound of mercury with another metal, occurs in them, and I have not observed it in any earlier author. 3. Soon after Albertus Magnus flourished Roger Bacon, by far the most illustrious, the best informed, and the most philosophical of all the alchemists. He was born in 1214, in the county of Somerset. After studying in Oxford, and afterward in Paris, he became a Cordelier friar, and devoting himself to philosophical investigations, his discoveries, notwithstanding the pains which he took to conceal them, made such a noise that he was accused of magic, and his brethren, in consequence, threw him into prison. He died, it is said, in the year 1284, though Sprengel fixes the year of his death to be 1285. His writings display a degree of knowledge and extent of thought scarcely credible, if we consider the time when he wrote, the darkest period of the Dark Ages. In his small treatise De Mirabili Potestae Artis et Naturae, he begins by pointing out the absurdity of believing in magic, necromancy, charms, or any of those similar opinions which were at that time universally prevalent. He points out the various ways in which mankind are deceived by jugglers, ventriloquists, and etc., mentions the advantages which physicians may derive from acting on the imaginations of their patients by means of charms, amulets, and infallible remedies. He affirms that many of those things which are considered as supernatural are merely so because mankind in general are unacquainted with natural philosophy. To illustrate this, he mentions a great number of natural phenomena, which had been reckoned miraculous, and concludes with several secrets of his own, which he affirms to be still more extraordinary imitations of some of the most singular processes of nature. These he delivers in the enigmatical style of the times, induced, as he tells us, partly by the conduct of other philosophers, partly by the propriety of the thing, and partly by the danger of speaking too plainly. From an attentive perusal of his works, many of which have been printed, it will be seen that Bacon was a great linguist, being familiar with Latin, Greek, Hebrew, and Arabic, and that he had perused the most important books at the time existing in all these languages. He was also a grammarian. He was well versed in the theory and practice of perspective. He understood the use of convex and concave glasses, and the art of making them. The camera obscura, burning glasses, and the powers of the telescope were known to him. He was well versed in geography and astronomy. He knew the great error in the Julian calendar, assigned the cause, and proposed the remedy. He understood chronology well. He was a skillful physician, and an able mathematician, logician, metaphysician, and theologist. But it is as a chemist that he claims our attention here. The following is a list of his chemical writings, as given by Gmelin, the whole of which I have never had an opportunity of seeing. 1. Speculum Alchymy. 2. Epistola de Secretis Operibus Artis de Naturae et de Notiliate Magiae. 3. De Mirabili Potestate Artis et Naturae. 4. Medulla Alchymi. 5. De Arte Chemiae. 6. Breviarium Alchemiae. 7. Documentae Alchemiae. 8. De Alchemisterium Artibus. 9. De Secretis. 10. De Rebus Metallicis. 11. De Sculpturis Lapidum. 12. De Philosophorum Lapide. 13. Opus Majus or Alchymia Major. 14. Breviarium de Dono Dei. 15. Verbum abbreviatum de Leone Veridi. 16. Secretum Secretorum. 17. Tractatus Trium Verborum. 18. Speculum Secretorum. A number of these were collected together and published at Frankfurt in 1603 under the title of Rogeri Baconis Angli de Arte Chemiae Scripta, in a small 12mo volume. The Opus Majus was published in London in 1733 by Dr. Jebb in a folio volume. Several of his tracts still continue in manuscript in the Harleian and Bodleian libraries at Oxford. He considered the metals as compound of mercury and sulphur. Gmelin affirms that he was aware of the peculiar nature of manganese, and that he was acquainted with bismuth. But after perusing the whole of the Speculum Alchemiae, the third chapter of which he quotes as containing the facts on which he founds his opinion, I cannot find any certain allusion either to manganese or bismuth. The term magnesia indeed occurs, but nothing is said respecting its nature, and long after the time of Paracelsus, bismuth, bismatum, was considered as an impure kind of lead. That he was acquainted with the composition and properties of gunpowder admits of no doubt. In the 6th chapter of his epistle, De Secretis Operibus Artis de Naturae et de Nullitate Magiae, the following passage occurs: For sounds like thunder, and coruscations like lightning, may be made in the air, and they may be rendered even more horrible than those of nature herself. A small quantity of matter, properly manufactured, not larger than the human thumb, may be made to produce a horrible noise and coruscation. And this may be done many ways, by which a city or an army may be destroyed, as was the case when Gideon and his men broke their pitchers and exhibited their lamps. Fire issuing out of them with inestimable noise, destroyed an infinite number of the army of the Midianites. And in the 11th chapter of the same epistle occurs the following passage: Mix together saltpeter, luro vopo ver con utriet, and sulphur, and you will make thunder and lightning, if you know the method of mixing them. Here all the ingredients of gunpowder are mentioned except charcoal, which is doubtless concealed under the barbarous terms luru vopo vir con utriet. But though Bacon was acquainted with gunpowder, we have no evidence that he was the inventor. How far the celebrated Greek fire, concerning which so much has been written, was connected with gunpowder, it is impossible to say, but there is good evidence to prove that gunpowder was known and used in China before the commencement of the Christian era. And Lord Bacon is of opinion that the thunder and lightning and magic stated by the Macedonians to have been exhibited in Oxydrix, when it was besieged by Alexander the Great, was nothing else than gunpowder. Now, as there is pretty good evidence that the use of gunpowder had been introduced into Spain by the Moors, at least as early as the year 1343, and as Roger Bacon was acquainted with Arabic, it is by no means unlikely that he might have become acquainted with the mode of making the composition, and with its most remarkable properties, by perusing some Arabian writer, with whom we are at present unacquainted. Barbour, in his Life of Bruce, informs us that guns were first employed by the English at the Battle of Werewater, which was fought in 1327, about 40 years after the death of Bacon. Two novelties that day they saw, that forth in Scotland had been the nane, timbers for helms was the ain, that they thought then of great beauty, and also wonder for to see. The other crackies were of war, that they before heard never ere. In another part of the same book we have the phrase guineas for crackies, showing that the term crackies was used to denote a gun or musket of some form or other. It is curious that the English would seem to have been the first European nation that employed gunpowder in war. They used it in the Battle of Crécy, fought in 1346, when it was unknown to the French, and it is supposed to have contributed materially to the brilliant victory which was obtained. 4. Raymond Lully is said to have been a scholar and a friend of Roger Bacon. He was a most voluminous writer, and acquired as high a reputation as any of the alchemists. According to Mutius, he was born in Majorca in the year 1235. His father was seneschal to King James, the First of Aragon. In his younger days he went into the army, but afterwards held a situation in the court of his sovereign. Devoting himself to science, he soon acquired a competent knowledge of Latin and Arabic. After studying in Paris, he got the degree of doctor conferred upon him. He entered into the order of the Minorites, and induced King James to establish a cloister of that order in Minorca. He afterwards travelled through Italy, Germany, England, Portugal, Cyprus, Armenia, and Palestine. He is said by Mutius to have died in the year 1315, and to have been buried in Majorca. The following epitaph is given by Olaus Borrichius, as engraven on his tomb. Raymundus Loli, Iugis pia dogmata nulli, sunt odiosa vira, jacet hic immormor miro, hic et sisi compi corspit sine sensibus esse. MCC in these lines denote 1300, and P, which is the 15th letter of the alphabet, denotes 15, so that if this epithet be genuine, it follows that his death took place in the year 1315. It seems scarcely necessary to notice the story that Raymund Lully made a present to Edward, King of England, of 6 millions of pieces of gold, to enable him to make war on the Saracens, which sum that monarch employed, contrary to the intentions of the donor, in his French wars. This story cannot apply to Edward III, because in 1315, at the time of Raymond's death, that monarch was only 3 years of age. It can scarcely apply to Edward II, who ascended the throne in 1305, but who had no opportunity of making war, either on the Saracens or French, being totally occupied in opposing the intrigues of his queen and rebellious subjects, to whom he ultimately fell a sacrifice. Edward I made war, both upon the Saracens and the French, and lived during the time of Raymond, but his wars with the Saracens were finished before he ascended the throne, and during the whole of his reign he was too much occupied with his projected conquest of Scotland to pay much serious attention to any French war whatever. The story, therefore, cannot apply to any of the 3 Edwards, and cannot be true. Raymund Lully is said to have been stoned to death in Africa for preaching Christianity in the year 1315. Others will have it that he was alive in England in the year 1332, at which time his age would have been 97. End of section 4. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section number 5 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 1 of Alchymy, Part 5. The following table exhibits a list of his numerous writings, most of which are to be found in the Theatrum Chemicum, the Artis Auriferae, or the Bibliotheca Chemica. 1. Praxis Universalis Magni Operis. 2. Clavicula. 3. Theoria et Practica. 4. Compendium Animae Transmutationis Artis Metallorum. 5. Ultimum Testamentum. Of this work, which professes to give the whole doctrine of alchemy, there is an English translation. 6. Elucidatio Testamentae. 7. Protestus Divatorium cum Expositione Testamentae Hermetis. 8. Compendium Artis Magici, quoad Compositium Lapidis. 9. De Lapide et Oleo Philosophorum. 10. Modus Accipiendae Aurum Potabile. 11. Compendium Alchemiae de Naturalias Philosophae. 12. Lapidarium. 13. Lux Mercuriorium. 14. Experimentae. 15. Ars Compendiosa vel Vadimicium. 16. De Accurtoriton Lapidis. Several other tracts besides these are named by Gmelin, but I have never seen any of them. I have attempted several times to read over the works of Raymond Lully, particularly his Last Will and Testament, which is considered the most important of them all. But they are all so obscure and filled with such unintelligible jargon that I have found it impossible to understand them. In this respect they form a wonderful contrast with the works of Albertus Magnus and Roger Bacon, which are comparatively plain and intelligible. For an account, therefore, of the chemical substances with which he was acquainted, I am obliged to depend on Gmelin, though I put no great confidence in his accuracy. Like his predecessors, he was of the opinion that all the metals are compounds of sulphur and mercury, but he seems first to have introduced those hieroglyphical figures or symbols which appear in such profusion in the English translation of his Last Will and Testament, and which he doubtless intended to illustrate his positions. Though what other purpose they could serve than to induce the reader to consider his statements as allegorical, it is not easy to conjecture. Perhaps they may have been designed to impose upon his contemporaries by an air of something very profound and inexplicable. For that he possessed a good deal of charlatanry is pretty evident from the slightest glance at his performances. He was acquainted with cream of tartar, which he distilled. The residue he burnt, and observed that the alkali extracted deliquesced when exposed to the air. He was acquainted with nitric acid, which he obtained by distilling a mixture of saltpetre and green vitriol. He mentioned its powers of dissolving not merely mercury, but likewise other metals. He could form aqua regia by adding sal ammoniac or common salt to nitric acid, and he was aware of the property which it had of dissolving gold. Spirit of wine was well known to him, and distinguished by him by the names of aquae vitae ardens and argentum vivum vegetabile. He knew the method of rendering it stronger by an admixture of dry carbonate of potash, and of preparing vegetable tinctures by means of it. He mentions alum from Rocca, marcasite, white and red mercurial precipitate. He knew the volatile alkali and its coagulations by means of alcohol. He was acquainted with cupellated silver, and first obtained rosemary oil by distilling the plant with water. He employed a mixture of flour and white of egg spread upon a linen cloth to cement cracked glass vessels, and used other lutes for similar purposes. 5. Arnoldus de Villanova is said to have been born at Villeneuve, a village of Provence, about the year 1240. Olaus Borrichius assures us that in his time his posterity lived in the neighborhood of Avignon, that he was acquainted with them, and that they were by no means destitute of chemical knowledge. He is said to have been educated at Barcelona, under John Casamila, a celebrated professor of medicine. This place he was obliged to leave in consequence of foretelling the death of Peter of Aragon. He went to Paris, and likewise travelled through Italy. He afterwards taught publicly in the University of Montpellier. His reputation as a physician became so great that his attendance was solicited in dangerous cases by several kings, and even the Pope himself. He was skilled in all the sciences of his time, and was besides a proficient in Greek, Hebrew, and Arabic. When at Paris he studied astrology, and calculating the age of the world, he found that it was to terminate in the year 1335. The theologians of Paris claimed against this and several other of his opinions, and condemned our astrologer as a heretic. This obliged him to leave France, but the Pope protected him. He died in the year 1313, on his way to visit Pope Clement V, who lay sick at Avignon. The following table exists a pretty full list of his works. 1. Antidotorium. 2. Divini. 3. De Aquis Laxativus. 4. Rosarius Philosophorum. 5. Lumen Novum. 6. De Sigillis. 7. Flos Florum. 8. Apostolae super Alchymia ad Regem Neapolitanum. 9. Liber Perfectionis Magisteri. 10. Secusa Carmina. 11. Questions de Arte Transmutationis Metallorum. 12. Testamentum. 13. Lumen Luminum. 14. Practica. 15. Speculum Alchymiae. 16. Carmen. 17. Questions ad Bonifacium. 18. Semita Semitiae. 19. De Lapida Philosophorum. 20. De Sanguine Humano. 21. De Spiritus Vini, Vino Artemoni, et Gemorem Viribus. Perhaps the most curious of all these works is the Rosarium, which is intended as a complete compend of all the alchemy of his time. The first part of it on the theory of the art is plain enough, but the second part on the practice, which is subdivided into 32 chapters, and which professes to teach the art of making the philosopher's stone, is in many places quite unintelligible to me. He considered, like many of his predecessors, mercury as a constituent of metals, and he professed a knowledge of the philosopher's stone, which he could increase at pleasure. Gold and gold water was, in his opinion, one of the most precious of medicines. He employed mercury in medicine. He seems to designate bismuth under the name marcasite. He was in the habit of preparing oil of turpentine, oil of rosemary, and spirit of rosemary, which afterwards became famous under the name Hungary water. These distillations were made in a glazed earthen vessel, with a glass top and helm. His works were published at Venice in a single folio volume in the year 1505. There were 7 subsequent editions, the last of which appeared at Strasbourg in 1613. 6. John Isaac Hollandus and his countryman of the same name were either 2 brothers or a father and son, it is uncertain which. For very few circumstances respecting these 2 laborious and meritorious men have been handed down to posterity. They were born in the village of Stolk in Holland, it is supposed in the 13th century. They were certainly after Arnoldus de Villanova, because they refer to him in their writings. They wrote many treatises on chemistry, remarkable considering the time when they wrote, for clearness and precision, describing their processes with accuracy, and even giving figures of the instruments which they employed. This makes their books intelligible, and they deserve attention because they show that various processes, generally supposed of a more modern date, were known to them. Their treatises are written partly in Latin and partly in German. The following list contains the names of most of them. 1. Opera Vegetabilia ad ejus alia opera intelligenda necessaria. 2. Opera Mineralia su de lapide philosophico libro duo. 3. Tractat vom Stein der Weisen. 4. Fragmenta quaedam chemica. 5. De triplis ordine elixiris e lapidis theoria. 6. Tractatus de salivus et oleis metallorum. 7. Fragmentum de opera philosophorum. 8. Rearies chemiae operationes. 9. Opus Saturni. 10. De spirito uraniae. 11. Hand der Philosopher. Olaus Borrichius complains that their opera mineralia abound with processes, but that they are ambiguous, and such that nothing certain can be deduced from them even after much labor. Hence they draw on the unwary tyro from labor to labor. I am disposed myself to draw a different conclusion from what I have read of that elaborate work. It is true that the processes which profess to make the philosopher's stone are fallacious, and do not lead to the manufacture of gold, as the author intended, and expected. But it is a great deal when alchemistical processes are delivered in such intelligible language that you know the substances employed. This enables us easily to see the results in almost every case, and to know the new compounds which were formed during a vain search for the philosopher's stone. Had the other alchemists written as plainly, the absurdity of their researches would have been sooner discovered, and thus a useless or pernicious investigation would have sooner terminated. 7. Basil Valentine is said to have been born about the year 1394, and is perhaps the most celebrated of all the alchemists, if we except Paracelsus. He was a Benedictine monk at Erfurt in Saxony. If we believe Olaus Borrichius, his writings were enclosed in the wall of a church at Erfurt, and were discovered long after his death, in consequence of the wall having been driven down by a thunderbolt. But this story is not well authenticated, and is utterly improbable. Much of his time seems to have been taken up in the preparation of chemical medicines. It was he that first introduced antimony into medicine, and it is said that on no good authority that he first tried the effects of antimonial medicines upon the monks of his convent, upon whom it acted with such violence that he was induced to distinguish the mineral from which these medicines had been extracted by the name of antimoine, hostile to monks. What shows the improbability of this story is that the works of Basil Valentine, and in particular his Cursus Triumphalis Antimoniae, were written in the German language. Now, the German name for antimony is not antimoine, but spiceglass. The Cursus Triumphalis Antimony was translated into Latin by Kerkringius, who published it, with an excellent commentary, at Amsterdam in 1671. Basil Valentine writes with almost as much virulence against the physicians of his time as Paracelsus himself did afterwards. As no particulars of his life have been handed down to posterity, I shall satisfy myself with giving a catalogue of his writings, and then pointing out the most striking chemical substances with which he was acquainted. The books which have appeared under the name of Basil Valentine are very numerous, but how many of them were really written by him, and how many are suppositions, is extremely doubtful. The following are the principal: 1. Philosophia Occulta. 2. Traktat von Naturlichen and Übernatürlichen Dingen, auch von der ersten Tinktur, Wurzel und Geist der Metallen. 3. Von der großen Stein der Urhelaten, Verträchtelin vom Stein der Weisen. 5. Kurzer Anhang und Klarrepetition oder Wiederlein vom großen Stein der Urhelaten. 6. De prima materia lapidis philosophicae. 7. As auf philosophorum se arealae occulte de materia lapidis philosophorum. 8. Apocalypsis chemica. 9. Claves 12 philosophiae. 10. Practicae. 11. Opus proclarum ad atrumca, quod protestamante dedit filio sua abdapivo. 12. Listis testament. 13. De microcosmo. 14. Von der großen Heimlich der Welt and ihrer Arznei. 15. Von der Wissenschaft der sieben Planeten. 16. Offenbarung der Verborgenen Begriffe. 17. Conclusions or Schurschlenden. 18. Dialogues Frietis Alberti cum Spiritu. 19. Des Sulfito el Fermento Philosophum. 20. Haliographia. 21. Triumph wagen Antimony. 22. Einiger Regser Weitlebt. 23. Licht der Natur. The only one of these works that I have read with care is Kerkringius's translation and commentary on the Cursus Triumphalis Antimoniae. It is an excellent book, written with clearness and precision, and contains everything respecting antimony that was known before the commencement of the 19th century. How much of this is owing to Kerkringius I cannot say, as I have never had an opportunity of seeing a copy of the original German work of Basil Valentine. Basil Valentine, like Isaac Hollandus, was of opinion that the metals are compounds of salt, sulphur, and mercury. The philosopher's stone was composed of the same ingredients. He affirmed that there exists a great similarity between the mode of purifying gold and curing the diseases of men, and that antimony answers best for both. He was acquainted with arsenic, knew many of its properties, and mentions the red compound which forms with sulphur. Zinc seems to have been known to him, and he mentions bismuth, both under its own name, and under that of marcasite. He was aware that manganese was employed to render glass colorless. He mentions nitrate of mercury, alludes to corrosive sublimate, and seems to have known the red oxide of mercury. It would be needless to specify the preparations of antimony with which he was acquainted. Scarcely one was unknown to him which, even at present, exists in the European pharmacopoeia. Many of the preparations of lead were also familiar to him. He was aware that lead gives a sweet taste to vinegar. He knew sugar of lead, litharge, yellow oxide of lead, white carbonate of lead, and mentions that this last preparation was often adulterated in his time. He knew the method of making green vitriol, and the double chloride of iron and ammonia. He was aware that iron could be precipitated from its solution by potash, and that iron has the property of throwing down copper. He was aware that tin sometimes contains iron, and ascribed the brittleness of Hungarian iron to copper. He knew that oxides of copper gave a green color to glass, that Hungarian silver contained gold, that gold is precipitated from aqua regia by mercury in the state of an amalgam. He mentions fulminating gold, but the important facts contained in his works are so numerous, while we are so uncertain about the genuineness of the writings themselves, that it will scarcely be worth while to proceed further with the catalogue. Thus I have brought the history of alchemy to the time of Paracelsus, when it was doomed to undergo a new and important change. It will be better. History of true chemistry, and in the first place to endeavor to determine what chemical facts were known to the ancients, and how far the science had proceeded to develop itself before the time of Paracelsus. End of Section 5. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com.
Section 6 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 2 of the Chemical Knowledge Possessed by the Ancients. Part 1. Notwithstanding the assertions of Olaus Borrichius and various other writers who followed him on the same side, nothing is more certain than that the ancients have left no chemical writings behind them, and that no evidence whatever exists to prove that the science of chemistry was known to them. Scientific chemistry, on the contrary, took its origin from the collection and comparison of the chemical facts made known by the practice and improvement of those branches of manufactures which can only be conducted by chemical processes. Thus the smelting of ores and the reduction of the metals which they contain is a chemical process, because it requires for its success the separation of certain bodies which exist in the ore chemically combined with the metals, and it cannot be done except by the application or mixture of a new substance, having an affinity for these substances and capable in consequence of separating them from the metal, and thus reducing the metal to a state of purity. The manufacture of glass, of soap, of leather, are all chemical, because they consist of processes by means of which bodies, having an affinity for each other, are made to unite in chemical combination. Now I shall in this chapter point out the principal chemical manufactures that were known to the ancients, that we may see how much they contributed toward laying the foundation of the science. The chief sources of our information on this subject are the writings of the Greeks and Romans. Unfortunately, the arts and manufactures stood in a very different degree of estimation among the ancients from what they do among the moderns. Their artists and manufacturers were chiefly slaves. The citizens of Greece and Rome devoted themselves to politics or war. Such of them as turned their attention to learning confined themselves to oratory, which was the most fashionable and the only important study, or to history or poetry. The only scientific pursuit which ever engaged their attention were politics, ethics, and mathematics. For, unless Archimedes is to be considered as an exception, scarcely any of the numerous branches of physics and mechanical philosophy, which constitute so great a portion of modern science, even attracted the attention of the ancients. In consequence of the contemptible light in which all mechanical employments were viewed by the ancients, we look in vain in any of their writings for accurate details respecting the processes which they followed. The only exception to this general neglect and contempt for all the arts and trades is Pliny the Elder, whose object, in his natural history, was to collect into one focus everything that was known at the period when he lived. His work displays prodigious reading and a vast fund of erudition. It is to him that we are chiefly indebted for the knowledge of the chemical arts which were practised by the ancients. But the low estimation in which these arts were held appears evident from the wonderful want of information which Pliny so frequently displays, and the erroneous statements which he has recorded respecting these processes. Still, a great deal may be drawn from the information which has been collected and transmitted to us by this indefatigable natural historian. 1. The ancients were acquainted with 7 metals, namely gold, silver, mercury, copper, iron, tin, and lead. They knew and employed various preparations of zinc and antimony and arsenic, though we have no evidence that these bodies were known to them in the metallic state. 1. Gold is spoken of in the 2nd chapter of Genesis as existing and familiarly known before the flood.
The name of the first is Pizon, that which it is encompasseth the whole land of Havilah.
Where there is gold, and the gold of that land is good, there is bdellium and the onyx stone. The Hebrew word for gold, zeb, signifies to be clear, to shine, alluding doubtless to the brilliancy of that metal. The term gold occurs frequently in the writings of Moses, and the metal must have been in common use among the Egyptians, when that legislator led the children of Israel out of Egypt. Gold is found in the earth almost always in a native state. There can be no doubt that it was much more abundant on the surface of the earth and in the beds of rivers in the early periods of society than it is at present. Indeed, this is obvious from the account which Pliny gives of the numerous places in Asia and Greece and other European countries where gold was found in his time.
Gold, therefore,
Could hardly fail to attract the attention of the very first inhabitants of the globe. Its beauty, its malleability, its indestructibility would give it value. Accident would soon discover the possibility of melting it by heat, and thus of reducing the grains or small pieces of it found in the surface of the earth into one large mass. It would be speedily made into ornaments and utensils of various kinds, and thus gradually would come into common use. This we find to have occurred in America, where it was discovered by Columbus. The inhabitants of the tropical parts of that vast continent were familiarly acquainted with gold, and in Mexico and Peru it existed in great abundance. Indeed, the natives of these countries seem to have been acquainted with no other metal, or at least no other metal was brought into such general use, except silver, which in Peru was, it is true, still more common than gold. Gold, then, was probably the first metal with which man became acquainted, and that knowledge must have preceded the commencement of history, since it is mentioned as a common and familiar substance in the book of Genesis, the oldest book in existence, of the authenticity of which we possess sufficient evidence. The period of leading the children of Israel out of Egypt by Moses is generally fixed to have been 1,648 years before the commencement of the Christian era. So early, then, we are certain that not only gold, but the other 6 malleable metals known to the ancients were familiar to the inhabitants of Egypt. The Greeks ascribed the discovery of gold to the earliest of their heroes. According to Pliny, it was discovered on Mount Pangaeus by Cadmus, the Phoenician. But Cadmus's voyage into Greece was nearly coeval with the exit of the Israelites out of Egypt, at which time we learn from Moses that gold was in common use in Egypt. All that can be meant, then, is that Cadmus first discovered gold in Greece, not that he made mankind first acquainted with it. Others say that Thoas and Ecleus, or Sol, the son of Oceanus, first found gold in Panchaea. Thoas was a contemporary of the heroes of the Trojan War, or at least was posterior to the Argonautic expedition, and consequently long posterior to Moses and the departure of the children of Israel from Egypt. 2. Silver also was not only familiarly known to the Egyptians in the time of Moses, but, as we learn from Genesis, was coined into money before Joseph was set over the land of Egypt by Pharaoh, which happened 1,872 years before the commencement of the Christian era, and consequently 224 years before the departure of the children of Israel out of Egypt. And Joseph gathered up all the money that was found in the land of Egypt and in the land of Canaan for the corn which they bought, and Joseph brought the money into Pharaoh's house. The Hebrew word chemep, translated money, signifies silver, and was so called from its pale color. Silver occurs in many other passages of the writings of Moses. The Greeks inform us that Eryxthonius the Athenian, or Caicus, were the discoverers of silver, but both of these individuals were long posterior to the time of Joseph. Silver, like gold, occurs very frequently in the metallic state. This, no doubt, was a still more frequent occurrence in the early ages of the world. It would therefore attract the attention of mankind as early as gold, and for the same reason. It is very ductile, very beautiful, and much more easily fused than gold. It would be therefore more easily reduced into masses, and thus formed into different utensils and ornaments than even gold itself. The ores of it which occur in the earth are heavy, and would therefore draw the attention of even rude men to them. They have, most of them at least, the appearance of being metallic, and the most common of them may be reduced to the state of metallic silver simply by keeping them in a sufficient time in fusion. Accordingly, we find that the Peruvians,
Before they were overrun by the Spaniards,
had made themselves acquainted with the mode of digging out and smelting the ores of silver which occur in their country, and that many of their most common utensils were made of that metal. Silver and gold approached each other nearer in value among the ancients than at present. An ounce of fine gold was worth from 10 to 12 ounces of fine silver, the variation depending upon the accidental relation of the supply of both metals. But after the discovery of America, the quantity of silver found in that continent, especially in Mexico, was so great compared with that of the gold found, that silver became considerably cheaper, so that an ounce of fine gold came to be equivalent to about 14 ounces and a half of fine silver. Of course, these relative values have fluctuated a little according to the abundance of the supply of silver. Though the revolution in the Spanish-American colonies has considerably diminished the supply of silver from the mines, that deficiency seems to have been supplied by other ways, and thus the relative proportion between the value of gold and silver has continued nearly unaltered. That copper must have been known in the earliest ages of society is sufficiently evident. It occurs frequently native, and could not fail to attract the attention of mankind, from its color, weight, and malleability. It would not be difficult to fuse it even in the rudest ages, and when melted into masses, as it is malleable and ductile, it would not require much skill to convert it into useful and ornamental utensils. The Hebrew word neheshet, translated brass, obviously means copper. We have the authority of the book of Genesis to satisfy us that copper was known before the flood, and probably as early as either silver or gold. And Zillah, she also bore Tubal-Cain, an instructor of every artificer in brass, copper, and iron.
the word copper
Occurs in many other passages of the writings of Moses. That the Hebrew word translated brass must have meant copper is obvious from the following passage. Out of whose hills thou mayest dig brass. Brass does not exist in the earth, nor any ore of it. It is always made artificially. It must therefore have been copper, or an ore of copper, that was alluded to by Moses. Copper must have been discovered and brought into common use long before iron or steel, for Homer represents his heroes of the Trojan War as armed with swords, etc., of copper. Copper itself is too soft to be made into cutting instruments, but the addition of a little tin gives it the requisite hardness. Now we learn from the analyses of Klaproth that the copper swords of the ancients were actually hardened by the addition of tin. Copper was the metal in common use in the early part of the Roman Commonwealth. Romulus coined copper money alone. Numa established a college of workers in copper, Ariorum Fabrum. The Latin word os sometimes signifies copper and sometimes brass. It is plain from what Pliny says on the subject that he did not know the difference between copper and brass. He says that an ore of os occurs in Cyprus, called chalcetis, where os was first discovered. Here, os obviously means copper. In another place, he says that os is obtained from a mineral called cadmia.
Now, from the account of cadmia by Pliny and Dioscorides,
there cannot be a doubt that it is the ore to which the moderns have given the name of calamine, by means of which brass is made. It is sometimes a silicate and sometimes a carbonate of zinc, for both of these ores are confounded together under the name of cadmia, and both are employed in the manufacture of brass. Solinus says that os was first made at Chalcis, a town in Euboea,
hence the Greek name chalkos,
by which copper was distinguished. The proper name for brass, by which is meant an alloy of copper and zinc, was aurichalcum, or golden or yellow copper. Pliny says that, long before his time, the ore of aurichalcum was exhausted, so that no more of that beautiful alloy was made. Are we to conclude from this that there once existed an ore consisting of calamine and ore of copper, mixed or united together? After the exhaustion of the aurichalcum mine, the salustanum became the most famous, but it soon gave place to the Livianum, a copper mine in Gaul named after Livia, the wife of Augustus.
Both these mines were exhausted in the time of Pliny.
The os Marianum, or copper of Cordova, was the most celebrated in his time. This last os, he says, absorbs most cadmia and acquires the greatest resemblance to aurichalcum. We see from this that in Pliny's time brass was made artificially, and by a process similar to that still followed by the moderns. The most celebrated alloy of copper among the ancients was the os Corinthium, or Corinthian copper, formed accidentally, as Pliny informs us, during the burning of Corinth by Mummius in the year 608, after the building of Rome, or 145 years before the commencement of the Christian era. There were 4 kinds of it,
of which Pliny gives the following description.
Not, however, very intelligible. White. It resembled silver much in its luster, and contained an excess of that metal. Red. In this kind there is an excess of gold. In the 3rd kind, gold, silver, and copper are mixed in equal proportions. The 4th kind is called hepatizon, from its having a liver color. It is this color which gives it its value. Copper was put by the ancients to almost all the uses to which it is put by the moderns. One of the great sources of its consumption was bronze statues, which were first introduced into Rome after the conquest of Asia Minor. Before that time, the statues of the Romans were made of wood or stoneware. Pliny gives various formulas for making bronze for statues. Of these it may be worthwhile to put down the most material. 1. To new copper, add a 3rd part of old copper. To every 100 pounds of this mixture, 12 pounds and a half of tin are added, and the whole melted together. Footnote. Pliny's phrase is plumbum argentorium, but that addition was tin, and consequently that plumbum argentorium meant tin. We have the evidence of Klaproth, who analyzed several of these bronze statues and found them composed of copper, lead, and tin. End footnote. 2. Another kind of bronze for statues was formed by melting together 100 pounds copper, 10 pounds lead, 5 pounds tin. 3. Their copper pots for boiling consisted of 100 pounds of copper melted with 3 or 4 pounds of tin. The 4 celebrated statues of horses, which, during the reign of Theodosius II, were transported from Chio to Constantinople, and when Constantinople was taken and plundered by the Crusaders and Venetians in 1204, were sent by Martin Zeno and set up by the Doge Peter Ziani in the portal of St. Mark, were in 1798 transported by the French to Paris, and finally, after the overthrow of Bonaparte and the restoration of the Bourbons in 1815, returned to Venice and placed upon their ancient pedestals. The metal of which these horses had been made was examined by Klaproth, and found by him to be composed of copper 993 parts, tin 7 parts. Klaproth also analyzed an ancient bronze statue in one of the German cabinets, and found it composed of copper 916 parts, tin 75 parts, lead 9 parts. Several other old brass and bronze pieces of metal, very ancient but found in Germany, were also analyzed by Klaproth. The result of his analyses was as follows. The metal of which the altar of Crodo was made consisted of copper 69 parts, zinc 18 parts, lead 13 parts. The emperor's chair, which had in the 11th century been transported from Harzburg to Goslar, where it still remains, was found to be composed of copper 92.5 parts, tin 5 parts, lead 2.5 parts. Another piece of metal, which enclosed the high altar in a church in Germany, was composed of copper 75 parts, tin 12.5 parts, lead 12.5 parts. These analyses, though none of them corresponds exactly with the proportions given by Pliny, confirm sufficiently his general statement that the bronze of the ancients employed for statues was copper, alloyed with lead and tin. End of section 6. Recording by April Walters. Section 7 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 2 of the Chemical Knowledge Possessed by the Ancients, Part 2. Some of the bronze statues cast by the ancients were of enormous dimensions, and show decisively the great progress which had been made by them in the art of working and casting metals. The addition of the lead and tin would not only add greatly to the hardness of the alloy, but would at the same time render it more easily fusible. The bronze statue of Apollo, placed in the Capitol at the time of Pliny, was 45 feet high and cost 500 talents, equivalent to about 50,000 pounds of our money. It was brought from Apollonia, in Pontus, by Lucullus. The famous statue of the sun at Rhodes was the work of Chares, a disciple of Lysippus. It was 90 feet high, was 12 years in making, and cost 300 talents, about 30,000 pounds. It was made out of the engines of war left by Demetrius when he raised the siege of Rhodes. After standing 56 years, it was overthrown by an earthquake. It lay on the ground 900 years and was sold by Movia, king of the Saracens, to a merchant who loaded 900 camels with the fragments of it. Copper was introduced into medicine at rather an early period of society, and various medicinal preparations of it are described by Dioscorides and Pliny. It remains for us to notice the most remarkable of these. Pliny mentions an institution to which he gives the name of Supplasia, the object of which was to prepare medicines for the use of medical men. It seems, therefore, to have been similar to our apothecary shops of the present day. Pliny reprobates the conduct of persons who had the charge of these supplasiae at this time. They were in the habit of adulterating medicines to such a degree that nothing good or genuine could be procured from them. Both the oxides of copper were known to the ancients, though they were not very accurately distinguished from each other. They were known by the names floss aeris and scoria aeris, or squama aeris. They were obtained by heating bars of copper red hot and letting them cool, exposed to the air. What fell off during the cooling was the floss. What was driven off by blows of a hammer was the squama or scoria iris. It is obvious that all of these substances were nearly of the same nature, and they were in reality mixtures of the black and red oxides of copper. Stomoma seems to have also been an oxide of copper, which was gradually formed upon the surface of the metal when it was kept in a state of fusion. These oxides of copper were used as external applications in cases of polypi of the nose, diseases of the anus, ear, and mouth, etc., seemingly as escharotics. Irugo, verdigris, was a subacetate of copper, doubtless often mixed with subacetate of zinc, as not only copper but brass also was used for preparing it. The mode of preparing this substance was similar to the process still followed. Whether verdigris was employed as a paint by the ancients does not appear, for Pliny takes no notice of any such use of it. Chalcantum, also called atramentum suturium, was probably a mixture of sulphate of copper and sulphate of iron. Pliny's account of the mode of procuring it is too imperfect to enable us to form precise ideas concerning it, but it was crystallized in strings, which were extended for the purpose in the solution. Its color was blue, and it was transparent like glass. This description might apply to sulphate of copper, but as the substance was used for blackening leather, and on that account was called astramentum suturium, it is obvious that it must have contained also sulphate of iron. Chalcitis was the name for an ore of copper. The account given of it by Pliny agrees best with copper pyrites, which is now known to be a sulfur salt, composed of 1 atom of sulphide of copper, the acid, united to 1 atom of sulphide of iron, the base. Pliny informs us that it is a mixture of copper, mizy, and sori. Its color is that of honey. By age, he says, it changes into sori. I think it most probable that native sori, of which Pliny speaks, was sulphuret of copper and artificial sori sulphate of copper. The native sori is said to constitute black veins in chalcitis. Pliny's description of mizy best agrees with copper pyrites. Dioscorides describes it as hard, as having the color of gold, and as shining like a star. All of this agrees pretty well with copper pyrites. Scolica, so called because it assumed the shape of a worm, was formed by triturating alumen, carbonate of soda, and white vinegar, till the matter became green. It was probably a mixture of sulphate of soda, acetate of alumina, and acetate of copper, probably with more or less oxide of copper, etc., depending upon the proportions of the respective constituents employed. Such are the preparations of copper employed by the ancients. They were only used as external applications, partly as escharotics, and partly to induce ulcers to put on a healthy appearance. It does not appear that copper was ever used by the ancients as an internal remedy. 4. Though zinc in the metallic state was unknown to the ancients, Yet, as they knew some of its ores and employed preparations of it in medicine, and were in the habit of alloying copper with it, and converting it into brass, it will be proper to state here what was known to them concerning it. Pliny nowhere makes us acquainted with the process by which copper was converted into brass, nor does he seem to have been acquainted with it. But from several facts incidentally mentioned by him, it is obvious that their process was similar to that which is followed at present by modern brass makers. The copper in grains is mixed with a certain quantity of calamine, cadmia, and charcoal, and exposed for some time to a moderate heat in a covered crucible. The calamine is reduced to the metallic state and imbibed by the copper grains. When the copper is thus converted into brass, the temperature is raised sufficiently high to melt the whole. It is then poured out and cast into a slab or ingot. The cadmia employed by ancients in medicine was not calamine, but oxide of zinc, which sublimed during the fusion of brass in an open vessel. It was distinguished by a variety of names, according to the state in which it was obtained. The lighter portion was called capnitis. Botrytis was the name of the portion in the interior of the chimney. Its name was derived by some resemblance which it was supposed to have to a bunch of grapes. It had two colors, ash and red. The red variety was reckoned best. This red color it might derive from some copper mixed with it, but more probably from iron, for a small quantity of oxide of iron is sufficient to give oxide of zinc a rather beautiful red color. The portion collected on the sides of the furnace was called placitis. It constituted a crust, and was distinguished by different names according to its color. Onychitis, when it was blue externally but spotted internally. Ostrachitis, when it was black and dirty looking. This last variety was considered an excellent application to wounds. The best cadmia in Pliny's time was furnished by the furnaces of the Isle of Cyprus. It was used as an external application in ulcers, inflammations, eruptions, etc., so that its use in medicine was pretty much the same as at present. Sulphate and acetate of zinc were unknown to the ancients. No attempt seems to have been made by them to introduce any preparations of zinc as internal medicines. Pompolix was a name given to oxide of zinc, sublimed by the combustion of the zinc which exists in brass. Sporos seems to have been a mixture of oxides of zinc and copper. There were different varieties of it, distinguished by various names. 5. Iron exists very rarely in the earth in a metallic state, but most commonly in the state of an oxide, and the processes necessary to extract metallic iron from these ores are much more complicated and require much greater skill than the reduction of gold, silver, or copper from their respective ores. This would lead us to expect that iron would have been much longer in being discovered than the three metals whose names have just been given. But we learn from the book of Genesis that iron, like copper and gold, was known before the flood, Tubal-Cain being represented as an artificer in copper and iron. The Hebrew word for iron, berazel, is said to be derived from ber, bright, nezel, to melt, and would lead one to the suspicion that it referred to cast iron rather than malleable iron. It is possible that in these early times
native iron may have existed, as well as native gold,
silver, and copper, and in this way Tubal-Cain may have become acquainted with the existence and properties of this metal. In the time of Moses, who was learned in all the wisdom of the Egyptians, iron must have been in common use in Egypt, for he mentions furnaces for working iron, ores from which it was extracted, and tells us that swords, knives, axes, and tools for cutting stones were then made of that metal. Now iron in its pure metallic state is too soft to be applied to these uses. It is obvious, therefore, that in Moses' time, not only iron, but steel also must have been in common use in Egypt. From this we see how much further advanced the Egyptians were than the Greeks in the knowledge of the manufacture of this most important metal. For during the Trojan War, which was several centuries after the time of Moses, Homer represents his heroes as armed with swords of copper, hardened by tin, and never using any weapons of iron whatever. Nay, in such estimation was it held, that Achilles, when he celebrated games in honor of Patroclus, proposes a ball of iron as one of his most valuable prizes. Then hurled the hero, thundering on the ground, a mass of iron, an enormous round, whose weight and size the circling Greeks admire, rude from the furnace and but shaped by fire. This mighty quoit Aetion wont to rear, and from his whirling arm dismissed in air. The giant by Achilles slain, he stowed among his spoils this memorable load. For this he bids those nervous artists vie, that teach the disk to sound along the sky. Let him whose might can hurl this bowl arise, who farthest hurls it, takes it as his prize. If he be one enriched with large domain of downs for flocks and arable for grain, small stock of iron needs that man provide, his hinds and swains whole years will be supplied from hence, nor ask the neighboring cities aid for plowshares, wheels, and all the rural trade. The mass of iron was large enough to supply a shepherd or plowman with iron for 5 years. This circumstance is sufficient proof of the high estimation in which iron was held during the time of Homer. Were a modern poet to represent his hero as holding out a large lump of iron as a prize, and were he to represent this prize as eagerly contended for by kings and princes, it would appear to us perfectly ridiculous. Hesiod informs us that the knowledge of iron was brought over from Phrygia to Greece by the Dactyli, who settled in Crete during the reign of Minos I, about 1431 years before the commencement of the Christian era, and consequently about 60 years before the departure of the children of Israel from Egypt. And it does not appear that in Homer's time, which is about 500 years later, the art of smelting iron had been so much improved as to enable men to apply it to the common purposes of life, as had long before been done by the Egyptians. The general opinion of the ancients was that the method of smelting iron ore had been brought to perfection by the Chalybes, a small nation situated near the Black Sea, and that the name Chalybes, occasionally used for steel, was derived from that people. Pliny informs us that ores of iron are scattered very profusely almost everywhere, that they exist in Elba, that there was a mountain in Cantabria composed entirely of iron ore, and that the earth in Cappadocia, when watered from a certain river, is converted into iron. He gives no account of the mode of smelting iron ores, nor does he appear to have been acquainted with the processes, for he says that iron is reduced from its ore precisely in the same way as copper is. Now we know that the processes for smelting copper and iron are quite different, and founded upon different principles. He says that in his time many different kinds of iron existed, and that they were stricturae, in Latin astringenda Alchymy. That steel was well known and in common use when Pliny wrote is obvious from many considerations, but he seems to have had no notion of what constituted the difference between iron and steel, or of the method employed to convert iron into steel. In his opinion, it depended upon the nature of the water, and consisted in heating iron red hot and plunging it while in that state into certain waters. The waters at Bilbilis and Turiasso in Spain and at Comum in Italy possess this extraordinary virtue. The best steel in Pliny's time came from China. The next best, in point of quality, was manufactured in Parthia. It would appear that at Noricum steel was manufactured directly from the ore of iron. This process was perfectly practicable, and is said still to be practiced in certain cases. The ancients were acquainted with the method of rendering iron, or rather steel, magnetic, as appears from a passage in the 14th chapter of the 34th book of Pliny. Magnetic iron was distinguished by the name ferrum vivum. When iron is dabbed over with alumen and vinegar, it becomes like copper, according to Pliny. Cerussa, gypsum, and liquid pitch keep it from rusting. Pliny was of opinion that a method of preventing iron from rusting had been once known, but had been lost before his time. The iron chains of an old bridge over the Euphrates had not rusted in Pliny's time, but a few new links, which had been added to supply the place of some that had decayed, were become rusty. It would appear from Pliny that the ancients made the use of something very like tractors, for he says that pain in the side is relieved by holding it near the point of a dagger that has wounded a man. Water in which red-hot iron had been plunged was recommended as a cure for the dysentery, and the actual cautery with a red-hot iron, Pliny informs us, prevents hydrophobia, when a person has been bitten by a mad dog. Rusts of iron and scales of iron were used by the ancients as astringent medicines. 6. Tin, also, must have been in common use in the time of Moses, for it is mentioned without any observation as one of the common metals. And from the way in which it is spoken of by Isaiah and Ezekiel, it is obvious it was considered as of far inferior value to silver and gold. Now tin, though the ores of where it does occur are usually abundant, is rather a scarce metal. That is to say, there are but few spots on the face of the earth where it is known to exist. Cornwall, Spain, in the mountains of Galicia, and the mountains which separate Saxony and Bohemia are the only countries in Europe where tin occurs abundantly. The last of these locations has not been known for 5 centuries. It was from Spain and from Britain that the ancients were supplied with tin, for no mines of tin exist, or have ever been known to exist, in Africa or Asia, except in the East Indies. The Phoenicians were the first nation which carried on a great trade by sea. There is evidence that at a very early period they traded with Spain and with Britain, and from these countries they drew their supplies of tin. It is doubtless the Phoenicians that supplied the Egyptians with this metal. They had imbibed strongly a spirit of monopoly, and to secure the whole trade of tin, they carefully concealed the source from which they drew that metal. Hence, doubtless, the reason why the Grecian geographers, who derived their information from Phoenicians, represented the Insulae Cassiterides, or Tin Islands, as a set of islands lying off the north coast of Spain. We know, in fact, the Scilly Islands in these early ages yielded tin, though doubtless the great supply was drawn from the neighboring province of Cornwall. It was probably from these islands that the Greek name for tin was derived, Casseteros. Even Pliny informs us that in his time tin was obtained from the Cassiterides and from Lusitania and Galicia. It occurs, he says, in grains in alluvial soil, from which it is obtained by washing. It is in black grains, the metallic nature of which is only recognizable by the great weight. This is a pretty accurate description of stream tin, which we know formerly constituted the only ore of that metal wrought in Cornwall. He says that the ore occurs also along with grains of gold, that it is separated from the soil by washing it along with the grains of gold, and afterwards smelted separately. Pliny gives no particulars about the mode of reducing the ore of tin to the metallic state, nor is it at all likely that he was acquainted with the process. The Latin term for tin was pumblum album. Stannum is also used by Pliny, but it is impossible to understand the account which he gives of it. There is, he says, an ore consisting of lead united to silver. When this ore is smelted, the first metal that flows out is stannum. What flows next is silver. What remains in the furnace is galena. This being smelted yields lead. Were we to admit the existence of an ore composed of lead and silver, it is obvious that no such products could be obtained simply by smelting it. Casseteros, or tin, is mentioned by Homer, and from the way in which the metal is said by him to have been used, it is obvious that in his time it bore a much higher price, and consequently was more valued than at present. In his description of the breastplate of Agamemnon, he said that it contained 10 bands of steel, 12 of gold, and 20 of tin. And in the 23rd book of the Iliad, line 561, Achilles describes a copper breastplate surrounded with shining tin. Pliny informs us that in his time tin was adulterated by adding to it 1/3 of white copper. A pound of tin, when Pliny lived, cost 10 denarii. Now, if we reckon a denarius at 7 3/4 penny, with Dr. Arbuthnot, this would make a Roman pound of tin to cost 6 shillings 5 1/2 pennies. But as the Roman pound was only equal to 3/4 of our avoirdupois pound, it is plain in the time of Pliny an avoirdupois pound of tin was worth 8 shillings 7 1/4 pence, which is almost 7 times the price of tin in the present day. End of section 7. Recording by April Walters. Section 8 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 2 of the Chemical Knowledge Possessed by the Ancients, Part 3. Tin, in the time of Pliny, was used for covering the inside of copper vessels, as it is at this day. And no doubt the process still followed is of the same nature as the process used by the ancients for tinning copper. Pliny remarks with surprise that copper thus tinned does not increase in weight. Now Bayen ascertained that a copper pan, 9 inches in diameter and 3 inches 3 lines in depth, when tinned, only acquired an additional weight of 21 grains. These measures and weights are French. When we convert them into English, we have a copper pan 9.59 inches in diameter and 3.46 inches deep, which, when tinned, increased in weight 17.23 troy grains. Now the surface of the copper pan, thus tinned, was 176.468 square inches. Hence it follows that a square inch of copper, when tinned, increases in weight only 0.097 grains. This increase is so small that we may excuse Pliny, who probably had never seen the increase of weight determined except by means of a rude Roman statera, for concluding that there was no increase of weight whatever. Tin was employed by the ancients for mirrors, But mirrors of silver were gradually substituted, and these in Pliny's time had become so common that they were even employed by female servants or slaves. That Pliny's knowledge of the properties of tin was very limited, and far from accurate, is obvious from his assertion that tin is less fusible than silver. It is true that the ancients had no measure to determine the different degrees of heat, but as tin melts at a heat under redness, while silver requires a bright red heat to bring it into fusion, a single comparative trial would have shown him which was most fusible. This trial, it is obvious, had never been made by him. The ancients seem to have been ignorant of the method of tinning iron. At least, no reference to tin plate is made by Pliny or by any other ancient author that I have had an opportunity of consulting. It would appear from Pliny that both copper and brass were tinned by the Gauls at an early period. Tinned brass was called aura coctilia, and was so beautiful that it almost passed for silver. Plating, or covering the metal with plates of silver, was gradually substituted for tinning, and finally gilding took the place of plating. The trappings of horses, chariots, etc., were thus ornamented. Pliny nowhere gives a description of the process of plating, but there can be little doubt that it was similar to that at present practiced. Gilding was accomplished by laying an amalgam of gold on the copper or brass, as at present. 7. Lead appears also to have been in common use among the Egyptians at the time of Moses. It was distinguished among the Romans by the name of plumbum nigrum. In Pliny's time, the lead mines existed chiefly in Spain and Britain. In Britain, lead was so abundant that it was prohibited to extract above a certain quantity in a year. The mines lay on the surface of the earth. Derbyshire was the county in which the lead ores were chiefly wrought by the Romans. The rich mines in the north of England seem to have been unknown to them. Pliny was of opinion that if a lead mine, after being exhausted, be shut up for some time, the ore will be again renewed. In the time of Pliny, leaden pipes were commonly used for conveying water. The vulgar notion that the ancients did not know that water will always rise in pipes as high as the source from which it proceeds, and that it was this ignorance which led to the formation of aqueducts, is quite unfounded. Nobody can read Pliny without seeing that this important fact was well known in his time. Sheet lead was also used in the time of Pliny, and applied to the same purposes as at present. But lead was much higher priced among the ancients than it is at present. Pliny informs us that its price was to that of tin as 7 to 10. Hence it must have sold at the rate of 6 shillings quarter pence per pound. The present price of lead does not much exceed 3 halfpence the pound. It is therefore only 1/48th part of the price which it bore in the time of Pliny. This difference must be chiefly owing to the improvements made by moderns in working the mines and smelting the ores of lead. Tin, in Pliny's time, was used as a solder for lead. For this purpose it is well adapted, as it is so much easier smelted than lead. But when he says that lead is used also as a solder for tin, his meaning is not so clear. Probably he means an alloy of lead and tin, which, fusing at a lower point than tin, may be used to solder that metal. The addition of some bismuth reduces the fusing point materially, but that metal was unknown to the ancients. Argentarium is an alloy of equal parts of lead and tin. Tertiarium, of 2 parts lead and 1 part tin. It was used as a solder. Some preparations of lead were used by the ancients in medicine, as we know from the descriptions of them given us by Dioscorides and Pliny. These preparations consisted chiefly of proto-oxide of lead and lead reduced to powder, and partially oxidized by triturating it with water in a mortar. They were applied to ulcers and employed externally as astringents. Molybdena was also employed in medicine. Pliny says it was the same as galena. From his description, it is obvious that it was litharge, for it was in scales and was more valued the nearer its color approached to that of gold. It was employed, as it still is, for making plasters. Pliny gives us the process for making the plaster employed by the Roman surgeons. It was made by heating together 3 pounds molybdena or litharge, 1 pound wax, 3 hemini or 1½ pints of olive oil. This process is very nearly the same as the one at present followed by apothecaries for making adhesive plaster. Simithium, or cerussa, was the same as our white lead. It was made by exposing lead in sheets to the fumes of vinegar. It would seem probable from Pliny's account, though it is confused and inaccurate, that the ancients were in the habit of dissolving cerussa in vinegar and thus making an impure acetate of lead. Cerussa was used in medicine. It constituted also a common white paint. At one time, Pliny says it was found native, but in his time all that was used was prepared artificially. Cerussa usta seems to have been nearly the same as our red lead. It was formed accidentally from cerussa during the burning of the Piraeus. The color was purple. It was imitated at Rome by burning Silis marmarosus, which was probably a variety of some of our ochres. 8. Besides the metals above enumerated, the ancients were also acquainted with quicksilver. Nothing is known about the first discovery of this metal, though it obviously precedes the commencement of history. I am not aware that the term occurs in the writings of Moses. We have therefore no evidence it was known to the Egyptians at that early period, nor do I find any allusion to it in the works of Herodotus. But this is not surprising, as that author confines himself chiefly to subjects connected with history. Dioscorides and Pliny both mentioned it as common in their time. Dioscorides gives a method of obtaining it by sublimation from cinnabar. It is remarkable because it constitutes the first example of a process which ultimately led to distillation. Cinnabar is also described by Theophrastus. The term minium was applied to it also, till in consequence the adulteration of cinnabar with red lead, the term minium came at last to be restricted to that preparation of lead. Theophrastus describes an artificial cinnabar, which came from the country above Ephesus. It was a shining red-colored sand, which was collected and reduced to a fine powder by pounding it in vessels of stone. We do not know what it was. The native cinnabar was found in Spain and was used chiefly as a paint. Dioscorides employs minium as a name for what we at present call cinnabar, or bisulphuret of mercury. His cinnabar was a red paint from Africa, produced in such small quantities that painters could scarcely procure enough of it to answer their purposes. Mercury is described by Pliny as existing native in the mines of Spain, and Dioscorides gives the process for extracting it from cinnabar. It was employed in gilding precisely as it is by the moderns. Pliny was aware of its great specific gravity and of the readiness with which it dissolves gold. The amalgam was squeezed through leather, which separated most of the quicksilver. When the solid amalgam remaining was heated, the mercury was driven off and pure gold remained. It is obvious from what Dioscorides says that the properties of mercury were very imperfectly known to him. He says that it may be kept in vessels of glass, or of lead, or of tin, or of silver. Now it is well known that it dissolves lead, tin, and silver with so much rapidity that vessels of these metals,
Were mercury put into them,
would be speedily destroyed. Pliny's account of quicksilver is rather obscure. It seems doubtful whether he was aware that native argentum vivum and the hydrargium extracted from the cinnabar were the same. Cinnabar was occasionally used as an external medicine, but Pliny disapproves of it, assuring his readers that quicksilver and all its preparations are virulent poisons. No other mercurial preparations, except cinnabar and the amalgam of mercury, seems to have been known to the ancients. Footnote: the ancients were in the habit of extracting mercury from cinnabar by a kind of imperfect distillation. The native mercury they called argentum vivum, that from cinnabar hydrogyrus. End footnote. 9. The ancients were unacquainted with the metal to which we at present give the name antimony, but several of the ores of that metal, and of the products of these ores, were not altogether unknown to them. From the account of stimi and stibium by Dioscorides and Pliny, there can be little doubt that these names were applied to the mineral now called sulphuret of antimony, or crude antimony. It is found most commonly, Pliny says,
among the ores of silver, and consists of two kinds,
the male and the female, the latter of which is most valued. This pigment was known at a very early period, and employed by the Asiatic ladies in painting their eyelashes, or rather the insides of their eyelashes, black. Thus it is said of Jezebel that when Jehu came to Jezreel, she painted her face. The original is She put her eyes in sulphuret of antimony. A similar expression occurs in Ezekiel. For whom thou didst wash thyself, paintedst thine eyes. Literally, put thy eyes in sulphuret of antimony. This custom of painting the eyes black with antimony was transferred from Asia to Greece, and while the Moors occupied Spain, it was employed by the Spanish ladies also. It is curious that the term alcohol, at present confined to spirit of wine, was originally applied to the powder of sulphuret and antimony. The ancients were in the habit of roasting sulphuret of antimony, and thus converting it into an impure oxide. This preparation was also called stymi and stybium. It was employed in medicine as an external application, and was conceived to act chiefly as an astringent. Dioscorides describes the method of preparing it. We see from Pliny's account of stybium that he did not distinguish between sulphuret of antimony and oxide of antimony. Some of the compounds of arsenic
were also known to the ancients,
though they were neither acquainted with the substance in the metallic state nor with its oxide, the poisonous nature of which is so violent that had it been known to them it could not have been omitted by Dioscorides and Pliny. The word sandaraki occurs in Aristotle and the term arenikon in Theophrastus. Dioscorides uses likewise the same name with Aristotle. It was applied to a scarlet-colored mineral which occurs native and is now known by the name of realgar. It is a compound of arsenic and sulfur. It was employed in medicine both externally and internally, and is recommended by Dioscorides as an excellent remedy for an inveterate cough. Auripigmentum and arsenicum were names given to the native yellow sulphuret of arsenic. It was used in the same way, and considered by Dioscorides and Pliny as of the same nature with realgar. But there is no reason for supposing that the ancients were acquainted with the compositions of either of these bodies, far less that they had any suspicion of the existence of the metal
to which we at present give the name of arsenic.
Such is a sketch of the facts known to the ancients respecting metals. They knew the 6 malleable metals which are still in common use, and applied them to most of the purposes to which the moderns apply them. Scarcely any information has been left us of the methods employed by them to reduce these metals from their ores. But, unless the ores were of a much simpler nature than the modern ores of these metals, of which we have no evidence, the smelting processes with which the ancients were familiar could scarcely have been contrived without a knowledge of the substances united with the different metals in their ores, and of the means by which these foreign bodies could be separated and the metals isolated from all impurities. This doubtless implied a certain quantity of chemical knowledge, which having been handed down to the moderns, served as a foundation upon which the modern science of chemistry was gradually reared. At the same time it will be admitted that this foundation was very slender, and would of itself led to little. Most of the oxides, sulphurets, etc., and almost all of the salts into which these metallic bodies enter, were unknown to the ancients. Besides the working in metals, there were some other branches of industry practiced by the ancients so intimately connected with chemical science that it would be improper to pass them over in silence. The most important of these are the following. 2. Colors used by painters. It is well known that the ancient Grecian artists carried the art of painting to the highest degree of perfection, and that their paintings were admired and sought after by the most eminent and accomplished men of antiquity. And Pliny gives us a catalogue of a great number of first-rate pictures, and a historical account of a vast many celebrated painters of antiquity. In his own time, he says, the art of painting had lost its importance, statues and tablets having came in place of pictures. 2 kinds of colors were employed by the ancients, namely the florid and the austere. The florid colors, as enumerated by Pliny, were minium, arminium, cinnaberis, chrysocolla, purpurissum, and indicium purpurissum. The word minium, as used by Pliny, means red lead, though Dioscorides employs it for bisulphuret of mercury or cinnabar. Armenium was obviously an ochre, probably of a yellow or orange color. Cinnaberis was bisulphuret of mercury, which is known to have a scarlet color. Dioscorides employs it to denote a vegetable red color, probably similar to the resin at present called dragon's blood. Cryoscolla was a green-colored paint, and from Pliny's description of it could have been nothing else than carbonate of copper or malachite. Purpurissum was a lake, as is obvious from the account of its formation given by Pliny. The coloring matter is not specified, but from the term used there can be little doubt that it was the liquor of the shellfish that yielded the celebrated purple dye of the Tyrians. Indicum purpurissum was probably indigo. This might be implied from the account of it given by Pliny. The austere colors used by the ancient painters were of two kinds, native and artificial. The native were sinopis, rubrica, parætonium, melinum, eretria, auripigmentum. The artificial were ochra, cerussa, usta, sandaraca, sandix, syricum, atramentum. Sinopsis is the red substance now known by the name of reddle and used for marking. On that account it is sometimes called red chalk. It was found in Pontus, in the Balearian Islands, and in Egypt. The price was 3 denarii, or 1 shilling
11 1/4
pence the poundweight. The most famous variety of sinopsis was from the Isle of Lemnos. It was sold sealed and stamped, hence it was called sphagris. It was employed to adulterate minium. In medicine it was used to appease inflammation and as an antidote to poison. Ochre is merely sinopis heated in a covered vessel. The higher the temperature to which it has been exposed, the better it is. Leucophrum is a compound of 6 pounds sinopsis of Pontus, 10 pounds cerus, 2 pounds melenium, triturated together for 30 days. It was used to make gold adhere to wood. Rubrica, from the name, was probably a red ochre. Parætonium was a white color, so called from a place in Egypt where it was found. It was obtained also in the island of Crete and in Cyrene. It was said to be a combination of the froth of the sea consolidated with mud. It consisted probably of carbonate of lime. 6 pounds of it cost only 1 denarius. Melinum was also a white-colored powder found in Melos and Samos in veins. It was most probably a carbonate of lime. Eretria was named from the place where it was found.
Pliny gives its medical properties,
but does not inform us of its color. It is impossible to say what it was. Auripigmentum was yellow sulphuret of arsenic. It was probably but little used as a pigment by the ancient painters. Cerussa usta was red lead. Sandaraca was red sulphuret of arsenic. The pound of sandaraca cost 5 as was imitated by red lead. Both it and ochre were found in the island Topazos in the Red Sea. Sandix was made by torrefying equal parts of true sandaraca and sinopsis. It cost half the price of sandaraca. Virgil mistook this pigment for a plant, as is obvious from the following line: Sponte sua sandix, pascentis vestiet agnos. Syricum is made by mixing sinopsis and sandix. Atramentum was obviously from Pliny's account of it lamp black. He mentions ivory black as an invention of Apelles. It was called elephantinum. There was a native atramentum which had the color of sulphur and got a black color artificially. It is not unlikely that it contained sulfate of iron, and that it got its black color from the admixture of some astringent substance. The ink of the ancients was lamp black mixed with water, containing some gum or glue dissolved in it. Atramentum indicium was the same as our China ink. End of section 8. Recording by April Walters.
Section 9 of the History of Chemistry by Thomas Thompson. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Your reader is Rosie Roberts from California. The ink of the ancients was lamp black, mixed with water, containing gum or glue dissolved in it. Atramentum indicum was the same as our China ink. The purpurissum was a high-priced pigment. It was made by putting Creta argentaria, open parentheses, a species of white clay, close parentheses, into the cauldrons containing the ingredients for dyeing purple. The Creta imbibed the purple color and became purpurissum. The first portion of the Creta put in constituted the finest and highest priced pigment. The portions put in afterwards became successively worse, and were of consequence lower priced. We see from this description that it was a lake similar to our modern cochineal lakes. That the purpurissum indicum was indigo is obvious from the statement of Pliny. that when thrown upon hot coals, it gives out a beautiful purple flame. This constitutes the character of indigo. Its price in Pliny's time was 10 denarii, or 6 shillings and 5 pence halfpenny, the Roman pound, which is equivalent to 8s. 7 1/3 d, the avoirdupois. Though few of none of the ancient pictures have been preserved, yet several specimens of the colors used by them still remain in Rome and in the ruins of Herculaneum. Among others, the fresco paintings in the baths of Titus still remain, and as these were made for a Roman emperor, we might expect to find the most beautiful and costly colors employed in them. These paints and some others were examined by Sir Humphrey Davy in 1813 while he was in Rome. From his researches we derived some pretty accurate information respecting the colors employed by the painters of Greece and Rome. 1. Red paints. 3 different kinds of red were found in a chamber opened in 1811 in the baths of Titus, namely a bright orange red, a dull red, and a brown red. The bright orange red was minium, or red lead. The other 2 were merely 2 varieties of iron ochres. Another still brighter red was observed on the walls. It proved on examination to be vermilion or cinnabar. 2. Yellow paints. All the yellows examined by Davy proved to be iron ochres, sometimes mixed with a little red lead. Orpiment was undoubtedly employed, as is obvious from what Pliny says on the subject, but Davy found no traces of it among the yellow colors which he examined. A very deep yellow, approaching orange, which covered a piece of stucco in the ruins near the monument of Caius Cestius, proved to be protoxide of lead, or massicot mixed with some red lead. The yellows in the Aldobrandini pictures were all ochres, and so were those in the pictures on the walls of the houses at Pompeii. 3. Blue paints. Different shades of blues are used in the different apartments of the baths of Titus, which are darker or lighter, as they contain more or less carbonate of lime, with which the blue pigment had been mixed by the painter. This blue pigment turned out, on examination, to be a frit composed of alkali and silica, fused together with a certain quantity of oxide of copper. This was the color called schwannos by the Greeks, and ceruleum by the Romans. Vitruvius gives the method of preparing it by heating strongly together sand, carbonate of soda, and fillings of copper. Davy found that 15 parts by weight anhydrous carbonate of soda, 20 parts of powdered opaque flints, and 3 parts of copper fillings, strongly heated together for 2 hours, gave a substance exactly similar to the blue pigment of the ancients, and which, when powdered, produced a fine deep blue color. The ceruleum has the advantage of remaining unaltered even when the painting is exposed to the actions of the air and sun. There is reason to suspect, from what Vitruvius and Pliny say, that glass rendered blue by means of cobalt constituted the basis of some of the blue pigments of the ancients. But all those examined by Davy consisted of glass tinged blue by copper, without any trace of cobalt whatever. 4. Green paints. All the green paints examined by Davy proved to be carbonates of copper, more or less mixed with carbonate of lime. I have already mentioned that verdigris was known to the ancients. It was no doubt employed by them as a pigment, though it is not probable that the acetic acid would be able to withstand the action of the atmosphere for a couple of thousand years. 5. Purple paints. Davy ascertained that the coloring matter of the ancient purple was combustible. It did not give out the smell of ammonia, at least perceptibly. There is little doubt that it was the purpurissum of the ancients, or a clay colored by means of the purple of the boxinum employed by the Syrians in the celebrated purple dye. 6. Black and brown paints. The black paints were lamp black. The browns were some of them ochres and some of them oxides of manganese. 7. White paints. All the ancient white paints examined by Davy were carbonate of lime. We know from Pliny that white lead was employed by the ancients as a pigment, but it might probably become altered in its nature by long continued exposure to the weather. Chapter 3. Glass. It is admitted by some that the word which in our English Bible is translated crystal means glass. In the following passage of Job, the gold and the crystal cannot equal it. Now, although the exact time when Job was written is not known, it is admitted on all hands to be one of the oldest of the books contained in the Old Testament. There are strong reasons for believing that it existed before the time of Moses, and some go so far as to affirm that there are several allusions to it in the writings of Moses. If therefore glass were known when the book of Job was written, it is obvious that the discovery of it preceded the commencement of history. But even though the word used in Job should not refer to glass, there can be no doubt that it was known at a very early period, for glass beads are frequently found on the Egyptian mummies, and they are known to have been embalmed at a very remote period. The first Greek author who uses the word glass, hylos, is Aristophanes, in his Comedy of the Clouds, Act 2, Scene 1. In the ridiculous dialogue between Socrates and Strepsiades, the latter announces a method which had occurred to him to pay his debts. You know, says he, the beautiful transparent stone used for kindling fire? Do you mean glass, Ton Hylan? Replied Socrates. I do, was the answer. He then describes how he would destroy the writings by means of it, and thus defraud his creditors. Now this comedy was acted about 423 years before the beginning of the Christian era. The story related by Pliny respecting the discovery of this beautiful and important substance is well known. Some Phoenician merchants in a ship loaded with carbonate of soda from Egypt stopped and went ashore on the banks of the river Belus. Having nothing to support their kettles, while they were dressing their food, they employed lumps of carbonate of soda for that purpose. The fire was strong enough to fuse some of this soda and to unite it with the fine sand of the river Belus. The consequence of this was the formation of glass. Whether this story be entitled to credit or not, it is clear that the discovery must have originated in some such accident. Pliny's account of the manufacture of glass, like his account of every other manufacture, is very imperfect, but we see from it that in his time they were in the habit of making colored glasses, that colorless glasses were most highly prized, and that glass was rendered colorless then as it is at present by the addition of a certain quantity of oxide of manganese. Colorless glass was very high priced in Pliny's time. He relates that for 2 moderate-sized colorless drinking glasses the Emperor Nero paid 6,000 sestertii, which is equivalent to 25 lira of our money. Pliny relates the story of the man who brought a vessel of malleable glass to the Emperor Tiberius, and who, after dimpling it by dashing it against the floor, restored it to its original shape and beauty by means of a hammer. Tiberius, as a reward for this important discovery, ordered the artist to be executed, in order, as he alleged, to prevent gold and silver from becoming useless. But though Pliny relates this story, it is evident that he does not give credit to it, nor does it deserve credit. We can assign no reason why malleable substances may not be transparent, but all of them hitherto known are opaque. Chloride of silver, chloride of lead, and iron constitute no exception, for they are not malleable, though by peculiar contrivances they may be extended, and their transparency is very imperfect. Many specimens of the colored glasses made by the ancients still remain, particularly the beads employed as ornaments to the Egyptian mummies. Of these ancient glasses, several have been examined chemically by Klaproth, Hatchett, and some other individuals, in order to ascertain the substance employed to give color to the glass. The following are the facts that have been ascertained. 1. Red glass. This glass was opaque and of lively copper-red color. It was probably the kind of red glass to which Pliny gave the name of hematinon. Klaproth analyzed it and obtained from 100 grains of it the following constituents: silica 71, oxide of lead 10, oxide of copper 7.5, oxide of iron 1, alumina 2.5, lime 1.5, total 93.5. No doubt the deficiency was owing to the presence of an alkali. From this analysis we see that the coloring matter of this glass was red oxide of copper. 2. Green glass. The color was light verdigris green, and the glass, like the preceding, was opaque. The constituents from 100 grains were silica 65, black oxide of copper 10, oxide of lead 7.5, oxide of iron 3.5, lime 6.5, alumina 5.5, total 98.0. Thus it appears that both the red and green glass are composed of the same ingredients, though in different proportion. Both owe their color to copper. The red glass is colored by the red oxide of that metal, the green by the black oxide, which forms green-colored compounds with various acids, particularly with carbonic acid and with silica. 3. Blue glass. The variety analyzed by Klaproth had a sapphire blue color and was only translucent on the edges. The constituents from 100 grain of it were silica 81.5, oxide of iron 9.5, alumina 1.5, oxide of copper 0.5, lime 0.25, total 93.25. From this analysis, it appears that the coloring matter of this glass was oxide of iron. It was therefore analogous to the lapis lazuli, or ultramarine, in its nature. Davy, as has been formerly noticed, found another blue glass or frit colored by means of copper, and he showed that the blue paint of the ancients was often made from this glass, simply by grinding it to powder. Klaproth could find no cobalt in the blue glass which he examined, but Davy found the transparent blue glass vessels, which are along with the vases, and the tombs of Magna Graecia, tinged with cobalt, and he found cobalt in all the transparent ancient blue glasses with which Mr. Millinen supplied him. The mere fusion of these glasses were alkali, and subsequent digestion of the product with muriatic acid was sufficient to produce a sympathetic ink from them. The transparent blue beads which occasionally adorn the Egyptian mummies have also been examined and found colored by cobalt. The opaque glass beads are all tinged by means of oxide of copper. It is probable from this that all the transparent blue glasses of the ancients were colored by cobalt, yet we find no allusion to cobalt in any of the ancient authors. Theophrastus says that copper (chalcus) was used to give glass a fine color. Is it not likely that the impure oxide of cobalt, in the state in which they used it, was confounded by them? (chalcus). Chapter 4. Vasa Murhina. The Romans obtained from the East, and particularly from Egypt, a set of vessels which they distinguished by the name of vasa murrhina, and which were held by them in very high estimation. They were never larger than to be capable of containing from about 36 to 40 cubic inches. One of the largest size cost, in the time of Pliny, about 7,000 lira. Nero actually gave for one 3,000 lira. They began to be known in Rome about the latter days of the Republic. The first 6 ever seen in Rome were sent by Pompey from the treasures of Mithridates. They were deposited in the temple of Jupiter in the Capitol. Augustus, after the battle of Actium, brought one of these vessels from Egypt and dedicated it also to the gods. In Nero's time they began to be used by private persons, and were so much coveted that Petronius, the favorite of that tyrant, being ordered for execution, and conceiving that his death was owing to a wish of Nero to get possession of a vessel of this kind which he had, broke the vessel in pieces in order to prevent Nero from gaining his object. There appear to have been 2 kinds of these vasa murrhina, those that came from Asia and those that were made in Egypt. The latter were much more common and much lower priced than the former, as appears from various passages in Marital and Propertius. Many attempts have been made, and much learning displayed by the moderns to determine the nature of these celebrated vessels, but in general these attempts were made by individuals too little acquainted with chemistry and with natural history in general to qualify them for researches of so difficult a nature. Some will have it that they consisted of a kind of a gum, others that they were made of glass, others of a particular kind of shell. Cardan and Scaliger assure us that they were porcelain vessels, and this opinion was adopted likewise by Whitaker, who supported it with his usual violence and arrogance. Many conceive them to have been made of some precious stone, some that they were of obsidian. Count the Walthium thinks that they were made of the Chinese agalmatolite, or figure stone, and Dr. Hager conceives that they were made from the Chinese stone Yu. Bruckmann was of the opinion that these vessels were made of sardonyx, and the Abbe Winkelmann joins him in the same conclusion. Pliny informs us that these vasa murrhina were formed from a species of stone dug out of the earth in Parthia, and especially in Carmenia, and also in other places but little known. They must have been very abundant at Rome in the time of Nero, for Pliny informs us that a man of consular rank, famous for his collection of vasa murrhina, having died, Nero forcibly deprived his children of these vessels, and they were so numerous that they filled the whole inside a theatre, which Nero hoped to have seen filled with Romans when he came to it to sing in public. It is clear that the value of these vessels depended on their size. Small vessels bore but a small price, while that of large vessels was very high. This shows us that it must have been difficult to procure a block of the stone out of which they were cut, of a size sufficiently great to make a large vessel. These vessels were so soft that an impression might be made upon them with the teeth, for Pliny relates the story of a man of consular rank, who drank out of one, and was so enamored with it that he bit pieces out of the lip of the cup. Potavit exio ante hos consularis, ob emorem abraso aegis margin. And what is singular, the value of the cup, so far from being injured by this abrasure, was augmented. Utamen injuria illa pretium augurat. Nequae est hodie, murini, alterios, prastantior indicatora. It is clear from this that the matter of these vessels was neither rock, crystal, agate, nor any precious stone whatever, all of which are too hard to admit of an impression from the teeth of a man. The luster was vitreous, to such a degree that the name Vertrium murinum was given to the artificial fabric in Egypt. The splendor was not very great, for Pliny observes, splendor his, sine viribus nitric viribus quam splendor. The colors, from their depth and richness, were what gave these vessels their value and excited admiration. The principal colors were purple and white, disposed in undulating bands, and usually separated by a third band, in which the two colors being mixed, assume the tint of flame. Sed in praecio veritas colorum, sub in circa magentibus, si maculis in purpuram. Candorimque et tertium ex utraci ingestum, velu per transitum coloris, purpuro rubescente, aut lacticandescente. Perfect transparency was considered as a defect. They were merely translucent. This we learn not merely from Pliny, but from the following epigram of Martial. Eminis bibibus, vitru tumura, pontice quere, pruda perspicus, nidua vina calix. Some specimens, and they were the most valued, exhibited a play of color like the rainbow. Pliny says they were very commonly spotted with salas veruxicae, non eminentes, sedut in corpore, etiam plurumque sessilis. This, no doubt, refers to foreign bodies such as grains of pyrites, antimony galena, and C. period, which were often scattered through the substances of which the vessels were made. Such are all the facts respecting the vasa murrhina to be found in the writings of the ancients. They all apply to fluor spar and to nothing else, but to it they apply so accurately as to leave little doubt that they were in reality vessels of fluor spar, similar to those at present made in Derbyshire. The artificial vasa murrhina made at Thebes, in Egypt, were doubtless of glass, colored to imitate fluorspar as much as possible, and having the semi-transparency which distinguishes that mineral, the imitations being imperfect. These factitious vessels were not much prized nor sought after by the Romans. They were rather distributed among the Arabians and Ethiopians, who were supplied with glass from Egypt. Rock crystal is compared by Pliny with the stone from which the vasa murrhina were made. The former, in his opinion, had been coagulated by cold, the latter by heat. Though the ancients, as we have seen, were acquainted with the method of coloring glass, yet they prized colorless glass highest on account of its resemblance to rock crystal. Cups of it in Pliny's time had supplanted those of silver and gold. Nero gave for a crystal cup 150,000 sesterti, or 625 lira. End of section 9. Section 10 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Your reader is Rosie Roberts from California. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 2 of the Chemical Knowledge Possessed by the Ancients. Part 5. Dyeing and Calico Printing. Very little has been handed down by the ancients respecting the process of dyeing. It is evident from Pliny that they were very acquainted with madder, and that preparations of iron were used in the black dyes. The most celebrated dye of all, the purple, was discovered by the Tyrians about 15 centuries before the Christian era. This color was given by various kinds of shellfish which inhabit the Mediterranean. Pliny divides them into two genera. The first, comprehending the smaller species, he called Buccinum, from this resemblance to a hunting horn. The second included those called Purpura. Fabius Columna thinks that these were distinguished also by the name of Morax. These shellfish yielded liquor of different shades of color, and they were often mixed in various proportions to produce particular shades of color. 1 or at most 2 drops of this liquor were obtained from each fish by extracting and opening a little reservoir placed in the throat. To avoid this trouble, the smaller species were gently bruised whole in a mortar. This was also frequently done with the large, though the other liquids of the fish must have in some degree injured the color. The liquor, when extracted, was mixed with a considerable quantity of salt to keep it from putrefying. It was then diluted with 5 or 6 times as much water, and kept moderately hot in leaden or tin vessels for 8 or 10 days, during which the liquor was often skimmed to separate all the impurities. After this, the wool to be dyed, being first well washed, was immersed and kept therein for 5 hours, then taken out, cooled, and again immersed, and continued in the liquor till all the color was exhausted. To produce particular shades of color, carbonate of soda, urine, and marine plant called fucus was occasionally added. One of these colors was a very dark reddish violet. Nigrantus rosei color, sublucent. But the most esteemed, and that in which the Tyrians particularly excelled, resembled coagulated blood. Laus e summa incolere sanguinis concreti nigracens aspectu indemque suspectu refulgens. Pliny says that the Tyrians first dyed their wool in their liquor of the purpura, and afterwards in that of the buccinum, and it is obvious from Moses that this purple was known to the Egyptians in his time. Wool, which had received this double Tyrian dye, open parenthesis, diabatha, close parenthesis, was so very costly that, in the reign of Augustus, it sold for about 36 lira the pound. But lest these should not be sufficient to exclude all from the use of it but those invested with the very highest dignities of the state, laws were made inflicting severe penalties, and even death, upon all who should presume to wear it under the dignity of an emperor. The art of dyeing this color came at length to be practised by a few individuals, only appointed by the emperors, and having been interrupted about the beginning of the 12th century, all knowledge of it died away, and during several ages this celebrated dye was considered and lamented as an irrecoverable loss. How it was afterwards recovered and made known by Mr. Cole of Bristol, M. Juicy, M. Reamer, and M. Duhamel would lead us too far from our present object. Were we to relate it, those who are interested in the subject will find an historical detail in Bancroft's work on permanent colors, just referred to. There is reason to suspect that the Hebrew word translated fine linen in the Old Testament, and so celebrated as a production of Egypt, was in reality cotton, and not linen. From a curious passage in Pliny, there is reason to believe that the Egyptians in his time, and probably long before, were acquainted with the method of calico printing, such as is still practiced in India and the East. The following is a literal translation of the passage in question. There exists in Egypt a wonderful method of dyeing. The white cloth is stained in various places, not with dye stuffs, but with substances which have the property of absorbing, open parentheses, fixing, close parentheses, colors. These applications are not visible upon the cloth, but when they are dipped into a hot cauldron of the dye, they are drawn out an instant after dyed. The remarkable circumstance is, that though there be only one dye in the vat, yet different colors appear upon the cloth, nor can the color be afterwards removed. It is evident enough that these substances applied were different mordants which served to fix the dye upon the cloth. The nature of these mordants cannot be discovered, as nothing specific seems to have been known to Pliny. The modern mordants are solutions of alumina, of the oxide of tin, oxide of iron, oxide of lead, and C. And doubtless these, or something equivalent to these, were the substances employed by the ancients. The purple dye required no mordant. It fixed itself to the cloth in consequence of the chemical affinity which existed between them. Whether indigo was used by the ancients as a dye does not appear, but there can be no doubt at least that its use was known to the Indians at a very remote period. From these facts, few as they are, there can be little doubt that dyeing, and even calico printing, had made considerable progress among the ancients. And this could not have taken place without a considerable knowledge of coloring matters, and of the mordant by which these coloring matters were fixed. These facts, however, were probably but imperfectly understood, and could not be the means of furnishing the ancients with any accurate chemical knowledge. 6. Soap. Soap, which constitutes so important and indispensable an article in the domestic economy of the moderns, was quite unknown to the ancient inhabitants of Asia, and even of Greece. No allusion to it occurs in the Old Testament. In Homer, we find Nausicaa, the daughter of the king of the Phoenicians, using nothing but water to wash her nuptial garments. They seek the cisterns, where Phoenicians' dames wash their fair garments in the limped streams, where gathering into depth from falling rills, the lucid wave a spacious basin fills. The mules unharnessed range beside the main, or crop the verdant herbage of the plain. Then immoless the royal robes they lave, and plunge the vestures in the cleansing wave. Odyssey 6:199. We find in some of the comic poets that the Greeks were in the habit of adding wood ashes to water to make it a better detergent. Wood ashes contain a certain portion of carbonate of potash, which of course would answer as a detergent, though from its caustic qualities it would be injurious to the hand of the washerwoman. There is no evidence that the carbonate of soda, the nitrum of the ancients, was ever used as a detergent. This is the more surprising, because we know from Pliny that it was employed in dyeing, and one cannot see how a solution of it could be employed by the dyers in the processes, without discovering that it acted powerfully as a detergent. The word soap, open parenthesis, sapo, close parenthesis, occurs first in Pliny. He informs us that it was an invention of the Gauls, who employed it to render their hair shining, that it was a compound of wood ashes and tallow, that there were two kinds of it, hard and soft, open parenthesis, species et liquidus, close parenthesis, and that the best kind was made of the ashes of the beech and the fat of goats. Among the Germans it was more employed by the men than the women. It is curious that no allusion whatever is made by Pliny to the use of soap as a detergent. Shall we conclude from this that the most important of all the uses of soap was unknown to the ancients? It was employed by the ancients as a pomatum, and, during the early part of the government of the emperors, it was imported into Rome from Germany as a pomatum for the young Roman boys. Beckmann is of opinion that the Latin word sapo is derived from the old German word sepe, a word still employed by the common people of Scotland. It is well known that the state of soap depends upon the alkali employed in making it. Soda constitutes a hard soap, and potash a soft soap. The ancients, being ignorant of the difference between the two alkalis, and using wood ashes in the preparation of it, doubtless formed soft soap. The addition of some common salt during the boiling of the soap would convert the soft into hard soap, as Pliny informs us that the ancients were acquainted both with hard and soft soap. The addition of some common salt during the boiling of the soap would convert the soft into hard soap, as Pliny informs us that the ancients were acquainted both with hard and soft soap. It is clear that they must have followed some such process. 7. Starch. The manufacture of starch was known to the ancients. Pliny informs us that it was made from wheat and from siligo, which was probably a variety of subspecies of wheat. The invention of starch is ascribed by Pliny to the inhabitants of the island of Chio, where in his time the best starch was still made. Pliny's description of the method employed by the ancients of making starch is tolerably exact. Next to the China starch, that of Crete was most celebrated, and next to it was the Egyptian. The qualities of starch were judged by the weight, the lightest being always reckoned the best. 8. Beer. That the ancients were acquainted with wine is universally known. This knowledge must have been nearly coeval with the origin of society, for we are informed in Genesis that Noah, after the flood, planted a vineyard and made wine, and got intoxicated by drinking the liquid which he had manufactured. Beer also is very old manufacture. It was in common use among the Egyptians in the time of Herodotus, who informs us that they made use of a kind of wine made from barley, because no vines grew in their country. Tacitus informs us that in his time it was the drink of the Germans. Pliny informs us that it was made by the Gauls and by other nations. He gives it the name of cerevisia or cervicia, the name obviously alluding to the grain from which it was made. But though the ancients seem acquainted with both wine and beer, there is no evidence of their having ever subjected these liquids to distillation, and of having collected the products. This would have furnished them with ardent spirit or alcohol, of which there is every reason to believe they were entirely ignorant. Indeed, the method employed by Dioscorides to obtain mercury from cinnabar is a sufficient proof that the true process of distillation was unknown to them. He mixed cinnabar with iron fillings, put the mixture into a pot, to the top of which a cover of stoneware was luted. Heat was applied to the pot, and when the process was at an end, the mercury was found adhering to the inside of the cover. Had they been aware of the method of distilling the quicksilver ore into a receiver, this imperfect mode of collecting only a small portion of the quicksilver, separated from the cinnabar, would never have been practiced. Besides, there is not the smallest allusion to ardent spirits, either in the writings of the poets, historians, naturalists, or medical men of ancient Greece, a circumstance not to be accounted for had ardent spirits been known, and applied even to 1/10 of the uses to which they are put by the moderns. 9. Stoneware. The manufacture of stoneware vessel was known at a very early period of society. Frequent allusions to the potter's wheel occur in the Old Testament, showing that the manufacture must have been familiar to the Jewish nation. The porcelain of the Chinese boasts of a very high antiquity indeed. We cannot doubt that the process of the ancients were similar to those of the moderns, though I am not aware of any tolerably accurate account of them in any ancient author whatever. Molds of plaster of Paris were used by the ancients to take casts precisely as at present. The sand of Puzzuli was used by the Romans, as it is by the moderns, to form a mortar capable of hardening under water. Pliny gives us some idea of the Romans' bricks, which are known to have been of an excellent quality. There were 3 sizes of bricks used by the Romans. 1 Lydian, which were 1½ foot long and 1 foot broad. 2 Tetradoron, which was a square of 16 inches each side. 3 Pentadoron, which was a square, each side of which was 20 inches long. Doron signifies the palm of the hand. Of course it was equivalent to 4 inches. 10. Precious stones and minerals. Pliny has given a pretty detailed description of the precious stones of the ancients, but it is not very easy to determine the specific minerals to which he alludes. 1. The description of the diamond is tolerably precise. It was found in Ethiopia, India, Arabia, and Macedonia, but the Macedonian diamond, as well as the adamas, cyprus, and siderites, were obviously not diamonds but soft stones. 2. The emerald of the ancients, open a parenthesis, smaragdus, close a parenthesis, must have varied in its nature. It was a green, transparent, hard stone, and as color was the criterion by which the ancients distinguished minerals and divided them into species, it is obvious that very different minerals must have been confounded together under the name of emerald. Sapphire, beryl, doubtless fluor, spar when green, and probably even serpentine, nephrite, and some ores of copper seem to have occasionally got the same name. There is no reason to believe that the emerald of the moderns was known before the discovery of America. At least it has been only found in modern times in America. Some of the emeralds described by Pliny as losing their color by exposure to the sun must have been fluorspars. There is a remarkably deep and beautiful green fluorspar met with some years ago in the country of Durham, in one of the Weardale mines, that possesses this property. The emeralds of the ancients were of such a size, open a parenthesis, 13½ feet, large enough to be cut into a pillar, close a parenthesis, that we can consider them in no other light than as a species of rock. 3. Topaz of the ancients had a green color, which is never the case with the modern topaz. It was found in the island Topazius in the Red Sea. It is generally supposed to have been the chrysolite of the moderns, but Pliny mentions a statue of it 6 feet long. Now, chrysolite never occurs in such large masses. Bruce mentions a green substance in an emerald island in the Red Sea, not harder than glass. Might not this be the emerald of the ancients? 4. Calais, from the locality and color, was probably the Persian turquoise, as it is generally supposed to be. 5. Whether the Preface and Chrysopraeus of Pliny were the modern stones to which the names are given, we have no means of determining. It is generally supposed that they are, and we have no evidence to the contrary. 6. The chrysolite of Pliny is supposed to be our topaz, but we have no other evidence of this than the opinion of M. du Thames. 7. Asteria of Pliny is supposed by Saussure to be our sapphire. The luster described by Pliny agrees with this opinion. The stone is said to have been very hard and colorless. Opalus seems to have been our opal. It is called, Pliny says, Paderus by many, on account of its beauty. The Indians called it sanguinon. 9. Obsidian was the same as the mineral to which we give that name. It was so called because a Roman named Obsidianus first brought it from Egypt. I have a piece of obsidian which the late Mr. Salt brought from the locality specified by Pliny, and which possesses all the characters of that mineral in its purest state. 10. Sarda was the name of carnelian, so called because it was first found near Sardis. The sardonyx was also another name for carnelian. 11. Onyx was a name sometimes given to a rock, gypsum. Sometimes it was a light-colored chalcedony. The Latin name for chalcedony was Carchedonus, so called because Carthage was the place where this mineral was exposed to sale. The Greek name Carthage was Capo, open a parenthesis, Carchedon, close parentheses. 12. Carbunculus was the garnet, and anthrax was a name for another variety of the same mineral. 13. The oriental amethyst of Pliny was probably a sapphire. The fourth species of amethyst described by Pliny seems to have been our amethyst. Pliny derives the name from a open parentheses, myth, close parentheses, wine, because it has not quite the color of wine. But the common derivation is from a and avon, to intoxicate, because it was used as an amulet to prevent intoxication. 14. The sapphire is described by Pliny as always opaque and as unfit for engraving on. We do not know what it was. 15. The hyacinth of Pliny is equally unknown. From its name, it was obviously of a blue color. Our hyacinth has a reddish-brown color and a great deal of hardness and luster. 16. The cyanus of Pliny may have been our cyanite. 17. Astrios agrees very well, as far as the description of Pliny goes, with the variety of feldspar called adularia. 18. Belioculus seems to have been our cat's eye. 19. Lychnites was a violet-colored stone, which became electric by heat. Unless it was a blue tourmaline, I do not know what it could be. 20. The jasper of the ancients was probably the same as ours. 21. Molochites may have been our malachite. The name comes from the Greek word moloch, mallow, or marshmallow. 22. Pliny considers amber as the juice of a tree concreted into a solid form. The largest piece of it that he had ever seen weighed 13 pounds, Roman weight, which is nearly equivalent to 9 3/4 pounds. Avoirdupois, Indian amber of which he speaks, was probably copal, or some transparent resin. It may be dyed, he says, by means of anchusa and the fat of kids. 23. Lapis specularis was foliated sulfate of lime or selenite. 24. Pyrites had the same meaning amongst the ancients that it has among the moderns, at least as far as iron pyrites or bisulphuret of iron is concerned. Pliny describes two kinds of pyrites, namely the white, open parentheses, arsenical pyrites, close parentheses, and the yellow, open parentheses, iron pyrites, close parentheses. It was used for striking fire with steel in order to kindle tinder, hence the name pyrites or firestone. 25. Gagates, from the account given of it by Pliny, was obviously pit coal or jet. 26. Marble had the same meaning among the ancients that it has among the moderns. It was sawed by the ancients into slabs, and the action of the saw was facilitated by a sand brought for the purpose from Ethiopia and the Isle of Naxos. It is obvious that the sand was powdered corundum or emery. 27. Crater was a name applied by the ancients not only to chalk but to white clay. 28. Melinum was an oxide of iron. Pliny gives a list of 151 species of stones in the order of the alphabet. Very few of the minerals contained in this list can be made out. He gives also a list of 52 species of stones whose names are derived from a fancied resemblance which the stones are supposed to bear to certain parts of animals. Of these, also, very few can be made out. End of section 10. Your reader has been Rosie Roberts from California.
Section 11 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. The History of Chemistry by Thomas Thompson. Volume 1, Chapter 2, of the Chemical Knowledge Possessed by the Ancients, Part 6. 11. Miscellaneous Observations. The ancients seem to have been ignorant of the nature and properties of air and of all gaseous bodies. Pliny's account of air consists of a single sentence: Aer densatur nubibus, furit procedes. Air is condensed in clouds, it rages in storms. Nor is his description of water much more complete, since it consists only of the following phrases: Aquae sibicunt in imbres, regescunt in grandines, tumescunt in fluctus, precipitantur in torrentes. Water falls in showers, congeals in hail, swells in waves, and rushes down in torrents.
In the 38th chapter of the second book,
Indeed, he professes to treat of air, but the chapter contains merely an enumeration of meteorological phenomena, without once touching upon the nature and properties of air. Pliny, with all the philosophers of antiquity, admitted the existence of the four elements: fire, air, water, and earth. But though he enumerates these in the 5th chapter of his first book, he never attempts to explain their nature or properties. Earth, among the ancients, had two meanings, namely, the planet on which we live, and the soil upon which vegetables grow. These two meanings still exist in common language. The meaning afterward given to the term earth by the chemists did not exist in the days of Pliny, or at least was unknown to him. A sufficient proof that chemistry, in his time, had made no progress as a science, for some notions respecting the properties and constituents
of those supposed four elements
must have constituted the very foundation of scientific chemistry. The ancients were acquainted with none of the acids, which at present constitute so numerous a tribe, except vinegar or acetic acid, and even this acid was not known to them in a state of purity. They knew none of the saline bases, except lime, soda, and potash, and these very imperfectly. Of course, the whole tribe of salts was unknown to them, except a very few, which they found ready formed in the earth, or which they succeeded in forming by the action of vinegar on lead and copper. Hence all that extensive and most important branch of chemistry, consisting of the combinations of the acids and bases, on which scientific chemistry mainly depends, must have been unknown to them. Sulphur, occurring native in large quantities, and being remarkable for its easy combustibility and its disagreeable smell when burning, was known in the very earliest ages. Pliny describes 4 kinds of sulphur, differing from each other probably merely in their purity. These were: 1. Sulphur vivum, or apyron. It was dug out of the earth solid, and was doubtless pure, or nearly so. It alone was used in medicine. 2. Gleba, used only by fullers. 3. Egula, used also by fullers. Pliny says it renders woolen stuffs white and soft. It is obvious from this that the ancients knew the method of bleaching flannel by the fumes of sulphur, as practised by the moderns. 4. The 4th kind was used only for sulphuring matches. Sulphur, in Pliny's time, was found native in the Aeolian Islands and in Campania. It is curious he never mentioned Sicily, whence the great supply is drawn for modern manufacture. In medicine, it seems to have been used only externally by the ancients. It was considered as excellent for removing eruptions. It was also used for fumigating. The word alumen, which we translate alum, occurs often in Pliny, and is the same substance which the Greeks distinguished by the name of stypteria. It is described pretty minutely by Dioscorides and also by Pliny. It was obviously a natural production, dug out of the earth, and consequently quite different from our alum, with which the ancients were unacquainted. Dioscorides says it was found abundantly in Egypt, that it was of various kinds, but that the slaty variety was the best. He mentions also many other localities. He says that, for medical purposes, the most valued of all the varieties of alumen were the slaty, the round, and the liquid. The slaty alumen is very white, has an exceedingly astringent taste, a strong smell, is free from stony concretions, and gradually cracks and emits long capillary crystals from these rifts, on which account it is sometimes called trichytes. This description obviously applies to a kind of slate clay, which probably contained pyrites mixed with it of the decomposing kind. The capillary crystals were probably similar to those crystals at present called hair salt by mineralogists, which exude pretty abundantly from the shale of coal beds when it has been long exposed to the air. Hair salt differs very much in its nature. Klaproth ascertained by analysis that the hair salt from the quicksilver mines in Idria is sulfate of magnesia
mixed with a small quantity of sulfate of iron.
The hair salt from the abandoned coal pits in the neighborhood of Glasgow is a double salt, composed of sulfate of alumina and sulfate of iron, in definite proportions, the composition being 1 atom protosulfate of iron, 1½ atom sulfate of alumina, 15 atoms water. I suspect strongly that the capillary crystals from the schistose alumen of Dioscorides were nearly of the same nature. From Pliny's account of the uses to which alumen was applied, it is quite obvious that it must have varied very much in its nature. Alumen nigrum was used to strike a black color, and must therefore have contained iron. It was doubtless an impure native sulfate of iron, similar to many native productions of the same nature still met with in various parts of the world, but not employed, their use having been superseded by various artificial salts, more definite in their nature, and consequently more certain in their application, and, at the same time, cheaper and more abundant than the native. The alumen employed as a mordant by the dyers must have been a sulfate of alumina more or less pure. At least it must have been free from all sulfate of iron, which would have affected the color of the cloth and prevented the dyer from accomplishing its object. What the alumen rotundum was is not easily conjectured. Dioscorides says that it was sometimes made artificially, but that artificial alumen rotundum was not much valued. The best, he says, was full of air bubbles, nearly white, and of a very astringent taste. It had a slaty appearance, and was found in Egypt or the island of Melos. The liquid alumen was limpid, milky, of an equal color, free from hard concretions, and having a fiery shade of color. In its nature it was similar to the alumen candidium, must therefore have consisted chiefly at least of sulfate of alumina. Bitumen and naphtha were known to the ancients and used by them to give light instead of oil. They were employed also as external applications in case of disease, and were considered as having the same virtues as sulfur. It is said that the word translated salt in the New Testament, "Ye are the salt of the earth, but if the salt have lost his savor, wherewith shall it be salted?" is henceforth good for nothing, but to be cast out, and trodden under foot of men. It is said that the word salt in this passage refers to asphalt, or bitumen, which was used by the Jews in their sacrifices, and called salt by them. But I have not been able to find satisfactory evidence of the truth of this opinion. It is obvious from the context that the word translated salt could not have had that meaning among the Jews, because salt can never be supposed to lose its savor. Bitumen, while liquid, has a strong taste and smell, which it loses gradually by exposure to the air as it approaches more and more to a solid form. Asphalt was one of the great constituents of the Greek fire. A great bed of it still existing in Albania supplied the Greeks with this substance. Concerning the nature of Greek fire, it is clear that many exaggerated and even fabulous statements have been published. The obvious intention of the Greeks being, probably, to make their invention as much dreaded as possible by their enemies. Nitre was undoubtedly one of the most important of its constituents, though no allusion whatever is made. We do not know when nitrate of potash, the nitre of the moderns, became known in Europe. It was discovered in the East, and was undoubtedly known in China and India before the commencement of the Christian era. The property of nitre, as a supporter of combustion, could not have remained long unknown after the discovery of the salt. The first person who threw a piece of it upon a red-hot coal would observe it. Accordingly, we find that its use in fireworks was known very early in China and India, though its prodigious expansive power, by which it propels bullets with so great and destructive velocity, is a European invention, posterior to the time of Roger Bacon. The word nitre had been applied by the ancients to carbonate of soda, a production of Egypt, where it is still formed from seawater by some unknown process of nature in the marshes near Alexandria. This is evident, not merely from the account given of it by Dioscorides and Pliny, for the following passage from the Old Testament shows it had the same meaning among the Jews. As he that taketh away a garment in cold weather is as vinegar upon nitre, so is he that singeth songs to a heavy heart. Vinegar poured upon saltpetre produces no sensible effect whatever, but when poured upon carbonate of soda, it occasions an effervescence. When saltpetre came to be imported to Europe, it was natural to give it the same name as that applied to carbonate of soda, to which both in taste and appearance it bore some faint resemblance. Saltpetre, possessing much more striking properties than carbonate of soda, much more attention was drawn to it, and it gradually fixed upon itself the term nitre, at first applied to a different salt. When this change of nomenclature took place does not appear, but it was completed before the time of Roger Bacon, who always applies the term nitrum to our nitrate of potash and never to carbonate of soda. In the preceding history of the chemical facts known to the ancients, I have taken no notice of a well-known story related of Cleopatra. This magnificent and profligate queen boasted to Antony that she would herself consume 1,000,000 of sestertii at a supper. Antony smiled at the proposal, and doubted the possibility of her performing it. Next evening a magnificent entertainment was provided, which Antony, as usual, was present, and expressed his opinion that the cost of the feast, magnificent as it was, fell far short of the sum specified by the queen. She requested him to defer computing till the dessert was finished. A vessel filled with vinegar was placed before her, in which she threw 2 pearls, the finest in the world, and which were valued at 10 millions of sestertii. These pearls were dissolved by the vinegar, and the liquid was immediately drunk by the queen. Thus she made good her boast, and destroyed the 2 finest pearls in the world. This story, supposing it true, shows that Cleopatra was aware that vinegar has the property of dissolving pearls, but not that she knew the nature of these beautiful productions of nature. We now know that pearls consist essentially of carbonate of lime, and that the beauty is owing to the thin concentric laminae of which they are composed. Nor have I taken any notice of lime, with which the ancients were well acquainted, and which they applied to most of the uses to which the moderns put it. Thus it constituted the base of the Roman mortar, which is known to have been excellent. They employed it also as a manure for the fields, as the moderns do. It was known to have a corrosive nature when taken internally, but was much employed by the ancients externally, and in various ways as an application to ulcers. Whether they knew its solubility in water does not appear, though from the circumstance of its being used for making mortar, this fact could hardly escape them. These facts, though of great importance, could scarcely be applied to the rearing of a chemical structure, as the ancients could have no notion of the action of acids upon lime, or of the numerous salts which it is capable of forming. Phenomena which must have remained unknown till the discovery of the acids enabled experimenters to try their effects upon limestone and quicklime. Not even a conjecture appears in any ancient writer that I have looked into about the difference between quicklime and limestone. This difference is so great that it must have been remarked by them, yet nobody seems ever to have thought of attempting to account for it. Even the method of burning or calcining lime is not described by Pliny, though there can be no doubt that the ancients were acquainted with it. Nor have I taken any notice of leather or the method of tanning it. There are so many allusions to leather and its uses by the ancient poets and historians that the acquaintance of the ancients with it is put out of doubt. But, so far as I know, there is no description of the process of tanning in any ancient author whatever. End of section 11. Recording by April Walters.
Section number 12 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rosehip. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 3, Chemistry of the Arabians, Part 1. Hitherto I have spoken of alchemy, or of the chemical manufactures of the ancients. The people to whom scientific chemistry owes its origin are the Arabians. Not that they prosecuted scientific chemistry themselves, but they were the first persons who attempted to form chemical medicines. This they did by mixing various bodies with each other and applying heat to the mixture in various ways. This led to the discovery of some of the mineral acids. These they applied to the metals, etc., and ascertained the effects produced upon that most important class of bodies. Thus the Arabians began those researches which led gradually to the formation of scientific chemistry. We must therefore endeavour to ascertain the chemical facts for which we are indebted to the Arabians. When Mahomet first delivered his dogmas to his countrymen, they were not altogether barbarous. Possessed of a copious and expressive language, and inhabiting a burning climate, their imaginations were lively and their passions violent. Poetry and fiction were cultivated by them with ardour and with considerable success. But science and inductive philosophy had made little or no progress among them. The fatalism introduced by Mahomet and the blind enthusiasm which he inculcated rendered them furious bigots and determined enemies to every kind of intellectual improvement. The rapidity with which they overran Asia, Africa, and even a portion of Europe is universally known. At that period the Western world was sunk into extreme barbarism, and the Greeks, with whom the remains of civilization still lingered, were sadly degenerated from those sages who graced the classic ages. Bent to the earth under the most grinding but turbulent despotism that ever disgraced mankind, and having their understandings sealed up by the most subtle and absurd and uncomprising superstition, all the energy of mind, all the powers of invention, all the industry and talent which distinguished their ancestors had completely forsaken them. Their writers aimed at nothing new or great, and were satisfied with repeating the scientific facts determined by their ancestors. The lamp of science fluttered in its socket, and was on the eve of being extinguished. Nothing good or great could be expected from such a state of society. It was, therefore, wisely determined by Providence that the Mussulman conquerors should overrun the earth, sweep out those miserable governors, and free the wretched inhabitants from the trammels of despotism and superstition. As a despotism not less severe, and a superstition still more gloomy and uncompromising, was substituted in their place, it may seem at first sight that the conquests of the Mahometans brought things into a worse state than they found them. But the listless inactivity, the almost death-like torpor which had frozen the minds of mankind, were effectually roused. The Mussulmans displayed a degree of energy and activity which have few parallels in the history of the world, and after the conquests of the Mahometans were completed, and the caliphs quietly seated upon the greatest and most powerful throne that the world had ever seen, after Almanzor, about the middle of the 8th century, had founded the city of Baghdad, and settled a permanent and flourishing peace, the arts and sciences, which usually accompany such a state of society, began to make their appearance. The Caliph founded an academy at Baghdad, which acquired much celebrity, and gradually raised itself above all the other academies in his dominions. A medical college was established there, with powers to examine all those persons who intended to devote themselves to the medical profession. So many professors and pupils flocked to this celebrated college from all parts of the world, that at one time their number amounted to no fewer than 6,000. Public hospitals and laboratories were established to facilitate a knowledge of diseases and to make the students acquainted with the method of preparing medicines. It was this last establishment, which originated with the caliphs, that gave a first beginning to the science of chemistry. In the 13th century, the Caliph Mostanza re-established the academy and the medical college at Baghdad, for both had fallen into decay and had been replaced by an infinite number of Jewish seminaries. Mostanza gave large salaries to the professors, collected a magnificent library, and established a new school of pharmacy. He was himself often present at the public lectures. The successor of Mostanza was the Caliph Harun al-Rashid, the perpetual hero of the Arabian tales. He not only carried his love for the sciences further than his predecessors, but displayed a liberality and a tolerance for religious opinions which was not quite consistent with Mahometan bigotry and superstition. He drew round him the Syrian Christians, who translated the Greek classics, rewarded them liberally, and appointed them instructors of his Mahometan subjects, especially in medicine and pharmacy. He protected the Christian school of Shondisabur, founded by the Nestorian Christians before the time of Mohammed, and still continuing in a flourishing state. Always surrounded by literary men, he frequently condescended to take a part in their discussions, and not unfrequently, as might have been expected from his rank, came off victorious. The most enlightened of all the caliphs was Al-Mamun, who has rendered his name immortal by his exertions in favour of the sciences. It was during his reign that the Arabian schools came to be thoroughly acquainted with Greek science. He procured the translation of a great number of important works. This conduct inflamed the religious zeal of the faithful, who devoted him to destruction, and to the divine wrath for favouring philosophy, and in that way diminishing the authority of the Koran. Al-Mamun purchased the ancient classics from all quarters, and recommended the care of doing so in a particular manner to his ambassadors at the court of the Greek emperors. To Leo, the philosopher, he made the most advantageous offers to induce him to come to Baghdad, but that philosopher would not listen to his invitation. It was under the auspices of this enlightened prince that the celebrated attempt was made to determine the size of the earth by measuring a degree of the meridian. The result of this attempt it does not belong to this work to relate. Al-Motassem and Motawakkel, who succeeded Al-Mamun, followed his example, favoured the sciences, and extended their protection to men of science who were Christians. Motawakkel re-established the celebrated academy and library of Alexandria, but he acted with more severity than his predecessors with regard to the Christians, who may perhaps have abused the tolerance which they enjoyed. The other vicars of the Prophet in the different Mahometan states followed the fine example set them by Al-Mamun. Already in the 8th century, the sovereigns of Maghreb and the western provinces of Africa showed themselves the zealous friends of the sciences. One of them, called Abdallah ibn Ibadshab, rendered commerce and industry flourishing at Tunis. He himself cultivated poetry, and drew numerous artists and men of science into his state. At Fez and in Morocco the sciences flourished, especially during the reign of the Edrisites, the last of whom, Jahaya, a prince possessed of genius, sweetness, and goodness, changed his court into an academy, and paid attention to those only who had distinguished themselves by their scientific knowledge. But Spain was the most fortunate of all the Mahometan states, and had arrived at such a degree of prosperity both in commerce, manufactures, population, and wealth as is hardly to be credited. The three Abdul-Rahmans and Al-Hakem carried from the 8th to the 10th century the country subject to the Caliph of Cordova to the highest degree of splendor. They protected the sciences, and governed with so much mildness that Spain was probably never so happy under the dominion of any Christian prince. Al-Hakem established at Cordova an academy, which for several ages was the most celebrated in the whole world. All the Christians of Western Europe repaired to this academy in search of information. It contained, in the 10th century, a library of 280,000 volumes. The catalogue of this library filled no less than 44 volumes. Seville, Toledo, and Murcia had likewise their schools of science and their libraries, which retained their celebrity as long as the dominion of the Moors lasted. In the 12th century there were 70 public libraries in that part of Spain which belonged to the Mahometans. Cordova had produced 150 authors, Almeria 52, and Murcia 62. The Mahometan states of the East continued also to favor the sciences. An emir of Iraq, Adad el-Dawla by name, distinguished himself towards the end of the 10th century by the protection which he afforded to men of science. To him almost all the philosophers of the age dedicated their works. Another emir of Iraq, Saif ed-Dawla, established schools at Kufa and at Bussorah, which soon acquired great celebrity. Abu Mansur Baharam established a public library at Firuzabad in Kurdistan, which at its very commencement contained 7,000 volumes. In the 13th century there existed a celebrated school of medicine in Damascus. The Caliph Malek Adel endowed it richly, and was often present at the lectures with a book under his arm. Had the progress of the sciences among the Arabians been proportional to the number of those who cultivated them, we might hail the Saracens as the saviours of literature during the dark and benighted ages of Christianity. But we must acknowledge with regret that notwithstanding the enlightened views of the caliphs, notwithstanding the multiplicity of academies and libraries, and the prodigious number of writers, the sciences received but little improvement from the Arabians. There are very few Arabian writers in whose works we find either philosophical ideas, successful researches, new facts, or great and new and important truths. How, indeed, could such things be expected from a people naturally hostile to mental exertion, professing a religion which stigmatizes all exercise of the judgment as a crime, and weighed down by the heavy yoke of despotism? It was the religion of the Arabians and the despotism of their princes that opposed the greatest obstacles to the progress of the sciences, even during the most flourishing period of their civilization. Fortunately, chemistry was the branch of science least obnoxious to the religious prejudices of the Mahometans. It was in it, therefore, that the greatest improvements were made. Of these improvements it will be requisite now to endeavour to give the reader some idea. Astrology and alchemy they both derived from the Greeks. Neither of them were inconsistent with the tastes of the nation. Neither of them were anathematized by the Mahometan creed, though Islamism prohibited magic and all the arts of divination. Alchemy may have suggested the chemical processes, but the Arabians applied them to the preparation of medicines, and thus opened a new and most copious source of investigation. The chemical writings of the Arabians, which I have had an opportunity of seeing and perusing in a Latin dress, being ignorant of the original language in which they were written, are those of Geber and Avicenna. Geber, whose real name was Abu Musa Shafar al-Soli, was a Sabaean of Haran, in Mesopotamia, and lived during the 8th century. Very little is known respecting the history of this writer, who must be considered as the patriarch of chemistry. Golius, professor of the Oriental languages in the University of Leyden, made a present of Geber's work in manuscript to the public library. He translated it into Latin, and published it in the same city in folio, and afterwards in quarto, under the title of Lapis Philosophorum. It was translated into English by Richard Russell in 1678, under the title of The Works of Geber, the most famous Arabian prince and philosopher. The works of Geber, so far as they appeared in Latin or English, consist of 4 tracts. The first is entitled Of the Investigation or Search of Perfection. The second is entitled Of the Sum of Perfection or of the Perfect Magistery. The third, Of the Invention of Verity or Perfection. And the last, Of Furnaces, with a recapitulation of the author's experiments. The object of Geber's work is to teach the method of making the philosopher's stone, which he distinguishes usually by the name of medicine of the 3rd class. The whole is in general written with so much plainness that we can understand the nature of the substances which he employed, the processes which he followed, and the greater number of the products which he obtained. It is therefore a book of some importance, because it is the oldest chemical treatise in existence, and because it makes us acquainted with the processes followed by the Arabians and the progress which they had made in chemical investigations. I shall therefore lay before the reader the most important facts contained in Geber's work. 1. He considered all the metals as compounds of mercury and sulphur. This opinion did not originate with him. It is evident from what he says that the same notion had been adopted by his predecessors, men whom he speaks of under the title of the Ancients. 2. The metals with which he was acquainted were gold, silver, copper, iron, tin, and lead. These are usually distinguished by him under the names of Sol, Luna, Venus, Mars, Jupiter, and Saturn. Whether these names of the planets were applied to the metals by Geber, or only by his translators, I cannot say, but they were always employed by the alchemists, who never designated the metals by any other appellations. 3. Gold and silver he considered as perfect metals, but the other 4 were imperfect metals. The difference between them depends, in his opinion, partly upon the proportions of mercury and sulphur in each, and partly upon the purity or impurity of the mercury and sulphur which enters into the composition of each. Gold, according to him, is created of the most subtle substance of mercury, and of most clear fixture, and of a small substance of sulphur, clean and of pure redness, fixed, clear, and changed from its own nature, tinged that. And because there happens a diversity in the colours of that sulphur, the yellowness of gold must needs have a like diversity. His evidence that gold consisted chiefly of mercury is the great ease with which mercury dissolves gold. For mercury, in his opinion, dissolves nothing that is not of its own nature. The lustre and splendour of gold is another proof of the great proportion of mercury which it contains. That it is a fixed substance, void of all burning sulphur, he thinks evident by every operation in the fire, for it is neither diminished nor inflamed. His other reasons are not so intelligible. Silver, like gold, is composed of much mercury and a little sulphur, but in the gold the sulphur is red, whereas the sulphur that goes to the formation of silver is white. The sulphur in silver is also clean, fixed, and clear. Silver has a purity short of that of gold, and a more gross inspissation. The proof of this is, that its parts are not so condensed, nor is it so fixed as gold, for it may be diminished by fire, which is not the case with gold. Iron is composed of earthy mercury and earthy sulphur, highly fixed, the latter in by far the greatest quantity. Sulphur, by the work of fixation, more easily destroys the easiness of liquefaction than mercury. Hence the reason why iron is not fusible, as is the case with the other metals. Sulphur not fixed melts sooner than mercury, but fixed sulphur opposes fusion. What contains more fixed sulphur more slowly admits of fusion than what partakes of burning sulphur, which more easily and sooner flows. Copper is composed of sulphur unclean, gross, and fixed as to its greater part, but as to its lesser part not fixed, red and livid, in relation to the whole not overcoming nor overcome and of gross mercury. When copper is exposed to ignition, you may discern a sulphureous flame to arise from it, which is a sign of sulphur not fixed, and the loss of the quantity of it by exhalation through the frequent combustion of it shows that it has fixed sulphur. This last being in abundance occasions the slowness of its fusion and the hardness of its substance. That copper contains red and unclean sulphur united to unclean mercury is, he thinks, evident from its sensible qualities. End of section 12. Section number 13 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rosehip. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 3. Chemistry of the Arabians, Part 2. Tin consists of sulphur of small fixation, white with a whiteness not pure, not overcoming, but overcome, mixed with mercury partly fixed and partly not fixed, white and impure. That this is the constitution of tin he thinks evident, for when calcined it emits a sulphureous stench, which is a sign of sulphur not fixed. It yields no flame, not because the sulphur is fixed, but because it contains a great portion of mercury. In tin there is a twofold sulphur and also a twofold mercury. One sulphur is less fixed, because in calcining it gives out a stench as sulphur. The fixed sulphur continues in the tin after it is calcined. He thinks that the twofold mercury in tin is evident from this, that before calcination it makes a crashing noise when bent, but after it has been thrice calcined, that crashing noise can no longer be perceived. Geber says that if lead be washed with mercury, and after its washing melted in a fire not exceeding the fire of its fusion, a portion of the mercury will remain combined with the lead, and will give it the crashing noise and all the qualities of tin. On the other hand, you may convert tin into lead. By manifold repetition of its calcination, and the administration of fire convenient for its reduction, it is turned into lead. Lead, in Geber's opinion, differs from tin only in having a more unclean substance commixed of the two more gross substances, sulphur and mercury. The sulphur in it is burning and more adhesive to the substance of its own mercury, and it has more of the substance of fixed sulphur in its composition than tin has. Such are the opinions which Geber entertained respecting the composition of the metals. I have been induced to state them as nearly in his own words as possible, and to give the reasons which he has assigned for them, even when his facts were not quite correct, because I thought that this was the most likely way of conveying to the reader an accurate notion of the sentiments of this father of the alchemists, upon the very foundation of the whole doctrine of the transmutation of metals. He was of opinion that all the imperfect metals might be transformed into gold and silver by altering the proportions of the mercury and sulphur of which they are composed, and by changing the nature of the mercury and sulphur so as to make them the same with the mercury and sulphur which constitute gold and silver. The substance capable of producing these important changes he calls sometimes the philosopher's stone, but generally the medicine. He gives the method of preparing this important magistery, as he calls it. But it is not worth while to state his process, because he leaves out several particulars, in order to prevent the foolish from reaping any benefit from his writings, while at the same time those readers who possess the proper degree of sagacity will be able, by studying the different parts of his writings, to divine the nature of the steps which he omits, and thus profit by his researches and explanations. But it will be worth while to notice the most important of his processes, because this will enable us to judge of the state of chemistry in his time. 4. In his book on furnaces, he gives a description of a furnace proper for calcining metals, and from the 14th chapter of the 4th part of the first book of his Sum of Perfection, it is obvious that the method of calcining or oxidizing iron, copper, tin, and lead, and also mercury and arsenic, were familiarly known to him. He gives a description of a furnace for distilling, and a pretty minute account of the glass or stoneware, or metallic aludel and alembic, by means of which the process was conducted. He was in the habit of distilling by surrounding his aludel with hot ashes, to prevent it from being broken. He was acquainted also with the water bath. These processes were familiar to him. The description of the distillation of many bodies occurs in his work, but there is not the least evidence that he was acquainted with ardent spirits. The term spirit occurs frequently in his writings, but it was applied to volatile bodies in general, and in particular to sulphur and white arsenic, which he considered as substances very similar in their properties. Mercury also he considered as a spirit. The method of distilling per descensum, as is practised in the smelting of zinc, was also known to him. He describes an apparatus for the purpose, and gives several examples of such distillations in his writings. He gives also a description of a furnace for melting metals, and mentions the vessels in which such processes were conducted. He was acquainted with crucibles, and even describes the mode of making cupels, nearly similar to those used at present. The process of cupellating gold and silver and purifying them by means of lead is given by him pretty minutely and accurately. He calls it cineritium, or at least that is the term used by his Latin translator. He was in the habit of dissolving salts in water and acetic acid, and even the metals in different menstrua. Of these menstrua he nowhere gives any account, but from our knowledge of the properties of the different metals, and from some processes which he notices, it is easy to perceive what his solvents must have been, namely, the mineral acids which were known to him, and to which there is no allusion whatever in any preceding writer that I have had an opportunity of consulting. Whether Geber was the discoverer of these acids cannot be known, as he nowhere claims the discovery. Indeed, his object was to slur over these acids as much as possible, that their existence, or at least their remarkable properties, might not be suspected by the uninitiated. It was this affectation of secrecy and mystery that has deprived the earliest chemists of that credit and reputation to which they would have been justly entitled, had their discoveries been made known to the public in a plain and intelligible manner. The mode of purifying liquids by filtration, and of separating precipitates from liquids by the same means, was known to Geber. He called the process distillation through a filter. Thus the greater number of chemical processes, such as they were practised almost to the end of the 18th century, were known to Geber. If we compare his works with those of Dioscorides and Pliny, we shall perceive the great progress which chemistry, or rather pharmacy, had made. It is more than probable that these improvements were made by the Arabian physicians, or at least by the physicians who filled the chairs in the medical schools, which were under the protection of the caliphs. For as no notice is taken of these processes by any of the Greek or Roman writers that have come down to us, and as we find them minutely described by the earliest chemical writers among the Arabians, we have no other alternative than to admit that they originated in the East. I shall now state the different chemical substances or preparations which were known to Geber, or which he describes the method of preparing in his works. 1. Common salt. This substance occurring in such abundance in the earth, and being indispensable as a seasoner of food, was known from the earliest ages. But Geber describes the method which he adopted to free it from impurities. It was exposed to a red heat, then dissolved in water, filtered, crystallized by evaporation, and the crystals being exposed to a red heat were put into a close vessel and kept for use. Whether the identity of sal gem, native salt, and common salt was known to Geber is nowhere said. Probably not, as he gives separate directions for purifying each. 2. Geber gives an account of the two fixed alkalis, potash and soda, and gives processes for obtaining them. Potash was obtained by burning cream of tartar in a crucible, dissolving the residue in water, filtering the solution, and evaporating to dryness. This would yield a pure carbonate of potash. Carbonate of soda he calls sagimen vitri, and salt of soda. He mentions plants which yield it when burnt, points out the method of purifying it, and even describes the method of rendering it caustic by means of quicklime. 3. Saltpeter, or nitrate of potash, was known to him, and Geber is the first writer in whom we find an account of this salt. Nothing is said respecting its origin, but there can be little doubt that it came from India, where it was collected, and known long before Europeans were acquainted with it. The knowledge of this salt was probably one great cause of the superiority of the Arabians over Europeans in chemical knowledge, for it enabled them to procure nitric acid, by means of which they dissolved all the metals known in their time, and thus acquired a knowledge of various important saline compounds, which were of considerable importance. There is a process for preparing saltpeter artificially in several of the Latin copies of Geber, though it does not appear in our English translation. The method was to dissolve sagimen vitri, or carbonate of soda, in aqua fortis, to filter and crystallize by evaporation. If this process be genuine, it is obvious that Geber must have been acquainted with nitrate of soda, but I have some doubts about the genuineness of the passage, because the term aqua fortis occurs in it. Now this term occurs nowhere else in Geber's work. Even when he gives the process for procuring nitric acid, he calls it simply water, but observes that it is a water possessed of much virtue, and that it constitutes a precious instrument in the hands of the man who possesses sagacity to use it aright. 4. Sal ammoniac was known to Geber, and seems to have been quite common in his time. There is no evidence that it was known to the Greeks or Romans, as neither Dioscorides nor Pliny make any allusion to it. The word in old books is sometimes sal ammoniac, sometimes sal ammoniac. It is supposed to have been brought originally from the neighbourhood of the temple of Jupiter Ammon, but had this been the case, and had it occurred native, it could scarcely have been unknown to the Romans, under whose dominions that part of Africa fell. In the writings of the alchemists, sal ammoniac is mentioned under the following whimsical names: anima sensibilis, aqua duorum fratrum ex sorore, aquila, lapis aquilinus, cancer, lapis angeli conjungentis, sal lapidum, sal alakoff. Geber not only knew sal ammoniac, but he was aware of its volatility, and gives various processes for subliming it, and uses it frequently to promote the sublimation of other bodies, as of oxides of iron and copper. He gives also a method of procuring it from urine, a liquid which, when allowed to run into putrefaction, is known to yield it in abundance. Sal ammoniac was much used by Geber in his various processes to bring the inferior metals to a state of greater perfection. By adding it or common salt to aqua fortis, he was enabled to dissolve gold, which certainly could not be accomplished in the time of Dioscorides or Pliny. The description, indeed, of Geber's process for dissolving gold is left on purpose in a defective state, but an attentive reader will find no great difficulty in supplying the defects, and thus understanding the whole of the process. 5. Alum, precisely the same as the alum of the moderns, was familiarly known to Geber and employed by him in his processes. The manufacture of this salt, therefore, had been discovered between the time when Pliny composed his Natural History and the 8th century, when Geber wrote, unless we admit that the mode of making it had been known to the Tyrian dyers, but that they had kept the secret so well that no suspicion of its existence was entertained by the Greeks and Romans. That they employed alumina as a mordant in some of their dyes is evident, but there is no proof whatever that alum, in the modern sense of the word, was known to them. Geber mentions 3 alums which he was in the habit of using, namely, icy alum or rocca alum, jaminous alum or alum of Jamini, and feather alum. Rocca, or Edessa in Syria, is admitted to have been the place where the first manufactory of alum was established, but at what time or by whom is quite unknown. We know only that it must have been posterior to the commencement of the Christian era and prior to the 8th century, when Geber wrote. Gemeni must have been another locality where, at the time of Geber, a manufactory of alum existed. Feather alum was undoubtedly one of the native impure varieties of alum known to the Greeks and Romans. Geber was in the habit of distilling alum by a strong heat, and of preserving the water which came over as a valuable menstruum. If alum be exposed to a red heat in glass vessels, it will give out a portion of sulphuric acid. Hence water distilled from alum by Geber was probably a weak solution of sulphuric acid, which would undoubtedly act powerfully as a solvent of iron and of the alkaline carbonates. It was probably in this way that he used it. 6. Sulphate of iron or copperas, as it is called, cuperosa, in the state of a crystalline salt, was well known to Geber, and appears in his time to have been manufactured. 7. Borac or borax is mentioned by him, but without any description by which we can know whether or not it was our borax. The probability is that it was. Both glass and borax were used by him when the oxides of metals were reduced by him to the metallic state. 8. Vinegar was purified by him by distilling it over, and it was used as a solvent in many of his processes. 9. Nitric acid was known to him by the name of dissolving water. He prepared it by putting into an alembic 1 pound of sulphate of iron of Cyprus, half a pound of saltpetre, and 1/4 pound of alum of Jamini. This mixture was distilled till everything liquid was driven over. He mentions the red fumes which make their appearance in the alembic during the process. This process, though not an economical one, would certainly yield nitric acid. And it is remarkable because it is here that we find the first hint of the knowledge of chemists of this most important acid, without which many chemical processes of the utmost importance could not be performed at all. 10. This acid, thus prepared, he made use of to dissolve silver. The solution was concentrated till the nitrate of silver was obtained by him in a crystallized state. This process is thus described by him. Dissolve silver calcined in solutive water, nitric acid, as before, which being done, cocked it in a phial with a long neck, the orifice of which must be left unstopped, for 1 day only, until a third part of the water be consumed. This being effected, set it with its vessel in a cold place, and then it is converted into small fusible stones like crystal. 11. He was in the habit also of dissolving sal ammoniac in this nitric acid, and employing the solution, which was the aqua regia of the old chemists, to dissolve gold. He assures us that this aqua regia would dissolve likewise sulphur and silver. The latter assertion is erroneous. But sulphur is easily converted into sulphuric acid by the action of aqua regia, and of course it disappears or dissolves. 12. Corrosive sublimate is likewise described by Geber in a very intelligible manner. His method of preparing it was as follows. Take of mercury 1 pound, of dried sulphate of iron 2 pounds, of alum calcined 1 pound, of common salt ½ pound, and of saltpetre 1/4 pound. Incorporate all together by trituration and sublime. Gather the white, dense, and ponderous portions, which shall be found about the sides of the vessel. If in the first sublimation you find it turbid or unclean, which may happen by reason of your own intelligence, sublime a second time with the same fuses. Still more minute directions are given in other parts of the work. We have even some imperfect account of the properties of corrosive sublimate. 13. Corrosive sublimate is not the only preparation of mercury mentioned by Geber. He informs us that when mercury is combined with sulphur, it assumes a red color and becomes cinnabar. He describes the affinities of mercury for the different metals. It adheres easily to 3 metals, namely lead, tin, and gold, to silver with more difficulty, to copper with still more difficulty than to silver, but to iron it unites in no ways unless by artifice. This is a tolerably accurate account of the matter. He says that mercury is the heaviest body in nature except gold, which is the only metal that will sink in it. Now this was true, applied to all the substances known when Geber lived. He gives an account of the method of forming the peroxide of mercury by heat, that variety of it formerly distinguished by the name of red precipitati per se. Mercury, he says, is also coagulated by long and constant retention in fire in a glass vessel with a very long neck and round belly, the orifice of the neck being kept open that the humidity may vanish thereby. He gives another process for preparing this oxide, possible perhaps, though certainly requiring very cautious regulation of the fire. Take, says he, of mercury 1 pound, of vitriol, sulphate of iron, rubified 2 pounds, and of saltpetre 1 pound. Mortify the mercury with these, and then sublime it from rock alum and saltpetre in equal weights. 14. Geber was acquainted with several of the compounds of metals with sulphur. He remarks that sulphur, when fused with metals, increases their weight. Copper combined with sulphur becomes yellow, and mercury red. He knew the method of dissolving sulphur in caustic potash, and again precipitating it by the addition of an acid. His process is as follows. Grind clear and gummose sulphur to a most subtle powder, which boil in a lixivium made of ashes of heartsease and quicklime, gathering from off the surface its oleaginous combustibility, until it be discerned to be clear. This being done, stir the whole with a stick, and then warily take off that which passeth out with the lixivium, leaving the more gross parts in the bottom. Permit that extract to cool a little, and upon it pour a fourth part of its own quantity of distilled vinegar, and then will the whole suddenly be congealed as milk. Remove as much of the clear lixivium as you can, but dry the residue with a gentle fire and keep it. 15. It would appear from various passages in Geber's works that he was acquainted with arsenic in the metallic state. He frequently mentions its combustibility and considers it as the compeer of sulphur, and in his book on furnaces, chapter 25, or 28 in some copies, he expressly mentions metallic arsenic, arsenicum metallinum, in a preparation not very intelligible, but which he considered of great importance. The white oxide of arsenic, or arsenious acid, was obviously well known to him. He gives more than one process for obtaining it by sublimation. He observes in his Sum of Perfection, Book 1, Part 4, Chapter 2, which treats of sublimation, arsenic, which before its sublimation was evil and prone to adustion, after its sublimation suffers not itself to be inflamed, but only resides without inflammation. Geber states the fact that when arsenic is heated with copper, that metal becomes white. He gives also a process by which the white arseniate of iron is obviously made. Grind 1 pound of iron filings with half a pound of sublimed arsenic, arsenious acid. Imbibe the mixture with the water of saltpeter and salt alkali, repeating this imbibation thrice. Then make it flow with a violent fire, and you will have your iron white. Repeat this labour till it flow sufficiently with peculiar dealbation. 16. He mentions oxide of copper under the name of aus ustum, the red oxide of iron under the name of crocus of iron. He mentions also litharge and red lead. But as all these substances were known to the Greeks and Romans, it is needless to enter into any particular details. 17. I am not sure what substance Geber understood by the word marcasite. It was a substance which must have been abundant and in common use, for he refers to it frequently and uses it in many of his processes, but he nowhere informs us what it is. I suspect it may have been sulphuret of antimony, which was certainly in common use in Asia long before the time of Geber. But he also makes mention of antimony by name, or at least the Latin translator has made use of the word antimonium. When speaking of the reduction of metals after heating them with sulphur, he says, "The reduction of tin is converted into clear antimony, but of lead into a dark-coloured antimony, as we have found by proper experience." It is not easy to conjecture what meaning the word antimony is intended to convey in this passage. In another passage he says, "Antimony is calcined, dissolved, clarified, congealed, and ground to powder, so it is prepared." 18. Geber's description of the metals is tolerably accurate, considering the time when he wrote. As an example I shall subjoin his account of gold. Gold is a metallic body, yellow, ponderous, mute, fulged, equally digested in the bowels of the earth, and very long washed with mineral water, under the hammer extensible, fusible, and sustaining the trial of the cupel and cementation. He gives an example of copper being changed into gold. In copper mines, he says, we see a certain water which flows out and carries with it thin scales of copper, which, by a continual and long continued course, it washes and cleanses. but after such water ceases to flow, we find these thin scales with the dry sand, in 3 years' time to be digested with the heat of the sun, and among these scales the purest gold is found. Therefore we judge those scales were cleansed by the benefit of the water, but were equally digested by heat of the sun, in the dryness of the sand, and so brought to equality. Here we have an example of plausible reasoning from defective premises. The gold grains doubtless existed in the sand before, while the scales of copper, in the course of 3 years, would be oxidized and converted into powder and disappear, or at least lose all their metallic luster. Such are the most remarkable chemical facts which I have observed in the works of Geber. They are so numerous and important as to entitle him with some justice to the appellation of the father and founder of chemistry. Besides the metals, sulphur and salt, with which the Greeks and Romans were acquainted, he knew the method of preparing sulphuric acid, nitric acid, and aqua regia. He knew the method of dissolving the metals by means of these acids, and actually prepared nitrate of silver and corrosive sublimate. He was acquainted with potash and soda, both in the state of carbonates and caustic. He was aware that these alkalis dissolve sulphur, and he employed the process to obtain sulphur in a state of purity. End of section 13. Section number 14 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rosehip. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 3, Chemistry of the Arabians, Part 3. But notwithstanding the experimental merit of Geber, his spirit of philosophy did not much exceed that of his countrymen. He satisfied himself with accounting for phenomena by occult causes, as was the universal custom of the Arabians, a practice quite inconsistent with real scientific progress. That this was the case will appear from the following passage, in which Geber attempts to give an explanation of the properties of the great elixir or philosopher's stone. Therefore, let him attend to the properties and ways of action of the composition of the greater elixir. For we endeavour to make one substance, yet compounded and composed of many, so permanently fixed, that being put upon the fire cannot injure, and that it may be mixed with metals in flux, and flow with them, and enter with that which in them is of an ingressible substance, and be fermented with that which in them is of a permixable substance, and be consolidated with that which in them is of a consolidable substance, and be fixed with that which in them is of a fixable substance, and not be burnt by those things which burn not gold and silver, and take away consolidation and weights with due ignition. The next Arabian whose name I shall introduce into this history is Al-Hussein Abu Ali ben Abdallah ibn Sina, surnamed Sheikh Reis, or Prince of Physicians, vulgarly known by the name of Avicenna. Next to Aristotle and Galen, his reputation was the highest, and his authority the greatest of all medical practitioners, and he reigned paramount, or at least shared the medical sceptre till he was hurled from his throne by the rude hands of Paracelsus. Avicenna was born in the year 978 at Bokhara, to which place his father had retired during the emirate of the Caliph Nu, one of the sons of the celebrated Al-Mansur. Ali, his father, had dwelt in Balkh in the Chorazan. After the birth of Avicenna, he went to Ashenna in Bukharia, where he continued to live till his son had reached his 15th year. No labour nor expense was spared on the education of Avicenna, whose abilities were so extraordinary that he is said to have been able to repeat the whole Koran by heart at the age of 10 years. Ali gave him for a master Abu Abdallah Anatoli, who taught him grammar, dialectics, the geometry of Euclid, and the astronomy of Ptolemy. But Avicenna quitted his tuition because he could not give him the solution of a problem in logic. He attached himself to a merchant who taught him arithmetic and made him acquainted with the Indian numerals from which our own are derived. He then undertook a journey to Baghdad, where he studied philosophy under the great peripatician Abu Nasr al-Farabi, a disciple of Messu the elder. At the same time, he applied himself to medicine under the tuition of the Nestorian Abu Sahel Masichi. He informs us himself that he applied with an extraordinary ardour to the study of the sciences. He was in the habit of drinking great quantities of liquids during the night to prevent him from sleeping, and he often obtained in a dream a solution of those problems at which he had laboured in vain while he was awake. When the difficulties to be surmounted appeared to him too great, he prayed to God to communicate to him a share of his wisdom, and these prayers, he assures us, were never offered in vain. The Metaphysics of Aristotle was the only book which he could not comprehend, and after reading them over 40 times, he threw them aside with great anger at himself. Already, at the age of 16, he was a physician of eminence, and at 18 he performed a brilliant cure on the Caliph Nu, which gave him such celebrity that Mohammed, Caliph of Chorazan, invited him to his palace. But Avicenna rather chose to reside at Shorshan, where he cured the nephew of the Caliph Qabus of a grievous distemper. Afterwards he went to Ray, where he was appointed physician to Prince Magd Odaula. Here he composed a dictionary of the sciences. Some time after this he was raised to the dignity of vizier at Hamdan, but he was speedily deprived of his office and thrown into prison for having favoured a sedition. While incarcerated, he wrote many works on medicine and philosophy. By and by he was set at liberty and restored to his dignity. But after the death of his protector, Shems Odaula, being afraid of a new attempt to deprive him of his liberty, he took refuge in the house of an apothecary, where he remained long concealed and completely occupied with his literary labours. Being at last discovered, he was thrown into the castle of Berdawa, where he was confined for 4 months. At the end of that time, a fortunate accident enabled him to make his escape in the disguise of a monk. He repaired to Ispahan, where he lived much respected at the court of the Caliph Ola Odaula. He did not live to a great age, because he had worn out his constitution by too free an indulgence of women and wine. Having been attacked by a violent colic, he caused 8 injections, prepared from long pepper, to be thrown up in one day. This excessive use of so irritating a remedy occasioned an excoriation of the intestines, which was followed by an attack of epilepsy. A journey to Hamdan, in company with the Caliph, and the use of mithridate, into which his servant by mistake had put too much opium, contributed still further to put an end to his life. He had scarcely arrived at the town when he died, in the 58th year of his age, in the year 1036. Avicenna was the author of the immense work entitled Canon, which was translated into Latin, and for 5 centuries constituted the great standard, the infallible guide, the confession of faith of the medical world. All medical knowledge was contained in it, and nothing except what was contained in it was considered by medical men as of any importance. When we take a view of the Canon, and compare it with the writings of the Greeks, and even of the Arabians that preceded it, we shall find some difficulty in accounting for the unbounded authority which he acquired over the medical world, and for the length of time during which that authority continued. But it must be remembered that Avicenna's reign occupies the darkest and most dreary period of the history of the human mind. The human race seems to have been asleep, and the mental faculties in a state of complete torpor. Mankind, accustomed in their religious opinions to obey blindly the infallible decisions of the Church, and to think precisely as the Church enjoined them to think, would naturally look for some means to save them the trouble of thinking on medical subjects. And this means they found, fortunately, in the canons of Avicenna. These canons, in their opinion, were equally infallible with the decisions of the Holy Father, and required to be as implicitly obeyed. The whole science of medicine was reduced to a simple perusal of Avicenna's canon, and an implicit adherence to his rules and directions. When we compare this celebrated work with the medical writings of the Greeks, and even of the Arabians, the predecessors of Avicenna, we shall be surprised that it contains little or nothing which can be considered as original. The whole is borrowed from the writings of Galen or Aetius or Rhazes. Scarcely ever does he venture to trust his own wings, but rests entirely on the sagacity of his Greek and Arabian predecessors. Galen is his great guide, or, if he ever forsake him, it is to place himself under the direction of Aristotle. The canon contains a collection of most of the valuable information contained in the writings of the ancient Greek physicians, arranged, it must be allowed, with great clearness. The Hawi of Rhazes is almost as complete, but it wants the Lucidus Ordo, which distinguishes the canon of Avicenna. I conceive that the high reputation which Avicenna acquired was owing to the care which he bestowed upon his arrangement. He was undoubtedly a man of abilities, but not of inventive genius. There is little original matter in the canon. But the physicians in the West, while Avicenna occupied the medical sceptre, had no opportunity of judging of the originality of their oracle, because they were unacquainted with the Greek language, and could not therefore consult the writings of Galen or Aetius, except through the corrupt medium of an Arabian version. But it is not the medical reputation of Avicenna that induced me to mention his name here. Like all the Arabian physicians, he was also a chemist, and his chemical tracts, having been translated into Latin and published in Western Europe, we are enabled to judge of their merit, and to estimate the effect which they may have had upon the progress of chemistry. The first Latin translation of the chemical writings of Avicenna was published at Basel in 1572. They consist of 2 separate books. The first, under the name of Porta Elementorum, consists of a dialogue between a master and his pupil respecting the mysteries of alchemy. He gives an account of the four elements, fire, air, water, earth, and gives them their usual qualities of dry, moist, hot, and cold. He then treats of air, which he says is the food of fire, of water, of honey, of the mutual conversion of the elements into each other, of milk and cheese, of the mixture of fire and water, and that all things are composed of the four elements. There is nothing in this tract which has any pretension to novelty. He merely retails the opinions of the Greek philosophers. The other treatise is much larger, and professes to teach the whole art of alchemy. It is divided into 10 parts, entitled Dictiones. The first diction treats of the philosopher's stone in general. The second diction treats of the method of converting light things into heavy, hard things into soft, of the mutation of the elements, and of some other particulars of a nature not very intelligible. The third diction treats of the formation of the elixir, and the same subject is continued in the fourth. The fifth diction is one of the most important in the whole treatise. It is in general intelligible, which is more than can be said of those that precede it. This diction is divided into 28 chapters. The first chapter treats of copper, which he says is of 3 kinds: Parmenian copper, natural copper, and Navarre copper. But of these 3 varieties he gives no account whatever, though he enlarges a good deal on the qualities of copper, not its properties, but its supposed medicinal action. It is hot and dry, he says, but in the calx of it there is humidity. His account of the composition of copper is the same with that of Geber. The second chapter treats of lead, the third of tin, and in the remaining chapters he treats successively of brass, iron, gold, silver, marcasite, sulphuret of antimony, which is distinguished by the name of alcohol, of soda, which he says is the juice of a plant called sosa, and he gives an unintelligible process by which it is extracted from that plant, without mentioning a syllable about the combustion to which it is obvious that it must have been subjected. In the 12th chapter he treats of saltpeter, which he says is brought from Sicily, from India, from Egypt, and from Herminia. He describes several varieties of it, but mentions nothing about its characteristic property of deflagrating upon burning coals. He then treats successively of common salt, of sal gem, of vitriol, of sulphur, of orpiment, and of sal ammoniac, which he says comes from Egypt, from India, and from Forperia. In the 19th and subsequent chapters he treats of aurum vivum, of hair, of urine, of eggs, of blood, of glass, of white linen, of horse dung, and of vinegar. The 6th diction, in 33 chapters, treats of the calcination of the metals, of sublimation, and of some other processes. I think it unnecessary to be more particular, because I cannot perceive anything in it that had not been previously treated of by Geber. The 7th diction treats of the preparation of blood and eggs, and the method of dividing them into their 4 elements. It treats also of the elixir of silver and the elixir of gold, but it contains no chemical fact of any importance. The 8th diction treats of the preparation of the ferment of silver and of gold. The 9th diction treats of the whole magistery and of the nuptials of the sun and moon, that is, of gold and silver. The 10th diction treats of weights. The chemical writings of Avicenna are of little value, and apply chemistry rather to the supposed medical qualities of the different substances treated of than to the advancement of the science. All the chemical knowledge which he possesses is obviously drawn from Geber. Geber, then, may be looked upon as the only chemist among the Arabians to whom we are indebted for any real improvements and new facts. It is true that the Arabian physicians improved considerably the materia medica of the Greeks, and introduced many valuable medicines into common use which were unknown before their time. It is enough to mention corrosive sublimate, manna, opium, asafoetida. It would be difficult to make out many of the vegetable substances used by the Arabian chemists, because the plants which they designated by particular names can very seldom be identified. Botany at that time had made so little progress that no method was known of describing plants so as to enable other persons to determine what they were. End of section 14.
Section 15 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dorothy Godfrey Smith. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 4, of the Progress of Chemistry under Paracelsus and his Disciples. Part 1. Hitherto we have witnessed only the first rude beginnings, or, as it were, the early dawn of the chemical day. It is from the time of Paracelsus that the true commencement of chemical investigations is to be dated. Not that Paracelsus or his followers understood the nature of the science, or undertook any regular or successful investigation. But Paracelsus shook the medical throne of Galen and Avicenna to its very foundation. He roused the latent energies of the human mind, which had for so long a period lain torpid. He freed medical men from those trammels, and put an end to that despotism which had existed for 5 centuries. He pointed out the importance of chemical medicines and of chemical investigations to the physician. This led many laborious men to turn their attention to the subject. Those metals which were considered as likely to afford useful medicines, mercury, for example, and antimony, were exposed to the action of an infinite number of reagents, and a prodigious collection of new products obtained and introduced into medicine. Some of these were better, and some worse than the preparations formerly employed. But all of them led to an increase of the stock of chemical knowledge, which now began to accumulate with considerable rapidity. It will be proper, therefore, to give a somewhat particular account of the life and opinions of Paracelsus, so far as they can be made out from his writings, because, though he was not himself a scientific chemist, he may be truly considered as the man through whose means the stock of chemical knowledge was accumulated, which was afterwards, by the ingenuity of Becker and Stahl, molded into a scientific form. Philippus Aureolus Theophrastus Paracelsus Bombast ab Hohenheim, as he denominates himself, was born at Einsiedeln, 2 German miles from Zurich. His father was called William Bombast von Hohenheim. He was a very near relation of George Bombast von Hohenheim, who became afterwards Grand Master of the Order of Johannites. William Bombast von Hohenheim practiced medicine at Einsiedeln. After receiving the first rudiments of his education in his native city, he became a wandering scholastic, as was then the custom with poor scholars. He wandered from province to province, predicting the future by the position of the stars and the lines on the hand, and exhibiting all the chemical processes which he had learned from founders and alchemists. For his initiation in alchemy, astrology, and medicine, he was indebted to his father, who was much devoted to these three sciences. Paracelsus mentions also the names of several ecclesiastics from whom he received chemical information, among others Trithemius, abbot of Spanheim, Bishop Scheidt of Stettbach, Bishop Erhard of Laventhal, Bishop Nicholas of Hippon, and Bishop Matthew Schacht. He seems also to have served some years as an army surgeon, for he mentions many cures which he performed in the Low Countries, in the states of the Church, in the kingdom of Naples, and during the wars against the Venetians, the Danes, and the Dutch. There is some uncertainty whether he received a regular college education, as was then the practice with all medical men. He acknowledges himself that his medical antagonists reproached him with never having frequented their schools, and he is perpetually affirming that a physician should receive all his knowledge from God and not from men. But if we can trust his own assertions, there can be no doubt that he took a regular medical degree, which implies a regular college education. He tells us in his preface to his Chirurgia Magna that he visited the universities of Germany, France, and Italy. He assures his readers that he was the ornament of the schools where he studied. He even speaks of the oath which he was obliged to take when he received his medical degree. But where he studied, or where and when he received his medical degree, are questions which neither Paracelsus nor his disciples nor his biographers have enabled us to solve. If he ever attended a university, he must have neglected his studies, otherwise he could not have been ignorant, as he confessedly was, of the very first elements of the most common kinds of knowledge. But if he neglected the universities, he labored long and assiduously with the rich Sigismund Fogaris of Schwartz in order to learn the true secret of forming the philosopher's stone. He gives us some details of the numerous journeys that he made, as was customary with the alchemists of the time, into the mountains of Bohemia, the East, and Sweden, to inspect the mines, to get himself initiated into the mysteries of the Eastern adepts, to inspect the wonders of nature, and to view the celebrated Diamond Mountain, the position of which, however, he unfortunately forgets to specify. In the preface to his Chirurgia Magna, he informs us that he traversed Spain, Portugal, England, Prussia, Poland, and Transylvania, where he not only profited by the information of the medical men with whom he became acquainted, but that he drew much precious information from old women, gypsies, conjurers, and chemists. He spent several years in Hungary, and informs us that at Weissenberg, in Croatia, and in Stockholm, he was taught by several old women to prepare drinks capable of curing ulcers. He is said also to have made a voyage into Egypt, and even into Tartary, and he accompanied the son of the Khan of the Tartars to Constantinople, in order to learn the secret of the philosopher's stone from Trismogen, who inhabited that capital. This prodigious activity, this constant motion from place to place, left him but little leisure for reading. Accordingly, he informs us himself that during the space of 10 years he never opened a book, and that his whole library consisted only of 6 sheets. The inventory of his books, drawn up after his death, confirms this recital, for they consisted only of the Bible, the concordance to the Bible, the New Testament, and the commentaries of St. Jerome on the Evangelists. We know not at what period he returned back to Germany, but at the age of 33, the great number of fortunate cures which he had performed rendered him an object of admiration to the people and of jealousy to the rival physicians of the time. He assures us that he cured 18 princes whose diseases had been aggravated by the practitioners devoted to the system of Galen. Among others, he cured Philip, Margrave of Baden, of a dysentery, who promised him a great reward, but did not keep his promise, and even treated him in a way unworthy of that prince. This cure, however, and others of a similar nature, added greatly to his celebrity, and in order to raise his reputation to the highest possible pitch, he announced publicly that he was able to cure all the diseases hitherto reckoned incurable, and that he had discovered an elixir by means of which the life of men might be prolonged at pleasure to any extent whatever. He began the practice, which has since been so successfully followed in this country, of dispensing medicines gratuitously to the poor, in order to induce the rich to apply to him for assistance when they were overtaken with diseases. In the year 1526, Paracelsus was appointed professor of physic and surgery in the University of Basel. This appointment was given him, it is said, by the recommendation of Ecolampadius. He introduced the custom of lecturing in the common language of the country, as is at present the universal practice. But during the time of Paracelsus, and long after indeed, all lectures were delivered in Latin. The new method which he followed in explaining the theory and practice of the art, the numerous fortunate cures which he stated in confirmation of his method of treatment, the emphasis with which he spoke of his secrets for prolonging life and for curing every kind of disease without distinction, but still more his lecturing in a language which was understood by the whole population, drew to Basle an immense crowd of idle, enthusiastic, and credulous hearers. The lectures which he delivered on practical medicine still remain, written in a confused mixture of German and barbarous Latin, and containing little or nothing except a farrago of empirical remedies, advanced with the greatest confidence. They have a much greater resemblance to a collection of quack advertisements than to the sober lectures of a professor in a university. In the month of November 1526, he wrote to Christopher Clauser, a physician in Zurich, that as Hippocrates was the first physician among the Greeks, Avicenna among the Arabians, Galen among the Pergamenians, and Marcellus among the Italians, so he was, beyond dispute, the greatest physician among the Germans. Every country produces an illustrious physician, whose medicines are adapted to the climate in which he lived, but not suited to other countries. The remedies of Hippocrates were good to the Greeks, but not suitable to the Germans. Thus, it was necessary that an inspired physician should spring up in every country, and that he was the person destined to teach the Germans the art of curing all diseases. Paracelsus began his professional career by burning publicly in his classroom and in the presence of his pupils the works of Galen and Avicenna, assuring his hearers that the strings of his shoes possessed more knowledge than those two celebrated physicians. All the universities united had not, he assured them, as much knowledge as was contained in his own beard, and the hairs upon his neck were better informed than all the writers that ever existed put together. To give the reader an idea of the arrogant absurdity of his pretensions, I shall translate a few sentences of the preface to his tract entitled Paragranum, where he indulges in his usual strain of rhodomontade. Me you shall follow, you Avicenna, you Galen, you Rhazes, you Montagnana, you Mesue. I shall not follow you, but you shall follow me. You, I say, you inhabitants of Paris, you inhabitants of Montpellier, you Suevi, you Messinians, you inhabitants of Cologne, you inhabitants of Vienna, all you whom the Rhine and the Danube nourish, you who inhabit the islands of the sea, you also Italy, you Dalmatia, you Athens, you Greek, you Arabian, you Israelite. I shall not follow you, but you shall follow me. Nor shall anyone lurk in the darkest and most remote corner whom the dogs shall not piss upon. I shall be the monarch, the monarchy shall be mine. If I administer and I bind up your loins, is he with whom you are at present delighted a Cacophrastus? This ordure must be eaten by you. What will your opinion be when you see your Cacophrastus constituted the chief of the monarchy? What will you think when you see the sect of Theophrastus leading on a solemn triumph, if I make you pass under the yoke of my philosophy? Your Pliny will you call Cacopliny, and your Aristotle Caco-Aristotle? If I plunge them together with your Porphyry, Albertus, etc., and the whole of their compatriots into my necessary? But the terms become now so coarse and indelicate that I cannot bring myself to proceed further with the translation. Enough has been given to show the extreme arrogance and folly of Paracelsus. So far, however, was this impudence and grossness from injuring the interest of Paracelsus, that we are assured by Ramus and Orsticius that it contributed still further to increase it. The coarseness of his language was well suited to the vulgarity of the age, and his arrogance and boasting were considered, as usual, as a proof of superior merit. The cure which he performed on Frobenius drew the attention of Erasmus himself, who consulted him about the diseases with which he was afflicted, and the letters that passed between them are still preserved. The epistle of Paracelsus is short, enigmatical, and unintelligible. That of Erasmus is distinguished by that clearness and elegance which characterize his writings. But Frobenius died in the month of October 1527, and the antagonists of Paracelsus attributed his death, and probably with justice, to the violent remedies which had been administered to a man whose constitution had been destroyed by the gout. His death contributed not a little to tarnish the glory of Paracelsus, but he suffered the greatest injury from the habits of intoxication in which he indulged, and from the vulgarity of the way in which he spent his time. He hardly ever went into his classroom to deliver a lecture till he was half intoxicated, and scarcely ever dictated to his secretaries till he had lost the use of his reason by a too liberal indulgence in wine. If he was summoned to visit a patient, he scarcely ever went but in a state of intoxication. Not unfrequently he passed the whole night in the alehouse in the company of peasants, and when morning came was quite incapable of performing the duties of his station. On one occasion, after a debauch which lasted the whole night, he was called next morning to visit a patient. On entering the room he inquired if the sick person had taken anything. Nothing, was the answer, except the body of our Lord. Since you have already, says he, provided yourself with another physician, my presence here is unnecessary. And he left the apartment instantly. When Albertus Bassa, physician to the King of Poland, visited Paracelsus in the city of Basel, he carried him to see a patient whose strength was completely exhausted, and which, in his opinion, it was impossible to restore. But Paracelsus, wishing to make a parade of his skill, administered to him 3 drops of his laudanum, and invited him to dine with him next day. The invitation was accepted, and the sick man dined next day with his physician. Footnote: there were 2 laudanums of Paracelsus. One was red oxide of mercury, the other consisted of the following substances: chloride of antimony, 1 ounce, hepatic aloes, 1 ounce, rose water, ½ an ounce, saffron, 3 ounces, ambergris, 2 drachms, all these well mixed. Towards the end of the year 1527, a disgraceful dispute into which he entered brought his career as a professor to a sudden termination. The Canon Cornelius of Lichtenfels, who had been long a martyr to the gout, employed him as his physician, and promised him 100 florins if he could cure him. Paracelsus made him take 3 pills of laudanum, and having thus freed him from pain, demanded the sum agreed upon, but Lichtenfels refused to pay him the whole of it. Paracelsus summoned him before the court, and the magistrate of Basel decided that the canon was bound to pay only the regular price of the medicine administered. Irritated at this decision, our intoxicated professor uttered a most violent invective against the magistrate, who threatened to punish him for his outrageous conduct. His friends advised him to save himself by flight. He took their advice, and thus abdicated his professorship. But by this time his celebrity as a teacher had been so completely destroyed by his foolish and immoral conduct that he had lost all his hearers. In consequence of this state of things, his flight from Basel produced no sensation whatever in that university. End of section 15. Recording by Dorothy Godfrey Smith. Section 16 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dorothy Godfrey Smith. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 4, of the Progress of Chemistry under Paracelsus and his Disciples, Part 2. Paracelsus betook himself in the first place to Alsace, and sent for his faithful follower the bookseller Operinus, together with the whole of his chemical apparatus. In 1528 we find him at Colmar, where he recommenced his ambulating life of a theosophist, which he had led during his youth. His book upon syphilis, known at that time by the name of Morbus Gallicus, was dedicated at Colmar to the chief magistrate of Colmar, Hieronymus Bonerus. In 1531 he was at St. Gallen, in 1535 at Feftersbad, and in 1536 at Augsburg, where he dedicated his Chirurgia Magna to Malhausen. At the request of John de Leipa, Marshal of Bohemia, he undertook a journey into Moravia, as that nobleman, having been informed that Paracelsus understood the method of curing the gout radically, was anxious to put himself under his care. Paracelsus lived for a long time at Cromen and its environs. John de Leipa, instead of receiving any benefit from the medicines administered to him, became daily worse, and at last died. This was the fate also of the Lady of Zeroten, in whom the remedies of Paracelsus produced no fewer than 24 epileptic fits in one day. Paracelsus, instead of waiting the disgrace with which the death of this lady would have overwhelmed him, announced his intention of going to Vienna, that he might see how they would treat him in that capital. It is said that from Vienna he went into Hungary, but in 1538 we find him in Villach, where he dedicated his Chronica et Orgio Carinthiae to the states of Carinthia. His book, De Natura Rerum, had been dedicated to Winkelstein, and the dedication is dated also at Villach in the year 1537. In 1540 he was at Mindelheim, and in 1541 at Strasbourg, where he died in St. Stephen's Hospital in the 48th year of his age. To form an accurate idea of this most extraordinary man, we must attend to his habits and to the situation in which he was placed. He had acquired such a habit of moving about, that he assures us himself he found it impossible for him to continue for any length of time in one place. He was always surrounded by a number of followers, whom neither his habits of intoxication nor the foolish and immoral conduct in which he was accustomed to indulge could induce to forsake him. The most celebrated of these was Operinus, a printer at Basel, on whom Paracelsus lavishes the most excessive praises in his book De Morbo Gallico. But Operinus loaded his master with obloquy, being provoked at him, because he had not made him acquainted with the secret of the philosopher's stone, as he had promised to do. We must therefore be cautious in believing the stories that he relates to the discredit of his master. We know the names of two others of his followers, Francis, who assures us that Paracelsus was devoted to the transmutation of metals, and George Vetter, who considered him as a magician, as was the opinion also of Operinus. Paracelsus himself speaks of Dr. Cornelius, whom he calls his secretary, and in honor of whom he wrote several of his libels. Other libels are dedicated to Doctors Peter, Andrew, and Ursinus, to the licentiate Pancrace, and to Mr. Raphael. On this occasion he complains bitterly of the infidelity of his servants, who, he says, had succeeded in stealing from him several of his secrets, and had by this means been enabled to establish their reputation. He accuses equally the barbers and bathers that followed him, and is no less severe upon the physicians of every country through which he travelled. When we attempt to form an accurate conception of the medical and philosophical opinions of this singular man, we find ourselves beset with almost insurmountable difficulties. His statements are so much at variance with each other in his different pieces, and so much confusion reigns with respect to the order of publication, that we know not what to fix on as his last and maturest opinions. His style is execrable, filled with new words of his own coining, and of mysticisms either introduced to excite the admiration of the ignorant, or from the fanaticism and credulity of the writer, who was undoubtedly, to a considerable extent, the dupe of his own impostures. That he was in possession of the philosopher's stone, or of a medicine capable of prolonging life to an indefinite length, as he all along asserted, he could not himself believe. But he had boasted so long and so loudly of his wonderful cures, and of the efficacy of his medicines, that there can be no doubt that he ultimately placed implicit faith in them. The blunders of the transcribers whom he employed to copy his works may perhaps account for some of the contradictions which they contain. But how can we look for a regular system of opinions from a man who generally dictated his works when in a state of intoxication, and thus labored under an almost constant deprivation of reason? His obscurity was partly the effect of design, and no doubt was intended to exalt the notions entertained of his profundity. he uses common words in new significations, without giving any indication of the change which he introduced. Thus, anatomy, in the writings of Paracelsus, signifies not the dissection of dead animals to determine their structure, but it means the nature, force, and magical designation of a thing. And as, according to the Platonic and Kabbalistic theory, every earthly body is formed after the model of a heavenly body, Paracelsus calls anatomy the knowledge of that model, of that ideal, or of that paradigm after which all things are created. He terms the fundamental force of a thing a star, and defines alchemy, the art of drawing out the stars of metals. The star is the source of all knowledge. When we eat, we introduce into our bodies the star, which is then modified and favors nutrition. It is probable that many of his obscure and unintelligible expressions are the fruit of ignorance. Thus he uses the term pagoias instead of paganus. He gives the name of pagoiae to the 4 entities or causes of diseases, founded on the influence of the stars, to the elementary qualities, to the occult qualities, and to the influence of spirits, because these had been already admitted by the pagans. But the 5th entity or cause of disease, which has God immediately for its author, is non-pagoia. The undimia of Paracelsus is our edema, only he applies the name to every kind of dropsy. The Latin word tonitru we find is declined by Paracelsus. Thus he says lapis tonitrui. The well-known line of Ovid, tolere nodosam nesit medicina podagram, he travestied into nestit tartariam roades curare podagram. Roads, he says, means medicines for horses, and if any person wishes a more elegant verse, he may make it for himself. He employs also a great number of words to which no meaning whatever can be attached, and to which, in all probability, he himself had affixed none. As is the case with all fanatics, he treated with contempt every kind of knowledge acquired by labor and application, and boasted that his wisdom was communicated to him directly by God Almighty. The theosophist who is worthy of partaking of the divine light has no occasion for adopting a positive religion, nor of subjecting himself to any kind of religious ceremony. The divine light within, which assimilates him to the deity, more than compensates for all these vulgar usages, and raises the illuminated votary far above the beggarly elements of external worship. Accordingly, Paracelsus has been accused of treating the public worship of the deity with contempt. Not satisfied with the plain sense of the book, he attempted to explain in a mystical manner the words and syllables of the Bible. He accused Luther of not going far enough. Luther, says he, is not worthy of untying the strings of my shoes. Should I undertake a reformation, I would begin by sending the Pope and the reformers themselves to school. God, says Paracelsus, is the first and most excellent of writers. The Holy Scripture conducts us to all truth and teaches us all things. But medicine, philosophy, and astronomy are among the number of things. Therefore, when we want to know what magical medicine is, we must consult the Apocalypse. The Bible, with its paraphrases, is the key to the theory of diseases. It puts it in our power to understand St. John, who, like Daniel, Ezekiel, Moses, etc., was a magician, a Kabbalist, a diviner. The first duty of a physician is to study the Kabbalah, without which he must every moment commit 1,000 blunders. Learn, says he, the Kabbalistic art, which includes under it all the others. Man invents nothing, the devil invents nothing. It is God alone who unveils to us the light of nature. God honored at first with his illumination the blind pagans, Apollo, Aesculapius, Machaon, Podalirius, and Hippocrates, and imparted to them the genius of medicine. Their successors were the sophists. One would suppose from this passage that Paracelsus had read and studied Hippocrates, and that he held him in high estimation. But the commentaries which he has left on some of the aphorisms show evidently that he did not even understand the Greek physician. The compassion of God, says he, is the only foundation of medical science, and not a knowledge of the great masters, or of the writings which they have left in Greek and Latin. God often acts in dreams by the light of nature, and points out to man the manner of curing diseases. This knowledge renders all those objects visible which would otherwise escape the sight. And when faith is joined with it, nothing is then impossible to the theosophist, who may transport the ocean to the top of Mount Etna and Olympus into the Red Sea. Paracelsus predicts that by the year 1590 Christian theosophy would be generally spread over the world, and that the Galenical schools would be almost or entirely overthrown. We find in Paracelsus some traces of the opinions of the Gnostics and Arians, who considered Christ as the first emanation of the deity. He calls the first man parens homitus, and makes all spirits emanate from him. He is the limbus minor, or the last creature into whom enters the great limbus, or the seed of all the creatures, the infinite being. All the sciences and all the arts of man are derived from this great limbus, and he who can sink himself in the little nimbus, that is to say, in Adam, and who can communicate by faith with Jesus Christ, may invoke all spirits. Those who owe their science to this limbus are the best informed. Those who derive it from the stars occupy the last rank, and those who owe it to the light of nature are intermediate between the preceding. Jesus Christ, in his capacity of limbus minor and first man, being always an emanation of the divinity, and consequently a subordinate personage. These ideas explain to us why Paracelsus passed for an Arian, and was supposed not to believe in the divinity of Jesus Christ. He was of opinion that the faithful performed miracles, and operated magical cures by their simple confidence in God the Father, and not by their faith in Christ. But he adds, however, that we ought to pray to Jesus in order to obtain his intercession. From the preceding attempt to explain the opinions of Paracelsus, it will be evident to the reader that he was both a fanatic and impostor, and that his theory, if such name can be given to the reveries of a drunkard, consisted in uniting medicine with the doctrines of the Kabbalah. A few more observations will be necessary to develop his dogmas still further. Everybody, in his opinion, and man in particular, is double, consisting of a material and spiritual substance. The spiritual, which may be called the sideric, results from the celestial influences, and we may trace after it a figure capable of producing all kinds of magical effects. When we can act upon the body itself, we act at the same time upon the spiritual form by characters and conjurations. Yet in another passage he blames all magical ceremonies and ascribes them to want of faith. the celestial intelligences impress upon material bodies certain signs which manifest their influence. The perfection of art consists in understanding the meaning of these signs, and in determining from them the nature, qualities, and essence of a body. Adam, the first man, had a perfect knowledge of the Kabbalah. He could interpret the signatures of all things. It was this which enabled him to assign to the animals names which suited them best. A man who renounces all sensuality and is blindly obedient to the will of God is capable of taking a share in the actions which celestial intelligences perform, and consequently is possessed of the philosopher's stone. Never does he want anything. All creatures in earth and in heaven are obedient to him. He can cure all diseases and prolong his life as long as he pleases, because he possesses the tincture which Adam and the patriarchs before the flood employed to prolong the term of their existence. Footnote: Afkidoxorum, lib. 8, Opera Paracelsi, 229. In this book he gives the method of preparing the elixir of life. It seems to have been nothing else than a solution of common salt in water, for the quintessence of gold with which this solution was to be mixed was doubtless an imaginary substance. End of footnote. Beelzebub, the chief of the demons, is also subject to the power of magic. And who can blame the theosophist for believing in the devil? He ought, however, to take care to prevent this malignant spirit from commanding him. Paracelsus was often wont to say, "If God does not aid me, the devil will help me." Pantheism was one of the principal dogmas of the Kabbalah, and Paracelsus adopts it in all its grossness. He affirms perpetually that everything is animated in the universe, that everything which exists eats, drinks, and voids excrements. Even minerals and liquids take food and void the digested remains of their nourishment. This opinion leads necessarily to the admission of a great number of spiritual substances, intermediate between material and immaterial, in every part of the sublunary world, in water, air, earth, and fire, who, as well as men, eat, drink, converse, beget children, but which approach pure spirits in this, that they are more transparent and infinitely more agile than all other animal bodies. Man possesses a soul of which these pure spirits are destitute. Hence it happens that these spiritual substances are at once body and spirit, without a soul. When they die, for like the human race they are subject to death, no soul remains. Like us, they are exposed to diseases. Their names vary according to the places that they occupy. When they inhabit the air, they are called sylphs; when the water, nymphs; when the earth, pygmies; when the fire, salamanders. The inhabitants of the waters are also called undinae, and those of the fire, vulcani. The sylphs approach nearest to our nature, as they live in the air like us. The sylphs, nymphs, and pygmies sometimes obtain permission from God to make themselves visible, to converse with men, to indulge in carnal pleasures, and to produce children. But the salamanders have no relation to man. These spiritual beings are acquainted with the future, and capable of revealing it to man. They appear under the form of ignis fatui. We have also the history of the fairies and the giants, and are told how these spiritual beings are the guardians of concealed treasures, and how these sylphs, nymphs, pygmies, and salamanders may be charmed, and their treasures taken from them. This division of man into body and spirit, and of the things of nature into visible and invisible, has in all ages of the world been adopted by fanatics, because it enabled them to explain the history of ghosts and 1,000 similar prejudices. Hence the distinction between soul and spirit, which is so very ancient, and hence the 3 following harmonies to which the successors of Paracelsus paid a particular attention: soul, spirit, body; mercury, sulfur, salt; water, air, earth. The will and the imagination of man acts principally by means of the spirit. Hence the reason of the efficacy of sorcery and magic. The Navi Materni are the impressions of these vice men, and Paracelsus calls them cocomica signa. The sideric body of man draws to him by imagination all that surrounds him, and particularly the stars, on which it acts like a magnet. In this manner, women with child, and during the regular period of monthly evacuation, having a diseased imagination, are not only capable of poisoning a mirror by their breath, but of injuring the infants in their wombs, and even also of poisoning the moon. But it seems needless to continue this disagreeable detail of the absurd and ridiculous opinions which Paracelsus has consigned to us in his different tracts. The physiology of Paracelsus, if such a name can be applied to his reveries, is nothing else than an application of the laws of the Kabbalah to the explanation of the functions of the body. There exists, he assures us, an intimate connection between the sun and the heart, the moon and the brain, Jupiter and the liver, Saturn and the spleen, Mercury and the lungs, Mars and the bile, Venus and the kidneys. In another part of his works, he informs us that the sun acts on the umbilicus and the middle parts of the abdomen, the moon on the spine, Mercury on the bowels, Venus on the organs of generation, Mars on the face, Jupiter on the head, and Saturn on the extremities. The pulse is nothing else than the measure of the temperature of the body, according to the space of the 6 places which are in relation to the planets. 2 pulses under the sole of the feet belong to Saturn and Jupiter, 2 at the elbow to Mars and Venus, 2 in the temples to the moon and Mercury. The pulse of the sun is found under the heart. The macrocosm has also 7 pulses, which are the revolutions of the 7 planets, and the irregularity or intermittence of these pulses is represented by the eclipses. The moon and Saturn are charged in the macrocosm with thickening the water, which causes it to congeal. In like manner, the moon of the microcosm, that is to say, the brain, coagulates the blood. Hence, melancholy persons, whom Paracelsus calls lunatics, have a thick blood. We ought not to say of a man that he has such and such a complexion, but that it is Mars, Venus, etc., so that a physician ought to know the planets of the microcosm, the Arctic and Antarctic pole, the meridian, the zodiac, the east and the west, before trying to explain the functions or cure the diseases. This knowledge is acquired by a continual comparison of the macrocosm with the microcosm. What must have been the state of medicine at the time when Paracelsus wrote, when the propagator of such opinions could be reckoned one of the greatest of its reformers? End of section 16. Recording by Dorothy Godfrey Smith.
Section 17 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga. pjk.scripts.mit.edu/pkj. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 4, of the Progress of Chemistry under Paracelsus and his Disciples, Part 2. The system of Galen had for its principal basis the doctrine of the four elements, fire, air, water, and earth. Paracelsus neglected these elements, and multiplied the substances of the disease itself. He admits, strictly speaking, 3 or 4 elements, namely the star, the root, the element, the sperm, which he distinguishes by the name of the true seed. All these elements were originally confounded together in the chaos or Iliados. The star is the active force, which gives form to matter. The stars are reasonable beings addicted to sodomy and adultery, like other creatures. Each of them draws at pleasure out of the chaos the plant and the metal to which it has an affinity, and it gives the sideric a form of the root. There are 2 kinds of seed. The sperm is the vehicle of the true seed. It is engendered by speculation, by imagination, by the power of the star. The occult, invisible sideric body produces the true seed, and the Adamic man secretes only the visible envelope of it. Putrefaction cannot give birth to a new body. The seed must pre-exist, and it is developed during putrefaction by the power of the stars. The generation of animals is produced by the concourse of the infinite number of seeds which detach themselves from all parts of the body. Thus the seed of the nose reproduces a nose, that of the eye, and so on. With respect to the elements themselves, Paracelsus admits occasionally their influence on the functions of the body and the theory of diseases, but he deduces the faculties which they possess from the stars. It was he that first shook the doctrine of the 4 elements, originally contrived by Empedocles. Alchemy had introduced another set of elements, and the alchemists maintained that salt, sulfur, and mercury were the true elements of things. Paracelsus endeavored to reconcile these chemical elements with his Kabbalistic ideas, and to show more clearly their utility in the theory of medicine. He invented a sideric salt, which can only be perceived by the exquisite senses of a theosophist, elevated to the abnegation of all gross sensuality to a level with pure and spiritual demons. This salt is the cause of the consistence of bodies, and it is it which gives them the faculty of being reproduced from their ashes. Paracelsus imagined also a sideric sulfur, which, being vivified in the influence of the stars, gives bodies the property of growing, and of being combustible. He admits also a sideric mercury, the foundation of fluidity and volatilization. The concourse of these 3 substances forms the body. In different parts of his works, Paracelsus says that the elements are composed of these 3 principles. In plants he calls the salt balsam, the sulfur resin, and the mercury gotteronium. In other passages he opposes the assertion of the Galenists that fire is dry and hot, air cold and moist, earth dry and cold, water moist and cold. Each of these elements, he says, is capable of admitting all qualities, so that in reality there exists a dry water, a cold fire, etc. I must not omit another remarkable physiological doctrine of Paracelsus, namely that there exists in the stomach a demon called Archeus, who presides over the chemical operations which take place in it, separating the poisonous from the nutritive part of the food, and furnishing the elementary substances with the tincture, in consequence of which they become capable of being assimilated. This ruler of the stomach, who changes bread into blood, is the type of the physician who ought to keep up a good understanding with him and lend him his assistance. To produce a change in the humours ought never to be the object of the true physician. He should endeavour to concentrate all his operations on the stomach and the ruler who reigns in it. This Archeus, to whom the name of nature may also be given, produces all the changes by his own power. It is he alone who cures diseases. He has a head and hands, and is nothing else than the spirit of life, the sideric body of man, and no other spirit besides exists in the body. Each part of the body has also a peculiar stomach, in which the secretions are elaborated. There are, he informs us, 5 different causes of diseases. The first is the ens astrorum. The constellations do not immediately induce diseases, but they alter and infect the air. This is what, properly speaking, constitutes the entity of the stars. Some constellations sulphurize the atmosphere, others communicate to it arsenical, saline, or mercurial qualities. The arsenical astral entities injure the blood, the mercurial the head, the saline the bones and the vessels. Orpiment occasions tumors and dropsies, and the bitter stars induce fever. The second morbific cause is the ens veneni, which proceeds from elementary substances. When the archeus is languid, putrefaction ensues, either localiter or emuncturaliter. This last takes place when those evacuations which ought to be expelled by the nose, the intestines, or the bladder, are retained in the body. Dissolved mercury escapes through the pores of the skin, white sulphur by the nose, arsenic by the ears, sulphur diluted with water by the eyes, salt in solution by the urine, and sulphur deliquesced by the intestines. The third morbific cause of disease is the ens naturale, but Paracelsus subjects to the ens astrorum the principles which the schools are in the habit of arranging among the smaller number of natural causes. The ens spirituale forms the 4th species, and the ens diale, or Christian entity, the 5th. This last class comprehends all the immediate effects of divine predestination. It would lead us too far if I were to point out the strange methods which he takes to discover the cause of diseases. But his doctrine concerning tartar is too important, and does our fanatic too much credit to be omitted. It is without doubt the most useful of all the innovations which he introduced. Tartar, according to him, is the principle of all maladies proceeding from the thickening of the humours, the rigidity of the solids, or the accumulation of earthly matter. Paracelsus thought the term stone not suitable to indicate that matter, because it applies only to one species of it. Frequently the principle proceeds from mucilage, and mucilage is tartar. He calls this principle tartar, tartarus, because it burns like hellfire, and occasions the most dreadful diseases. As tartar, or bitartarate of potash, is deposited at the bottom of the wine cask, in the same way tartar in the living body is deposited on the surface of the teeth. It is deposited on the internal parts of the body when the archeus acts with too great impetuosity and in an irregular manner, and when it separates the nutritive principle with too much impetuosity. Then the saline spirit unites itself to it and coagulates the earthly principle, which is always present, but often in the state of materia prima without being coagulated. In this manner tartar in the state of materia prima may be transmitted from father to son, but it is not hereditary and transmittable when it has already assumed the form of gout, of renal calculus, or of obstruction. The saline spirit which gives it form, and causes its coagulation, is seldom pure and free from mixture. Usually it contains alum, vitriol, or common salt, and this mixture contributes also to modify the tartarous diseases. The tartar may be likewise distinguished according as it comes from the blood itself, or from foreign matters accumulated in the humours. The great number of calculi which have been found in every part of the body, and the obstructions, confirm to the generality of this morbific cause, to which are due most of the diseases of the liver. When the tartarous matter is increased by certain articles of food, renal calculi are engendered, and a calculous paroxysm is induced, and a violent pain is occasioned. It acts as an emetic, and may be even given occasion to death when the saline spirit becomes corrosive, and when the tartar coagulated by it becomes too irritating. Tartar, then, is always an excrementitious substance, which in many cases results from the too great activity of the digestive forces. It may make its appearance in all parts of the body, from the irregularity and the activity, too energetic or too indolent, of the archeus, and then it occasions particular accidents relative to each of the functions. Paracelsus enumerates a great number of diseases of the organs, which may be explained by that one cause, and affirms that the profession of medicine would be infinitely more useful if medical men would endeavour to discover the tartar before they tried to explain the affections. Paracelsus points out, also, the means by which we can distinguish the presence of tartar in urine, for this is necessary not merely to inspect the urine, but to subject it to a chemical analysis. He declaims violently against the ordinary auroscopy. He divides urine into internal and external. The internal comes from the blood, and the external announces the nature of the food and drink which has been employed. To the sediment of urine he gives the new name of alcola, and admits 3 species of it, namely hypostasis, dilvusio, and sedimen. The first is connected with the stomach, the second with the liver, and the third with the kidneys, and tartar predominates in all the 3. The Kabbalah constantly directs Paracelsus in his Therapeutics and Materia Medica. As all terrestrial things have their image in the region of the stars, and as diseases depend on the influence of the stars, we have nothing more to do, in order to obtain a certain cure for these diseases, than to discover, by means of the Kabbalah, the harmony of the constellations. Gold is a specific against all diseases of the heart, because, in the mystic scale, it is in harmony with that viscous. The liquor of the moon and crystal cure the diseases of the brain. The liquor, alkahest, and cherry are efficacious against those of the liver. When we employ vegetable substances, we must consider their harmony with the constellations, and their magical harmony with the parts of the body and the diseases. Each star drawing, by a sort of magical virtue, the plant for which it has an affinity, and imparting to it its activity. So that plants are a kind of sublunary stars. To discover the virtues of plants, we must study their anatomy and chiromancy, for the leaves are their hands, and the lines observable on them enable us to appreciate the virtues which they possess. Thus, the anatomy of the chelidonium shows us that it is a remedy for jaundice. These are the celebrated signatures by means which we deduce the virtues of vegetables, and the medicines of analogy which they present in relation to their form. Medicines, like women, are known by the forms which they affect. He who calls in question this principle accuses the divinity of falsehood, the infinite wisdom of whom has contrived these external characters to bring the study of them more upon a level with the weakness of the human understanding. On the corolla of the euphrasia there is a black dot. From this we may conclude that it furnishes an excellent remedy against all the diseases of the eye. The lizard has the colour of malignant ulcers, and that of the carbuncle. This points out the efficacy which that animal possesses as a remedy. These signatures were exceedingly convenient for the fanatics, since they saved them the trouble of studying the medical virtues of plants, but enabled them to decide the subject a priori. Paracelsus acted very considerately when he ascribed these virtues principally to the stars, and affirmed that the observation of favourable constellations is an indispensable condition in the employment of these medicines. These remedies are subjected to the will of the stars, and directed by them, You ought therefore to wait till heaven is favourable before ordering a medicine. Paracelsus considered all the effects of plants as specifics, and the use of them as secrets. The same notions explain the eulogy which he bestowed on the elixir of long life, and upon all the means which he employed to prolong the term of existence. He believed that these methods, which contain the materia prima, serve to repair the constant waste of matter in the human body. He was acquainted, he says, with 4 of these arcana, to which he applied the mystic terms mercury of life, philosopher's stone, etc. The polygonum persicaria was an infallible specific against all the effects of magic. The method of using it is, to apply it to the suffering part and then to bury it in the earth. It draws out the malignant spirits like a magnet, and it is buried to prevent these malignant spirits from making their escape. The Reformation of Paracelsus had the great advantage of representing chemistry as an indispensable art in the preparation of medicines. The disgusting decoctions and useless syrups gave place to tinctures, essences, and extracts. Paracelsus says expressly that the true use of chemistry is to prepare medicines, not to make gold. He takes that opportunity declaiming against cooks and innkeepers who drown medicines in soup, and thus destroy all their properties. He blames medical men for prescribing simples or mixtures of simples, and affirms that the object should always be to extract the quintessence of each substance, and he describes at length the method of extracting this quintessence. But he was very little scrupulous about the substances from which this quintessence was to be extracted. The heart of a hare, the bones of a hare, the bone of the heart of a stag, mother of pearl, coral, and various other bodies may, he says, be used indiscriminately to furnish a quintessence capable of curing some of the most grievous diseases. Paracelsus combats with peculiar energy the method of cure employed by the disciples of Galen, directed solely against the predominating humours and the elementary qualities. He blames them for attempting to correct the action of their medicines by the addition of useless ingredients. Fire and chemistry, he affirmed, are the sole correctives. It was Paracelsus that first introduced tin as a remedy for worms, though his mode of employing it was not good. I have been thus particular in pointing out the philosophical and medical opinions of Paracelsus, because they were productive of such important consequences by setting medical men free from the slavish deference which they have been accustomed to pay to the dogmas of Galen and Avicenna. But it was the high rank to which he raised chemistry, by making a knowledge of it indispensable to all medical men, and by insisting that the great importance of chemistry did not consist in the formation of gold, but in the preparation of medicines, that rendered the era of Paracelsus so important in the history of chemistry. For after his time, the art of chemistry was cultivated by the medical men in general. It became a necessary part of their education, and began to be taught in colleges and medical schools. The object of chemistry came to be, not to discover the philosopher's stone, but to prepare medicines. And a great number of new medicines, both from the mineral and vegetable kingdoms, some of more, some of less consequence, soon issued from the laboratories of the chemical physicians. There can be little doubt that many chemical preparations were either first introduced into medicine by Paracelsus, or at least were first openly prescribed by him, though from the nature of his writings, and the secrecy in which he endeavoured to keep his most valuable remedies, it is not easy to point out what these remedies were. Mercury is said to have been employed in medicine by Basil Valentine, but it was Paracelsus who first used it openly as a cure for the venereal disease, and who drew general attention to it by his encomium on its medical virtues, and by the eclat of the cures which he performed by means of it, after all the Galenical prescriptions of the schools had been tried in vain. He ascertained that alum contains, united to an acid, not a metallic oxide but an earth. He mentions metallic arsenic, but there is some reason for believing that this metal was known to Geber and the Arabian physicians. Zinc is mentioned by him, and likewise bismuth, as substances not truly metallic, but approaching to metals in their properties, for malleability and ductility were considered by him as essential to the metals. Footnote: Philosophiae, Tract 4, De Mineralibus, Opera Paracelsi 2, 282. Quando ergo hoc modo metalla fiunt et producentur, dum silicet verus metallicus fluxus ec ductilitas offeritur et in sata metalla distributor, residentia quendam manet ineres, instar fetum trium primorum. Ex hat nescitur zinetum quod et metallum est et non est, sic et bisemutum et huic similia alia partem fluida, partem ductilia sunt. Zinetum maxima ex parte spuria subolis ex et cupro et bisemutum destano, ex hici duobus omnium pluremae fascis et remanentae in aeres fiunt. End of footnote. I cannot be sure of any other chemical fact which appears in Paracelsus, and which was not known before his time. The use of sal ammoniac in subliming several metallic calces was familiar to him, but it had long ago been explained by Geber. It is clear also that Geber was acquainted with aqua regia, and that he employed it to dissolve gold. Paracelsus's reputation as a chemist, therefore, depends not upon any discoveries which he actually made, but upon the great importance which he attached to the knowledge of it, and to his making an acquaintance with chemistry an indispensable requisite of a medical education. End of section 17. Read by Paul King, pjk.scripts.mit.edu/pkj. Section 18 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, Ontario. pjk.scripts.mit.edu/pkj. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 4, of the Progress of Chemistry under Paracelsus and his Disciples, Part 4. Paracelsus, as the father of a new system of medicine, the object of which was to draw chemistry out of that state of obscurity and degradation into which it had been plunged, and to give it the charge of the preparation of medicine, and presiding over the whole healing art, deserved a particular notice. And I have even endeavoured at some length to lay his system of opinions, absurd as it is, before the reader. But the same attention is not due to the herd of followers who adopted his absurdities and even carried them, if possible, still further than their master. At the same time there are one or two particulars connected with the Paracelsian sect which it would be improper to omit. The most celebrated of his followers was Leonhard Thurneysser zum Thurn, who was born in 1530 at Basel, where his father was a goldsmith. His life, like that of his master, was checkered with very extraordinary vicissitudes. In 1560 he was sent to Scotland to examine the lead mines in that country. In 1558 he commenced miner and sulphur extractor at Terrens-on-the-Inn, and was so successful that he acquired a great reputation. He had turned his attention to medicine on the Paracelsian plan, and in 1568 made himself distinguished by several important cures which he performed. In 1570 he published his Quinta Essentia with wooden cuts in Munster. From thence he went to Frankfort on the Oder and published his Piso, a work with treats of waters, rivers, and springs. John George, Elector of Brandenburg, was at the time in Frankfort, and was informed that the treatise of Thurneysser pointed to the existence of a great deal of riches in the March of Brandenburg, till that time unknown. His courtiers, who were anxious to establish mines in their possessions, united in recommending the author. He was consulted about a disease under which the wife of the elector was labouring, and having performed a cure, he was immediately named physician to this prince. He turned the situation to the best account. He sold Spanish white and other cosmetics to the ladies of the court, and instead of the disgusting decoctions of the Galenists, he administered the remedies of Paracelsus under the pompous titles of tincture of gold, magistry of the sun, potable gold, etc. By these methods he succeeded in amassing a prodigious fortune, but was not fortunate enough to be able to keep it. Gaspard Hoffmann, professor at Frankfurt, a well-informed and enlightened man, published a treatise, the object of which was to expose the extravagant pretensions and ridiculous ignorance of Thurneysser. This book drew the attention of the courtiers and opened the eyes of the elector. Thurneysser lost much of his reputation, and the methods by which he attempted to bolster himself up served only to sink him still lower in the estimation of men of sense. Among other things, he gave out that he was the possessor of a devil, which he carried about with him in a bottle. This pretended devil was nothing else than a scorpion, preserved in a phial of oil. The trick was discovered, and the usual consequences followed. He lost a process with his wife, from whom he was separated. This deprived him of the greatest part of his fortune. In 1584 he fled to Italy, where he occupied himself with the transmutation of metals, and he died at Cologne in 1595. Thurneysser extols Paracelsus as the only true physician that ever existed. His quintessence is written in verse. In the first book, The Secret is the speaker. He is represented with a padlock in his mouth, a key in his hand, and seated on a coffer in a chamber, the windows of which are shut. The personage teaches that all things are composed of salt, sulphur, and mercury, or of earth, air, and water, and consequently that fire excluded from the number of the elements. We must search for the secret in the Bible, and then in the stars and the spirits. In the second book, Alchymy is the speaker. She points out the mode of performing the process, and says that to endeavour to fix volatile substances is the same thing as to endeavour to trace white letters on the wall with a piece of charcoal. She prohibits all long processes, because God created the world in 6 days. His method of judging the disease from the urine of the patient deserves to be mentioned. He distilled the urine and fixed to the receiver a tube furnished with a scale, the degrees of which consisted of all parts of the body. The phenomena which he observed during the distillation of the urine enabled him to draw inferences respecting the state of all these different organs. I pass over Bodstein, Taxis, and Dorn, who distinguish themselves as the partisans of Paracelsus. Dorn derived the whole of chemistry from the first chapter of Genesis, the words of which he explained in alchemical sense. These words in particular, "And God made the firmament, and divided the waters which were under the firmament from the waters which were above the firmament," appeared to him to be an account of the great work. Severinus, physician to the king of Denmark and canon of Roskilde, was also a celebrated partisan of Paracelsus, but his writings do not show either that knowledge or stretch of thought which would enable us to account for the reputation which he acquired and enjoyed. There were very few partisans of Paracelsus out of Germany. The most celebrated of his followers among the French was Joseph de Chesne, better known by the name of Quercetanus, who was physician to Henry IV. He was a native of Gascony, and drew many enemies upon himself by his arrogant and overbearing conduct. He pretended to be acquainted with the method of making gold. He was a thoroughgoing Paracelsian. He affirmed that diseases, like plants, spring from seeds. The word alchemy, according to him, is composed of the two Greek words ius, salt, and chemia, because the great secret is concealed in salt. All bodies are composed of three principles, as God is of three substances. These principles are contained in saltpeter, the salts of sulfur, solid and volatile, and the volatile mercurial salts. He who possesses sal generalis may easily produce the philosophical gold and draw potable gold from the three kingdoms of nature. To prove the possibility of this transmutation, he cites an experiment very often repeated after him, and which some theologians have even employed as analogous to the resurrection of the dead, namely, the faculty which plants have of being produced from their ashes. His Materia Medica is founded on the signatures of plants, which he carries so far as to assert that male plants are more suitable to men, and female plants to women. Sulfuric acid, he says, has a magnetic virtue, in consequence of which it is capable of curing the epilepsy. He recommends the Magisterium Crani Humani as an excellent medicine and boasts much of the virtues of antimony. Duchesne was opposed by Riolanus, who attacked chemical remedies with much bitterness. The medical faculty of Paris took up the cause of the Galenists with much zeal, and prohibited their fellows and licentiates from using any chemical medicines whatever. He had to sustain a dispute with Aubert relative to the origin and the transmutation of metals. Fenot came to the assistance of Aubert, and affirmed that gold possesses no medical properties whatever, that crab's eyes are of no use when administered in intermittents, and that the laudanum of Paracelsus, being an opiate, is in reality hurtful instead of being beneficial. The decree of the medical faculty of Paris which placed antimony among the poisons, and which occasioned that of the Parliament of Paris, was composed by Simon Pietre, an elder, a man of great erudition, and the most unimpeachable probity. Had it been literally obeyed, it would have occasioned very violent proceedings, because chemical remedies, as they act more promptly and with greater energy, were getting daily into more general use. In 1603 the celebrated Theodore Turquet de Mayenne was prosecuted, because, in spite of the prohibition, he had sold antimonial preparations. The decree of the faculty against him exhibits a remarkable proof of the bigotry and intolerance of the times. Footnote. It was as follows. Collegium Medicorum in Academia Parisiensi legitime congregatum audita renunciatione censorum quibus demandata erat provincia examinande apologium sub nomine mereni terqueti editam. Ipsam unanimi consensu damnat, tanquam famosam libellum mendacibus convicis impudentibus calumnis refrutum. Coina nisi ab homine imperito impudenti telmulento e furioso profitiari potuerunt. Ipsum turquetum indignum judicat, qui usque medicinam faciat propter terminatim impudentium et veri medicinae ignorantiam. Omnis vero medicus, qui ubique gentium et locorum medicinam exercent horator ut ipsum turquetum similaque hominem et opinionum prudenta, assesisque fidibus acceant et id Hippocrates ac Galeni doctrina constantis permanent, et prohibuit nequis ex hoc mediocrum Parisensium ordine cum turqueto aeque similibus medica consilia iniat. Qui sequis fercit scholae ornamentos et academiae privilegius previbitur, et de regimentum numero expungentur. Datum luminati in scholis superiobis zi quinque Decembris annos saliotis, sedecem tribus. End of footnote. However, Turquet does not seem to have been molested notwithstanding this decree. He ceased indeed to be professor of chemistry, but continued to practice medicine as formerly, and 2 members of the faculty, Seguin and Akakia, even wrote an apology for him. At last he went to England, whither he had been invited, to accept an honourable appointment. The mystical doctrines of Paracelsus are supposed to have given origin to the sect of the Rosicrucians, concerning which so much has been written, so little certain is known. It is not at all unlikely that the greatest part, if not the whole, that has been stated about the antiquity and extent and importance of this sect is mere fiction, and that the origin of the whole was nothing else than a ludicrous performance of Valentine André, an ecclesiastic of Calwy, in the country of Württemberg, a man of much learning, genius, and philanthropy. From his life, written by himself and preserved in the library of Wolfenbüttel, we learn that in the year 1603 he drew up the celebrated Noci Chimique of Christian Rosenkreutz in order to counteract the alchemistical and theosophistical dogmas so common at that period. He was unable to restrain his risible faculties when he saw this lubridium juvenilis ingenii adopted as a true history, while he meant it merely as a satire. It is believed that the Fama Fraternitalis is a production of this ecclesiastic, and that he published it in order to correct the chemists and enthusiasts of the time. He himself was called André, Knight of the Rose Cross, Rosicrucius, because he had engraven on his seal a cross with 4 roses. It is true that André instituted in 1620 a Fraternitas Christiana, but with quite other views than those which are supposed to have actuated the Rosicrucians. His object was to correct the religious opinions of the times, and to separate Christian theology from scholastic controversies, with which it had been unhappily intermixed. He himself, in different parts of his writings, distinguishes carefully between the Rosicrucians and his own society, and amuses himself with the credulity of the German theosophists, who adopted so readily his fiction for a series of truths. It would appear, therefore, that this secret order of Rosicrucians, notwithstanding the brilliant origin assigned to it, really owes its birth to the pleasantry of a clergyman of Württemberg, who endeavoured by that means to set bounds to the chimeras of theosophy, but who unfortunately only increased still more the adherents of this absurd science. A crowd of enthusiasts found it too advantageous to propagate the principles of the Rosicrucians not to endeavour to unite them into a sect. Valentine Weigel, a fanatical preacher at Zschopau, near Chemnitz, left at his death a prodigious number of followers who were already Rosicrucians, without bearing the name. Aegius Gutmann of Sobia was equally a Rosicrucian, without bearing the name. He condemned all pagan medicines, and affirmed that he possessed the universal remedy which ennobles man, cures all diseases, and gives man the power of fabricating gold. To fly in the air, to transmute all metals, and to know all the sciences, says he, nothing is more requisite than faith. Oswald Crolius of Hesse must also take his station in this honourable fraternity of enthusiasts. He was physician to the Prince of Anhalt, and afterwards a counsellor of the Emperor Rodolphus II. The introduction to his Basilica Chymica contains a short but exact epitome of the opinions of Paracelsus. It is not worth while to give the reader a notion of his own opinions, which are quite as absurd and unintelligible as those of Paracelsus and his followers. As a preparer of chemical medicines he deserves more credit. Antimonium diaphoreticum was a favourite preparation of his, and so was sulphate of potash, which was known at the time by the name Specificum purgans Paracelsi. He knew chloride of silver well, and first gave it the name luna cornea, or horn silver. Fulminating gold was known to him, and called by him aurum volatile. This is the place to mention Andrew Libavius of Halle in Saxony, where he was a physician and a professor in the gymnasium of Coburg, who is one of the most successful opponents of the school of Paracelsus, and whose writings do him much credit. As a chemist, he deserves perhaps to occupy a higher rank than any of his contemporaries. He was, it is true, a believer in the possibility of transmuting metals, and boasted of the wonderful powers of aurum potibile, but he always distinguishes between rational alchemy and the mental alchemy of Paracelsus. He separated with great care chemistry from the reveries of the theosophists, and stands at the head of those who opposed most successfully the progress of superstition and fanaticism, which was making such an overwhelming progress in his time. His writings are very numerous and various, and were collected and published at Frankfurt in 1615 in 3 folio volumes, under the title Opera Omnia Medico-Chymia. Libavius himself died in 1616. It would occupy more space than we have room for, to attempt an abstract of his very multifarious works. A few observations will be sufficient. He wrote no fewer than 5 different tracts to expose the quackery of George Armwald, who had boasted that he was in possession of a panacea, by means of which he was enabled to perform the most wonderful cures, of which he was in the habit of selling to his patients at an enormous price. Libavius showed that this boasted panacea was nothing else than cinnabar, which neither possessed the virtues ascribed to it by Armwald, nor deserved to be purchased at so high a price. He entered also into a controversy with Crollius, and exposed his fanatical and absurd opinions. He engaged likewise in a dispute with Henning Scheunemann, a physician in Bamberg, who was a Rosicrucian and, like the rest of his brethren, profoundly ignorant not merely of all science, but even of philology. The expressions of Scheunemann are so obscure that we learn more of his opinions from Libavius than from his own writings. He divides the internal nature of man into 7 different degrees, from the 7 changes it undergoes. These are combustion, sublimation, dissolution, putrefaction, distillation, coagulation, and tincture. He gives us likewise an account of 10 modifications which the elements undergo, but as they are quite unintelligible, it is not worth while to state them. Libavius had the patience to analyze and expose all these gallimantias. Libavius's system of chemistry, entitled Alchymia e dispersis passim optimorum octium veterum et recentiorum exemplis potissimum, tum etiam preceptis quibusdum operose collecta, adhibitisque ratione experientia quanta potuit esse methodo accurate explicata et in integrum corpus redacta, accesserunt tractati nonnulli physici chimici item methodistici. Frankfurt, 1595, folio 1597, 4-2, is really an excellent book, considering the period in which it was written, and deserves the attention of every person who is interested in the history of chemistry. I shall notice some of the most remarkable chemical facts which occur in Libavius, and which I have not observed in any preceding writer. Who the actual discoverer of these facts really was, it is impossible to say, in consequence of the secrecy which at the time was affected, and the obscure terms in which the chemical facts are in general stated. He was aware that the fumes of sulphur have the property of blackening white lead. He was in the habit of purifying cinnabar by means of arsenic and oxide of lead. He knew the method of giving glass a red color by means of gold or its oxide, and was aware of the method of making artificial gems, such as ruby, topaz, hyacinth, garnet, balas, by tinging glass by means of metallic oxides. He points out fluorspar as an excellent flux for various metals and their oxides. He knew that when metals were fused along with alkaline bodies, a certain portion of them was converted into slags, and this portion he endeavoured to recover by the addition of iron filings. He was aware of the mode of acidifying sulphur by means of nitric acid. He knew that camphor is soluble in nitric acid and forms with it a kind of oil. Of the perchloride of tin he was undoubtedly the discoverer, as it has continued ever since his time to pass by his name, namely fuming liquor of Libavius. He was aware that alcohol or spirits could be obtained by distilling the fermented juice of a great variety of sweet fruits. He procured sulphuric acid by the distillation of alum and sulphate of iron, as Geber had done long before his time, but he determined the nature of the acid with more care than had been done, and showed that it was the same as that obtained by the combustion of sulphur along with saltpetre. To him, therefore, in some measure, are we indebted for the process of preparing sulphuric acid, which is at present practised by manufacturers. Libavius found a successor in Angelus Sala of Vicenza, a physician to the Duke of Mecklenburg-Schwerin, worthy of his enlightened views and indefatigable exertions to oppose the torrent of fanaticism which threatened to overwhelm all Europe. Sala was still more addicted to chemical remedies than Libavius himself, and he had abjured a multiple of prejudices which had distinguished the school of Paracelsus. He discarded aurum potabile, and considered fulminating gold as the only remedy of that metal that deserved to be prescribed by medical men. He treated the notion of the existence of a universal remedy with contempt. He described sulphuret of gold and glass of antimony with a good deal of precision. He recommended sulphuric acid as an excellent remedy, and showed that it might be formed indifferently from sulphur, or by distilling blue vitriol or green vitriol. He affirmed that the essential salts obtained from plants had not the same virtues as the plants from which they are obtained. He showed that sal ammoniac is a compound of muriatic acid and ammonia. To him, therefore, we are indebted for the first accurate mention of ammonia. It could not but have been noticed before by chemists, as it is procured with so much ease by the distillation of animal substances. But Sala is the first person who seems to have examined it with attention, and to have recognized its peculiar properties, and the readiness with which it saturates the different acids. He showed that iron has the property of precipitating copper from acid solutions. He points out also various precipitations of metals by other metals. He seems to have been acquainted with calomel, and to have been aware of at least some of its medical properties. He says that fulminating gold loses its fulminating property when mixed with its own weight of sulphur, and the sulphur is burnt off it. Many other curious chemical facts occur in his writings, with which it would be too tedious to particularize here. His works were collected and published in a quarto volume at Frankfurt in 1647, under the title of Opera Medico-Chymia quae extant omnia. There was another edition in the same place in 1682, and an edition was published in Rome in 1650. End of Part 18. Read by Paul King, Mississauga, Ontario. pjk.scripps.mit.edu/pkj. Section 19 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, Ontario. pjk.scripps.mit.edu/pkj. The History of Chemistry by Thomas Thomson, Volume 1, Chapter 5. Of Van Helmont and the Iatrochemists, Part 1. Paracelsus first raised the dignity of chemistry by pointing out the necessity of it for medical men, and by showing the superiority of chemical medicines over the disgusting decoctions of the Galenists. Libavius and Angelus Sala had carefully separated chemistry from the fanatical opinions of the followers of Paracelsus and the Rosicrucians. But matters were not doomed to remain in this state. Chemistry underwent a new revolution at this period, which shook the spagyrical system to its foundation, substituted other principles, and gave to medicine an aspect entirely new. This revolution was in great measure due to the labours of Van Helmont. John Baptist Van Helmont was a gentleman of Brabant and the Lord of Merode, of Royenbock, Oorschot, and of Pellins. He was born in Brussels in 1577, and studied scholastic philosophy in Louvain till the age of 17. After having finished his humanity, as it was termed, he ought, according to the usage of the place, have taken the degree of Master of Arts, but having reflected on the futility of these ceremonies, he resolved never to solicit any academical honour. He next associated himself to the Jesuits, who then delivered courses of philosophy at Louvain, to the great displeasure of the professors of that city. One of the most celebrated of the Jesuits, Martin del Rio, even taught him magic. But Van Helmont was disappointed in his expectations. Instead of that true wisdom which he hoped to acquire, he met with nothing but scholastic dialectics, with all its usual subtleties. He was no better satisfied with the doctrines of the Stoics, who taught him his own weakness and misery. At last the works of Thomas à Kempis and John Taulerus fell into his hands. These sacred books of mysticism attracted his attention. He thought that he perceived that wisdom is the gift of the Supreme Being, that it must be obtained by prayer, and that we must renounce our own will if we wish to participate in the influence of the divine grace. From this moment he imitated Jesus Christ in his humility. He abandoned all his property to his sister, renouncing the privileges of his birth, and laying aside the rank which he had hitherto occupied in society. It was not long before he reaped the fruit of these abnegations. A genius appeared to him in all the important circumstances of his life. In the year 1633 his own soul appeared to him under the figure of a resplendent crystal. The desire which he had of imitating in every respect the conduct of Christ suggested to him that the idea of practicing medicine as a work of charity and benevolence. He began, as was the custom of the time, by studying the art of healing in the writings of the ancients. He read the works of Hippocrates and Galen with avidity, and made himself so well acquainted with their opinions that he astonished all the medical men by the profundity of his knowledge. But as his taste for mysticism was insatiable, he soon became disgusted with the writings of the Greeks. An accident led him to abandon them forever. Happening to take up the glove of a young girl afflicted with the itch, he caught that disagreeable disease. The Galenists whom he consulted attributed to the combustion of the bile and the saline state of the phlegm. They prescribed a course of purgatives which weakened him considerably without effecting a cure. This circumstance disgusted him with the system of the humorists, and led him to form the resolution of reforming medicine, as Paracelsus had done. The works of this reformer, which he read with attention, awakened in him a spirit of reformation, but did not satisfy him, because his knowledge being much greater than that of Paracelsus, he could not avoid despising the disgusting egotism and the ridiculous ignorance of that fanatic. Though he had already refused to canonicate, he took the degree of Doctor of Medicine in 1599, and afterwards travelled through the greatest part of France and Italy, and he assures us that during his travels he performed a great number of cures. On his return he married a rich Brabantine lady by whom he had several children, among others a son, afterwards celebrated under the name of Francis Mercurius, who edited his father's works, and who went a good deal further than his father had done in all branches of theosophy. Van Helmont passed the rest of his life on his estate at Vilvoorde, almost constantly occupied with the process of his laboratory. He died in the year 1644 on the 13th of December at 6 o'clock in the evening, after having nearly reached the age of 67 years. The system of Van Helmont had for its basis the opinions of the spiritualists. He arranged even the influence of evil genii, the efforts of sorcerers, and the power of magicians among the causes which produce diseases. The Archeus of Paracelsus constituted one of the capital points of his theory, but he ascribed to it a more substantial nature than Paracelsus had done. This Archeus is independent of the elements. It has no form. For form constitutes the object of generation or of production. These ideas are obviously borrowed from the ancients. The form of Aristotle is not the morphe, but the energia, the power of acting, which matter does not possess. The Archeus draws all the corpuscles of matter to the aid of fermentation. There are, properly speaking, only two causes of things, the cause of ex qua and the cause of per quam. The first of these causes is water. Van Helmont considered water the true principle of everything which exists, and he brought forward very specious arguments in favour of his opinion, drawn both from the animal and the vegetable kingdom. The reader will find his arguments on the subject in his treatise entitled Complexionum Atque Mistionum Elementalium Figmentum. Footnote: J. B. Van Helmont, Opera Omnia, page 100. The edition which I quote was printed at Frankfurt in 1682 at the expense of John Justus Erythropoulos in a very thick quarto volume. End of footnote. The only one of his experiments that, in the present state of our knowledge, possess much plausibility is the following. He took a large earthen vessel and put into it 200 pounds of earth, previously dried in an oven. This earth he moistened with rainwater, and planted in it a willow which weighed 5 pounds. After an interval of 5 years, he pulled up his willow and found that its weight amounted to 169 pounds, and about 3 ounces. During these 5 years the earth in the pot was duly watered with rain or distilled water. To prevent the earth in which the willow grew from being mixed with new earth blown upon it by the winds, the pot was covered with tin plate, and pierced with a great number of holes to admit the air freely. The leaves which fell every autumn during the vegetation of the willow in the pot were not reckoned into 169 pounds 3 ounces. The earth in the pot, again being dried in the oven, was found to have lost about 2 ounces of its original weight. Thus 164 pounds of wood, bark, roots, etc. were produced from water alone. This and several other experiments which it is needless to state, satisfied him that all vegetable substances are produced from water alone. He takes it for granted that fish live, ultimately at least, on water alone. But they contain almost all of the peculiar animal substances that exist in the animal kingdom. Hence he concludes that animal substances are derived also from pure water. His reasoning with respect to sulphur, glass, stone, metals, etc., all of which he thinks may ultimately be resolved into water, is not so satisfactory. Water produces elementary earth or pure quartz. But this elementary earth does not enter into the composition of organic bodies. Van Helmont excludes fire from the number of elements, because it is not a substance, nor even the essential form of a substance. The matter of fire is compound, and differs entirely from the matter of light. Water gives origin also to the 3 chemical principles, salt, sulphur, and mercury, which cannot be considered as elements or active principles. I do not see clearly how he gets rid of air, for he says that though water may be elevated in the form of vapour, yet that these vapours are no more air than the dust of marble is water. According to Van Helmont, a particular disposition of matter, or a particular mixture of that matter, is not necessary for the formation of a body. The archeus, by its sole power, draws all bodies from water, when the ferment exists. This ferment, in its quality of a mean which determines the action of the archeus, is not a formal being. It can neither be called a substance nor an accident. It pre-exists the seed which is developed by it, and which contains in itself a second ferment of the seed, the product of the first. The ferment exhales an odour which attracts the generating spirit of the archeus. The spirit consists in an aura vitalis, and it creates the bodies of nature in its own image, after its own idea. It is the true foundation of life, and of all the functions of organized bodies. It disappears only at the instant of death to produce a new creation of the body, which enters then for the second time into fermentation. The seed then is not indispensable to enable an animal to propagate its species. It is merely necessary that the archeus should act upon a suitable ferment. Animals produced in this manner are as perfect as those which spring from eggs. When water as an element ferments, it develops a vapour to which Van Helmont gave the name of gas, and which he endeavours to distinguish from air. This gas contains the chemical principles of the body from which it escapes in aerial form by the impulse of the archeus. It is a substance intermediate between spirit and matter, the principal action of life, and of generation of all bodies, for its production is the first result of the action of the vital spirit on the torpid ferment, and it may be compared to the chaos of the ancients. The term gas, now in common use among chemists, and applied by them to all elastic fluids which differ in their properties from common air, was first employed by Van Helmont, and it is evident from different parts of his writings that he was aware that different species of gas exist. His gas sylvestre was evidently our carbonic acid gas, for he says that it is evolved during the fermentation of wine and beer, that it is formed when the charcoal is burnt in air, and that it exists in the Grotto del Cane. He was aware that this gas extinguishes a lighted candle, but he says that the gases from dung and those formed in the large intestines when passed through a candle catch fire and exhibit a variety of colors like the rainbow. To these combustible gases he gave the names of gas pingue, gas siccum, gas fuliginosum, or endemicum. Sal ammoniac, he says, may be distilled alone without danger, and so may aqua fortis, aqua cressulca. But if they be mixed together, so much gas sylvestre is produced that the vessels employed, however strong, will burst asunder unless an opening be left for the escape of this gas. In the same way, cream of tartar cannot be distilled in close vessels without breaking them into pieces. An opening must be left for the escape of the gas sylvestre, which is generated in such abundance. He says also that when carbonate of lime is dissolved in distilled vinegar, or silver in nitric acid, abundance of gas sylvestre is extracted. From these, and many other passages which might be quoted, it is evident that Van Helmont was aware of the evolution of gas during the solution of carbonates and metals in acids, and during the distillation of various animal and vegetable substances, that he had anticipated the experiments made so many years after by Dr. Hales, and for which that philosopher got so much credit. But it would be going too far to say, as some have done, that Van Helmont knew accurately the differences which characterized the different gases which he produced, or indeed that he distinguished accurately between them. For it is evident from the passages quoted and from many others which occur in his treatise De Flatibus that carbonic acid, protoxide of azote, and deutoxide of azote, and probably also muriatic acid gas, were all considered by him as constituting one and the same gas. How indeed could he distinguish between the different gases when he was not acquainted with the method of collecting them or of determining their properties? These observations of Van Helmont, then, though they do him much credit and show how far his chemical knowledge was superior to that of the age in which he lived, take nothing from the merit or the credit of those illustrious chemists who in the latter half of the 18th century devoted themselves to the investigations of this part of chemistry, at that time attended with much difficulty, but intimately connected with the subsequent progress which the science has made. Van Helmont was aware also that the bulk of air is diminished when bodies are burnt in it. He considered respiration to be necessary in this way. The air was drawn into the blood by the pulmonary arteries and veins, and occasioned a fermentation in it requisite for the continuance of life. Gas, according to Van Helmont, has an affinity with the principle of the movement of the stars, to which he gave the name of Blas. It had, he supposed, much influence on all sublunary bodies. He admitted in the ferment which gives birth to plants, a substance which, after the example of Paracelsus, he called Pessas, and to the metallic ferment he gave the name of Bur. Footnote. In his Magnum Optet, section 39, page 151, he gives an account of the origin of the metals in the earth, and in that section there is a description of Bur, which to those who are anxious to understand the idea of the author on this subject may consult. End of footnote. The archeus of Van Helmont, like that of Paracelsus, has its seat in the stomach. It is the same thing as the sentient soul. This notion of the nature and seat of the archeus was founded on the following experiment. He swallowed a quantity of aconitum. In 2 hours he experienced the most disagreeable sensation in his stomach. His feeling and understanding seemed to be concentrated in that organ, for he had no longer the free use of his mental faculties. This feeling induced him to place the seat of understanding in the stomach, of volition in the heart, and of memory in the brain. The faculty of desire, to which the ancients had assigned the liver and its organ, he placed in the spleen. What confirmed him still more in the idea that the stomach is the seat of the soul is the fact that life sometimes continues after the destruction of the brain, but never, he alleges, after that of the stomach. The sentient soul acts constantly by means of the vital spirits, which are of a resplendent nature, and the nerves serve merely to moisten these spirits which constitute the mediums of sensation. By virtue of the archeus, man is much nearer to the realm of spirits and the father of all the genii than to the world. He thinks that Paracelsus's constant comparison of the human body with the world is absurd. Yet Van Helmont, at least in his youth, was a believer in magnetism, which he employed as a method of explaining the effect of sympathy. The archeus exercises the greatest influence on digestion, and he had chiefly the stomach and spleen under his superintendence. Those two organs form a duumvirate in the body, for the stomach cannot act alone and without the concurrence of the spleen. Digestion is produced by means of an acid liquor, which dissolves the food under the superintendence of the archeus. Van Helmont assures us that he had himself tasted this acid liquor in the stomach of birds. Heat, strictly speaking, does not favour digestion, for we see no increase of the digestive powers during the most ardent fever, nor are the powers of digestion wanting in the fishes, although they want the animal heat which is requisite for the mammiferous animals. Certain birds even digest fragments of glass, which certainly simple heat would not enable them to do. The pylorus is in some measure the director of digestion. It acts by a peculiar and immaterial power, in virtue of a blas, and not as a muscle. It opens and shuts the stomach according to the orders of the archeus. It is in it, therefore, that the causes of derangement of digestion must be sought for. The duumvirate just spoken of is the cause of natural sleep, which does not belong to the soul as far as it resides in the stomach. Sleep is a natural action, and one of the first vital actions. Hence the reason why the embryo sleeps without ceasing. At any rate, it is not true that sleep is owing to vapours which mount to the brain. During sleep, the soul is naturally occupied, and it is then that the deity approaches most intimately to man. Accordingly, Van Helmont informs us that he received in dreams the revelation of several secrets, which he could not have learnt otherwise. The duumvirate operates the first digestion, of which Van Helmont enumerates 6 different species. When the acid which is prepared for digestion passes into the duodenum, it is neutralized by the bile of the gallbladder. This constitutes a second digestion. To the bile of the gallbladder Van Helmont gave the name of fel, and he carefully distinguished it from the biliary principle in the mass of the blood. This last he called the bile. The fel is not an excrementous matter, but a humour necessary for life, a true vital balsam. Van Helmont endeavoured to show by various experiments that it is not bitter. The third digestion takes place in the vessels of the mesentery, into which the gallbladder sends the prepared fluid. The fourth digestion is operated in the heart, where the red blood becomes more yellow and more volatile by the addition of the vital spirits. This is owing to the passage of the vital spirit from the posterior and anterior ventricle through the pores of the septum. At the same time the pulse is produced, which of itself develops heat, but does not regulate it in any manner, as the ancients pretended that it did. The fifth digestion consists in the conversion of the arterial blood into vital spirit. It takes place principally in the brain, but is produced also throughout all the body. The sixth digestion consists in the elaboration of the nutritive principle in each member, where the archeus prepares its own nourishment by means of the vital spirits. Thus there are 6 digestions. The number 7 has been chosen by nature for a state of repose. End of part 19. Read by Paul King. Mississauga, Ontario. pjk.scripts.mit.edu/pkj. Section 20 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, Ontario. pjk.scripts.mit.edu/pkj. The History of Chemistry by Thomas Thomson. Volume 1, Chapter 5. Part 2 of Van Helmont and the Iatrochemists. From the preceding sketch of the physiology of Van Helmont, it is evident that he paid little or no regard to the structure of the parts in explaining the functions. In his pathology we find the same passion for spiritualism. He admitted indeed the importance of anatomy, but he regretted that the pathological part of that science had been so little cultivated. As the archeus is the foundation of life and of all the functions, it is plain that the diseases can neither be derived from the 4 cardinal humours nor from the disposition or the action of opposite things. The proximate cause of diseases must be sought for in the sufferings, the anger, the fear, and the other affections of the archeus, and their remote cause may be considered as the ideal seed of the archeus. Disease, in his opinion, is not a negative state or a mere absence of health. It is a substantial and active thing as well as a state of health. Most of the diseases which attack certain parts or members of the body result from an error in the archeus, who sends his ferment from the stomach in which he resides into the other parts of the body. Van Helmont explained in this way not only the epilepsy and madness, but likewise the gout, which does not proceed from a flux and has not its seat in the limb in which the pain resides, but is always owing to an error in the vital spirit. It is true that the character of the gout acts upon the semen in which the vital spirit principally manifests its action, and that in this way diseases are propagated in the act of generation. But if during life, instead of altering the semen, it is carried to the liquid of the articulations, this is a proof of the prudence of nature, which lavishes all her cares on the preservation of the species, and loves better to alter the humours of the articulations than the semen itself. The gout acidifies the liquors of the articulations, which is then coagulated by the acids. The duumvirate is the cause of the apoplexy, vertigo, and particularly of a species of asthma, which Van Helmont calls caducus pulmonalis. Pleurisy is produced in a similar way. The archeus, in a movement of rage, sends acrid acids to the lungs, which occasion an inflammation. Dropsy is also owing to the anger of the archeus, who prevents the secretions of the kidneys from going on in the usual way. Of all the diseases, fever appeared to him most conformable to his notions of the unlimited power of the archeus. The causes of fever are all much more proper to offend the archeus than to alter the structure of parts and the mixture of humours. The cold fit is owing to a state of fear and consternation into which the archeus is thrown, and the hot stage results from his disordered movements. All fevers have their peculiar seat in the duumvirate. Van Helmont was in general much more successful in refuting the scholastic opinions by which the practice of medicine was regulated in his time than in establishing his own. We are struck with the force of his arguments against the Galenical doctrine of fever, and against the influence of the cardinal humours on the different kinds of fever. He refuted no less vehemently the idea of the putridity of the blood, while that liquid circulates in the vessels. Perhaps he carried the opposite doctrine too far, but his opinions have had a good effect upon the subsequent medical theory, and medical men learned from them to make less use of the term putridity. The phrase mixture of humours, not more intelligible, however, came to be substituted for it. Van Helmont's theory of urinary calculi deserves peculiar attention, because it exhibits the germ of a more rational explanation of these concretions than had been previously attempted by physiologists. Van Helmont was aware that Paracelsus, who ascribed these concretions to tartar, had formed an idea of their nature which a careful chemical analysis would immediately refute. He satisfied himself that urinary calculi differ completely from the common stones, and that they do not exist in the food or drink which the calculous person had taken. Tartar, he says, precipitates from wine not as an earth, but as a crystallized salt. In like manner, the natural salt of urine precipitates from that liquid, and gives origin to calculi. We may imitate this natural process by mixing spirit of urine with rectified alcohol. Immediately an alpha alba is precipitated. It is needless to observe that Van Helmont was mistaken in supposing that this alpha was the matter of calculus. Spirit of urine was a strong solution of carbonate of ammonia. The alcohol precipitated this salt, so that his alpha was merely carbonate of ammonia. Nor is there the shadow of evidence that alcohol, as Van Helmont thought it did, ever makes his way into the mass of humours. yet his notion of the origin of calculi is not less accurate, though of course he was ignorant of the chemical nature of the various substances which constitute these calculi. From this reasoning Van Helmont was induced to reject the term tartar employed by Paracelsus. To avoid all false interpretations he substitutes the word dulech to denote the state in which the spirit of urine precipitates and gives origin to these calculous concretions. As all diseases proceeded in his opinion from the archeus, the object of his treatment was to calm the archeus, to stimulate it, and to regulate its movements. To accomplish these objects he relied upon dietetics, and upon acting on the imaginations of his patients. He considered certain words as very efficacious in curing the diseases of the archeus. He admitted the existence of the universal medicine, to which he gave the names of liquor alcahest, ons primum salium, and primus metallus. Mercurials, antimonials, opium, and wine are particularly agreeable to the archeus when in a state of delirium from fever. Among the mercurial preparations he praises what he calls mercurius diaphoreticus as the best. He gives no account of the mode of preparing it, but from some circumstances I think it must have been calomel. He considers it as a sovereign remedy in fevers, dropsies, diseases of the liver, and ulcers of the lungs. He employed the red oxide of mercury as an external application to ulcers. The principal antimonial preparations which he employed were the hydrosulfuret or golden sulphur, and the deutoxide or antimonium diaphoreticum. The last medicine was used in scruple doses, a proof of its great inertness compared with the protoxide of antimony. Opium he considered as a fortifying and calming medicine. It contains an acrid salt and bitter oil, which give it the virtue of putting a stop to the errors of the archeus, when it is sending its acid ferment into the other acid parts of the body. Van Helmont assures us that he wrought many important cures by the employment of wine. Such is a very short statement of the opinions of a man who, notwithstanding his attachment to the fanatical opinions which distinguished the time in which he lived, had the merit of overturning a vast number of errors, both theoretical and practical, and of laying down many principles which, for want of erudition, have been frequently assigned to modern writers. Van Helmont has been frequently placed on the same level with Paracelsus and treated like him with contempt. But his claims upon the medical world are much higher, and his merits infinitely greater. His notions, it is true, were fanatical, but his erudition was great, his understanding excellent, and his industry indefatigable. His writings did not become known until rather a late period, for with the exception of a single tract, they were not published until 1684 by his son after his death. The decided preference given to chemical medicines by Van Helmont and the uses to which he applies chemical theory had a natural tendency to raise chemistry to a higher rank in the eyes of medical men than it had yet reached. But the man to whom the credit of founding the iatrochemical sect is due is Francis de la Bois Sylvius, who was born in the year 1614. While a practitioner of medicine at Amsterdam, he studied with profound attention the system of Van Helmont, and the rival and much more popular theory of Descartes. Upon these he founded his own theory, which in reality contains little entitled to the name of original, notwithstanding the tone in which he speaks of it, and his repeated declarations that he had borrowed from no one. He was appointed professor of the theory and practice of medicine in the University of Leyden, where he taught with such éclat and drew after him so great a number of pupils that Boerhaave alone surpassed him in this respect. It was he that first introduced the practice of giving clinical lectures in the hospitals on the cases treated in the presence of the pupils. This admirable innovation has been productive of much benefit to medicine. He greatly promoted anatomical studies and inspected, himself, a vast number of dead bodies. This is the more remarkable because his own system, like that of Van Helmont, from whom it was borrowed, was quite independent of the structure of the parts. Everything was explained by him according to the principles of chemistry as they were then understood. The celebrity of the university in which he taught, and the vast number of his pupils, contributed to the spread of his theory into every part of the world, and to give it an eclat which is really surprising when we consider it with attention. But he possessed the talents just suited for securing the reception of his opinions by his pupils as infallible oracles, and of being the idol of the university. Yet it is melancholy to be obliged to add that few persons ever more abuse the favours of nature, or the advantages of situation and elocution. To form a clear idea of the principles of this founder of iatrochemistry, we have only to call to mind the ferments of Van Helmont, which constitute the foundation stone of the whole system. We cannot, says he, conceive a single change in the mixture of the humours which is not the consequence of fermentation, and yet he assigns to this fermentation conditions which are scarcely to be found united in the living body. Digestion, in his opinion, is a true fermentation produced by the application of a ferment. Like Van Helmont, he admits a triumvirate, but places it in the humours. The effervescence or fermentation which enabled him to explain most of the functions of the body. Digestion is the result of the mixture of the saliva in which the pancreatic juice and the bile, and the fermentation of these humours. The saliva, as well as the pancreatic juice, contains an acidulous salt easily recognized by the taste. Here Sylvius derives advantage from the experiments of Rayner de Graaf on the pancreatic juice, which he had constantly found acid. Sylvius, who affirmed that the bile contained an alkali united with an oil and a volatile spirit, supposes an effervescence from the union of the alkali of the bile with the acid of the pancreatic juice, and this fermentation he considered as the cause of digestion. By this fermentation the chyle is produced, which is nothing else than the volatile spirit of the food accompanied by an oil and an alkali neutralized by a weak acid. The blood is more than completed, plusquam perfector, in the spleen. It acquires its highest perfection by the addition of a certain quantity of vital spirits. The bile is not drawn from the blood in the liver, but pre-exists in the circulating fluid. It mixes with that fluid anew, to be carried to the heart together with the lymph, equally mixed with the blood, and there it gives the origin to a vital fermentation. In this way the blood becomes a centre of reunion of all the humours and secretions, which mix together or separate, without the solids taking the smallest share of the operations. Indeed, so completely are the solids banished from the system of Sylvius, that he attends to nothing whatever except the humours. The formation and motion of the blood is explained by the fermentation of the oily volatile salt of the bile, and the dulcified acid of the lymph, which develops the vital heat, by which the blood is attenuated and becomes capable of circulating. This vital fire, quite different from ordinary fire, is kept up in its turn by the uniform mixture of the blood. It attenuates the humours not because it is heat, but because it is composed of pyramids. This last notion is obviously borrowed from Descartes, just as the fermentation in the heart as the cause of the motion of the blood reminds us of the opinions of Van Helmont. Sylvius explains the preparation of the vital spirits in the encephalos by distillation, and he finds a great resemblance between the properties and those of spirit of wine. The nerves conduct these spirits to the different parts, and they spread themselves in the substance of the organs to render them sensible. When they insinuate themselves into the glands, the addition of the acid of the blood produces a liquid analogous to naphtha, which constitutes the lymph. Lymph, then, is a compound of the vital spirit and the acid of the blood. Milk is formed from the mammæ by the afflux of a very mild acid, which gives a white colour to the red humour of the blood. The theory of the natural functions was no less chemical. Even the diseases themselves were explained upon chemical principles. Sylvius first introduced the word acridity to denote a predominance of the chemical elements of the humours, and he looked upon these acridities as the proximate cause of all diseases. But as everything acrid may be referred to one or other of two classes, acids and alkalis, there are only two great classes of diseases, namely those proceeding from an acid acridity and those proceeding from an alkaline. Sylvius was not altogether ignorant of the constituent parts of the animal humours, but it is obvious from the account of his opinions just given that this knowledge was very incomplete. Indeed, the whole of his chemical science resolves itself into a comparison of the humours of the living body with chemical liquids. Perhaps his notions respecting such of the gases as he had occasion to observe were somewhat clearer than those of Van Helmont. He called them halitus, and takes some notice of their different chemical properties, and states the influence which he supposes them to exert in certain diseases. In the human body he saw nothing but a magna of humours continually in fermentation, distillation, effervescence, or precipitation, and the physician was degraded by him to the rank of a distiller or a brewer. Bile acquires different acridities when bad food, altered air, or some other causes act upon the body. It becomes acid or alkaline. In the former case, it thickens and occasions obstructions. In the latter, it excites febrile heat, and the viscid vapours elevated from it are the cause of the cold fit with which fever commences. All acute and continued fevers have their origin in this acridity of the bile. The vicious mixture of the bile with the blood, or its specific acridity, produces jaundice, which is far from being always owing to obstructions in the liver. The vicious effervescence of the bile with the pancreatic juice produces almost all other diseases. But all these assertions of Sylvius are unsupported by evidence. The acid acridity of the pancreatic juice and the obstruction of the pancreatic ducts which are produced by it are considered by him as the cause of intermittent fevers. When the acid of the pancreatic juice acquires still more acridity, hypochondriasis and hysteria are the consequence of it. If during morbid effervescence of the pancreatic juice with the bile and acid and viscid humour arise, the vital spirits of the heart are overwhelmed during a certain time. This occasions syncope, palpitation of the heart, and other nervous affections. When the acid acridity of the pancreatic juice or of the lymph, for both are similar, is deposited on the nerves, the consequence is spasms or convulsions. Epilepsy in particular depends upon the acrid vapours produced by the morbid effervescence of the pancreatic juice with acrid bile. Gout has the same origin as intermittent fevers, for we must look for it in the obstruction of the pancreas and the lymphatic glands, accompanied with an acid acridity of the lymph. Rheumatism is owing to the acrid acid deprived of the oil which dulcifies it. The smallpox is occasioned by an acid acridity in the lymph, which gives origin to the pustules. Indeed, all suppuration in general is owing to a coagulating acid in the lymph. Syphilis results from a caustic acid in the lymph. The itch is produced by an acid acridity of the lymph. Dropsies are produced by the same acid acridity of the lymph. Urinary calculi are the consequences of a coagulating acid existing in the lymph and the pancreatic juice. Corrosive acids and the loss of volatile spirits occasion leukorrhea. From the preceding statement it would appear that almost all diseases proceed from acids. However, Sylvius informs us that malignant fevers are owing to a superabundance of volatile salts and to a too great tenuity of the blood. The vital spirits themselves give occasion to diseases. They are sometimes too aqueous, sometimes they effervesce too violently, and sometimes not at all. Hence all the nervous diseases which Sylvius never considers as existing by themselves, but as always derived from the acid, acrid, or alkaline vapours which trouble the vital spirits. The method of cure which Sylvius deduced from these absurd and contemptible hypotheses was worthy of the hypotheses themselves, and certainly constitute the most detestable mode of treatment that ever has disgraced medical science. To diseases produced by the effervescence of bile that he opposed purgatives, because in his opinion emetics produced injurious effects. The reason was that the emetics which he employed were too violent, consisting of antimonial preparations, particularly powder of alcrotti, or an impure protoxide of antimony. For, though emetic tartar had been discovered in 1630, it does not seem to have come into use till a much later period. We do not find any notice of it in the Praxis Chymiatrica of Hartmann, published in 1647 at Geneva. He endeavoured to moderate the acridity of the bile by opiates and other narcotics. It will scarcely be believed, though it was a natural consequence of his opinions, when we state that he recommended ammoniacal preparations, particularly his oleaginous volatile salt and spirit of hartshorn, etc., as cures for almost all diseases. Sometimes they were employed to correct the acidity of the lymph, sometimes to destroy the acid acridity of the pancreatic juice, sometimes to correct the inertness of the vital spirits, sometimes to promote the secretions and to induce a flow of the menses. Volatile spirit of amber and opium were prescribed by him in intermittent fevers, and volatile salts in almost all acute diseases. He united them with antivenomous potions, angelica, contraierva, bezoard, crab's eyes, and other similar substances. These absorbents seemed to him very necessary to correct the acidity of the pancreatic juice and the acridity of the bile. In administering them he had paid no attention to the regular course which acute diseases usually run. He neither inquired into the remote nor proximate causes of disease, nor to the symptoms. Everything was neglected connected with induction, and his whole proceedings regulated by wild speculations and absurd theories, quite inconsistent with the phenomena of nature. End of section 20. Recording by Paul King, Mississauga. pjk.scripts.mit.edu/pkj